All right, hello everyone. Welcome to the Climate Variability and Change Working Group. Thanks for coming. So I'm going to kick us off with the CVCWG update on behalf of the other co-chairs. Aishu Hu is there, and Sarah Larson, who unfortunately couldn't join us, but she's online. And then the liaisons, Adam Phillips and Gary Strands. So first of all, just a reminder of the code of conduct. Please be respectful in your feedback. And a reminder about this Slido QR code. This is not for this session, but for the very end of the day when we have the overall discussion. Please put your thoughts and questions for the overall discussion in there. So first of all, just a reminder, this is nothing new here, but just in case any of you are new and unfamiliar with the things that are going on in the working group and kind of associated with that, we have two big data sets which might be of use. We've got the CSM2 large ensemble. This was not run by the working group, but working group members participated in this. So this is a 100-member ensemble of coupled simulations that go over the historical period and out to the end of the century under SSP 370 scenario. And then what was run by the working group is the single forcing large ensemble, where you can decompose this all forcing run into the contributions from various forcings. And so if you go to the working group webpage, which I'll put up at the end of the presentation, you can find out the information of how to get at those simulations. So now a summary of kind of what's happened since the last summer meeting. So one thing which I mentioned at the last summer meeting, and I'm very excited about, we still don't really have any results, but we have finished the simulation, and that we've done this regionally refined North Atlantic AMIP simulation, which runs from 1958. Currently it runs to 2014, but we'll try and extend that to present day. And this has regionally refined 1/8 degree resolution in the North Atlantic. So I think this is kind of an unprecedented length of a simulation with that resolution. And really the motivation here is to see how does that impact on the ocean atmosphere coupling and the jet stream variability. And hopefully by next summer meeting, we'll have some results to share from this simulation and we'll be able to make the data available. Also in the realms of regional refinement, Brian Medeiros has been running this regionally refined tropical belt with regional refinement down to 15 kilometers in the tropics. These are relatively short runs, 7-year simulations right now, but they have the data that you might want to look at things like tropical waves and extremes, atmospheric rivers, tropical cyclones, and things like that in the tropics. As an example here, you can see the precipitation distribution over West Africa. The low-res model is in gray, and we do have red. So the high-res regional refinement is in red, and then the observations are in blue. So you see this much improved precipitation distribution in the tropics with the regional refinement. We've also run, just with the regular 1 degree model, an SSP 585 ensemble. So the large ensemble, the 100-member one, is 370. The working group previously ran a 245 ensemble with 16 members, and now we have the 585 ensemble with 15 members. So we're really spanning the range here of the forcings, and all this data, again, is available for download you can get to it from the working group website. We've also run a 3-member ensemble of these RF, MIP, PI, CLIM, HIST-all experiments. So these are experiments where you run with prescribed climatological sea surface temperatures from the pre-industrial control, and then you run with the historical forcing. So it's really to look at the kind of direct effect of the forcings. You can use it to diagnose a transient effective radiative forcing, and just look in general at what do the forcings do by themselves without the sea surface temperatures responding. And again, these are available through the website. We've run a suite of simulations with this 83 level grid. So as you may have heard in other sessions, CAM is moving to have an enhanced vertical resolution. It's going to have an 80 kilometer top and 500 meter resolution in the free troposphere. So you can see the old grid here in the black and the new one in the red. In CAM7, everything's going to change. And so here what we've run is simulations just with the change in resolution and the model lid in the free troposphere and lower stratosphere. We have not changed the boundary layer resolution, which is another thing that's going to change in CAM7, because when you do that, you have to retune the physics and it becomes a different model. So this is kind of a clean comparison between the current grid and what the new grid will be. And the big thing that this gets you is the quasi-biennial oscillation, and of course an improved representation of the stratospheric polar vortices. So we have a 3-member ensemble of coupled simulations and 3 AMIP members, and they're currently being kind of uploaded to the Climate Data Gateway, so these should be available for download in the coming weeks. Some work that's been going on with collaborators Flavio Lehner and Yaning Kuo at Cornell. Unfortunately, Yaning, she was supposed to do a talk in the session, but she's sick, so that she's unable to do that. But they've been looking at what could happen as a result of alternative histories of sea surface temperature variability. So over the historical record, this is the sea surface temperature trends we've had. And this is the associated sea level pressure trends that you get in the model with those SSTs, and you get a drying over, or maybe this is the observations actually, a drying over the southwest. But of course, this is just one realization of the combined influence of forcings and natural variability, and the natural variability could have done something else. And so they've been using a linear inverse model to come up with different alternative histories of natural variability, and looking at, well, what could have happened if we had a more negative PDO like sea surface temperature trend, or a more positive PDO like surface temperature trend. And interestingly, what they find is that kind of no matter what the sea surface temperatures are doing, there's more of a tendency to have an anomalous high over the Pacific Northwest area and drying of the southwest. So of course the sea surface temperatures make a big impact, but there's something else going on in the underlying forcings or the kind of global warming itself that's kind of leading to this prevalence of a high pressure and more drying over the southwest. So they're investigating the mechanisms, and I'm sure there will be a paper coming soon about that. Kind of maybe a bit related, motivated by the fact that we predicted this big El Niño for 2023, 2024, Clara and others have been looking into the impact of this El Niño. So the Earth System Prediction Working Group run these seasonal to multi-year hindcasts, and this is the skill of these hindcasts for the August initialization. You can see it's very good. And then for the November initialization. So back last year in August, the working group was predicting this big El Niño. In November, the amplitude of that went down a little, but still a very big El Niño. And so Clara decided to investigate kind of ahead of time what are kind of the range of winters we might see as a result of this El Nino, and then all the natural variability that can just kind of happen. So they've been running these ensembles, 50-member ensembles, taking the sea surface temperatures from those predictions and looking at what they do. And then also in this framework, you can also run counterfactual experiments. So they've run experiments where you look at what if you detrend everything and look at this El Nino back in 1979, within the climate of 1979, and that's what you see in the middle row here. And then how does that change kind of the impacts of the El Nino? And I think quite aligned with the Flavio and Yaning's work, there is a change kind of as a result of the underlying trend in the climate in how an El Nino, like the one we've just had, might impact on the North Pacific circulation and other regions. There's work going on to run experiments for this TBI COEX project. So this is a project that is looking at interactions between the tropical basins. Steve mentioned this in the Earth System Prediction Working Group yesterday. They've been running initialized hindcasts in the same kind of a framework with pacemaking, where you relax the sea surface temperature anomalies towards what actually happened in observations. And so what this working group is doing is running free-running simulations with the pacemaking. So these are going to be 10-member ensembles from 1850 to 2021, where the sea surface temperature anomalies are relaxed towards observations, and there's 3 different ensembles, one with relaxation in the Pacific, one with relaxation in the Atlantic, and one with relaxation in the Indian Ocean. The Pacific ensemble is completed, and then the other 2 are still to run. And then finally, for the updates, there's a new version of the Climate Variability Diagnostics package, thanks to Adam Phillips and Clara Desser. So this is combining the utilities of the original CVDP and then the more recent CVDP for large ensembles, which has features like what you see here, where you get kind of nice summaries of the representation of things for across members and then across models. And Dave showed this on Monday, where CSM2 is really good in this particular metric. This also has new detrending options. I think before, primarily, it's a linear trend was being done to kind of isolate the variability from the long-term trends. Now you can specify options, linear or quadratic detrending, 30-year high-pass filtering, or in the case when you have a large ensemble, you can remove the ensemble mean. So if you have questions about that, you can contact Adam or Clara. Okay, we still have a little time left on the current allocation, and these are some of the things that are planned for that remaining time. So one is to run an aerosol-only ensemble with CSM2, but with the CMIP5 aerosol forcing. So this is motivated by a couple of things. Marika Holland and Cecile Hane ran an ensemble of all forcing simulations with CSM2 with the CMIP5 forcings. And then we also find somewhat different aerosol forced responses in the single forcing large ensemble between CSM2 and CSM1. So running CSM2 with the CMIP5 aerosol forcing would allow us to know what is the difference between differences in the model and what is the impact of differences in the forcings themselves, because the forcings were pretty different between CMIP6 and CMIP5. As you can see up there. This needs a little work to figure out exactly how we impose this forcing. It's not totally straightforward because we want to start from the CMIP6 pre-industrial control as the baseline. So I think we need to be taking the anomalies of the historical CMIP5 forcings from the pre-industrial control and be adding them on to CMIP6. And we need to make sure they don't go negative or that will be problematic. So we haven't got those running yet because there's a bit of work we need to do to figure out exactly how to do that. There's also a plan to do a volcanic-only ensemble. This is really motivated by some other things that we saw in the single forcing large ensemble. And you kind of transition from having these volcanoes punctuating the historical record to going into just kind of a steady aerosol forcing. And there were some indications that might be leading to a warming as you go into the SSP scenario. So this ensemble was planned to investigate that, and also in general it will allow people to investigate just the impact of volcanoes alone. And then finally, the pencil model. This has been going on for a while. There's been various technical issues of getting this pencil model up and running, but Young-O, who's leading this project, thinks it's close. So this is basically in between a slab ocean and a coupled ocean, where you just have a single column ocean model at every grid point, and that allows you to have things like prognostic mixed layer depth. And so Young-O thinks it might be ready to start running along pre-industrial control with this configuration. So that'll be exciting if that actually can happen in this allocation. If not, maybe we'll do it next time. So that's all I have for the summary. I think we have a couple of minutes for questions if anyone has any. We're going to have more time for discussion at the end, so please be thinking about things you'd like to see the working group do in the next allocation. We'll be writing the proposal later this summer, so now is a good chance to speak up if there are any things you think would be important for us to be doing. So with that, I'll finish. Does anyone have any questions? All right. If not, I guess we will move on to the talks. So you have 10-minute slots for the speakers. I'll stand up at 7, and that will be your kind of cue to wrap up. The laser pointer is a little difficult to deal with. You've got to hold it down, and sometimes it goes to sleep, so you might have to hold it down for quite some time until it starts, but hopefully you can figure that out. Okay, so we'll start with our first speaker, who I believe is Jerry Neal. Okay, so yeah, Jerry Neal talking about processes that contribute to future South Asian monsoon differences between E3SM and CESM.
All right, thanks, Isla. So I wanted to acknowledge my co-authors on this work, and the results I'm going to be talking about in this 7 minutes are summarized in 2 papers. One was published about 6 months ago, and the other one is currently under review. So just to motivate why we're interested in the South Asian monsoon, 2 billion people more or less live across this region. If you look at the summertime maximum precipitation here in this plot, you can see that the South Asian monsoon encompasses areas of India, Southeast Asia, and southern China. So of course, it'd be interesting or of interest to accurately predict this and do it on all timescales, but to do that, you have to understand the processes and mechanisms that can provide the skill. And so that's what we're doing here. We're trying to understand processes and mechanisms. So the question we're asking here is, how does the climate base state, and there are 2 aspects we're going to look at in the base state, are tropical sea surface temperatures and ENSO amplitude. How do these affect the Walker circulation, the large-scale east-west circulation that connects South Asia and the Pacific, and the consequent monsoon ENSO connections in present day and future climates? So we've got 2 Earth system models, CSM2 and E3SM2. We have historical and future climate simulations, 20 Ensemble members each. And the first kind of base state difference we can see between these 2 models is that if you difference the E3SM minus CSM2, you see that almost all the tropics are about a degree colder in E3SM compared to CSM2. So that's one thing to keep in mind when we're talking about this. The other is we're looking at ENSO amplitude, and so these are the spectra of Niño 3.4 sea surface temperatures for present day climate. If you look down here at the bottom plot, this is kind of the summary. This is CSM has this big peak here, and E3SM is kind of closer to the observation. So a notable feature of the base state differences for ENSO amplitude is CSM2 is about twice the amplitude of E3SM2. So how does that get affected? How does that affect these large-scale teleconnections between monsoon and ENSO? We can look at that by doing a regression of Niño 3.4 SSTs onto 200 hectopascal velocity potential, and you can see that both models get what we see in the observations, where you get this kind of dipole pattern with negative values over the Pacific, positive values over the Indian Ocean. Of course, this is the indication that you get increased upper level outflow and divergence and increased upper level convergence and suppression of monsoon precipitation during El Nino events. So you get this negative correlation between monsoon and ENSO, and you see this in both models, but you see that the colors here, it's the same color scale, the colors are darker in CSM2. So when you look at the differences, you can see that CSM2 has a stronger monsoon-ENSO connection. We can say at least 2 of the things that are contributing to this are the warmer sea surface temperatures in the tropics and the higher ENSO amplitude in CSM2. Both of these act to give a bigger pulse of energy through the water circulation during El Nino events that act to influence Indian monsoon rainfall. Well, which one's more important? And we have some pacemaker experiments we analyzed, which I don't have time to talk about, but we determined from those experiments it's about half each, half ENSO amplitude and half base state SSTs. So can we kind of apply any of these things we've learned from present-day climate to understanding future climate? If you look at just the simple differences of surface temperature of future minus present for E3SM and CSM2, you can see that both of them have this kind of El Nino-like response in the Eastern Pacific, but it's much stronger and much larger in the CSM2. So that's one aspect of this base state response now, as a pattern of SST warming is much greater in the east compared to the west in CSM2. What about ENSO amplitude, which is the other thing we thought was important? If you look here at the bottom, it's kind of the summary plot here. CSM2 amplitude is pretty close in present day and future. E3SM actually gets a little bit bigger amplitude, 10 to 15% larger ENSO amplitude. So those are the two things that we think could affect these future connections. And so when you look at these regressions now and you do these differences, future minus present of the regressions of Niño 3.4 on 200 hectopascal velocity potential, you can see that for the E3SM, you get this pattern we saw before, negative over the Pacific, positive over the Indian Ocean. That indicates there's a stronger monsoon ENSO connection in the future, because the sign of those differences is the same as what we saw in the present day. But when you look at CSM2, you get this kind of interesting shift to the east. So this whole water circulation dipole is shifted to the east. Part of this is due to the fact we get this very large El Nino-like response in the Eastern Pacific. And so you've kind of shifted this center of descent, anomalous descent, kind of away from the South Asian monsoon region. And so you get a weaker monsoon ENSO connection in E3SM2 in the future. So the two things we looked at, you can see here the larger El Nino-like response and larger amplitude ENSO in E3SM2. So to summarize, in present-day climate, the key processes that weaken the monsoon ENSO connection in E3SM2 versus CSM2 are cooler tropical Indian and Pacific SSTs and reduced amplitude ENSO. Pacemaker experiments were used to show that both these contribute about equally to those connections. In future climate, the key processes that weaken these connections are the relatively larger increase in future amplitude ENSO in E3SM2 that acts to strengthen the connection, but this larger El Nino-like response in CSM2 and this consequent eastward shift of the water circulation acts to weaken that connection in the future in CSM2. Thanks.
Thanks. Do we have any questions for Jerry? Yeah, please go to the mic.
Did you look at individual events? For example, the 98 ENSO was very strong. That was also the year when the relationship between ENSO and monsoons broke down. Is that something that the models can pick up?
Yeah, that's something that's the next thing we're actually going to look at, is when you look at time series of correlations between monsoon and ENSO in these models, you do see times when the monsoon-ENSO relationship breaks down, like in the case you were talking about. And that was an interesting year because everybody thought there was going to be this massive drought in India, and it turned out the precipitation was actually suppressed a little bit to the south and to the east, so you still had this connection, but it was kind of shifted to the east. And I think that's kind of analogous to what we saw in this future climate case with CSM2. So I think it does make a difference as to the actual pattern, where the warming sets up in the tropical Pacific, and how that affects how the water circulation sets up.
Questions? We can walk a mic around if someone wants to ask one. Okay.
Yeah, a question about the regression. Did you do a concurrent regression? Because the reason I ask is because we know the relationship between JJA summer monsoon rainfall with the DDF before that JJA is different from the relationship with the following DDF. Have you considered that in the regression?
These are all simultaneous for the northern summer season, June, July, August, September. But that sequencing of the seasonal cycle is another interesting aspect of this, because we know that the monsoon-ENSO connection has a kind of a biennial tendency to it, and that would actually come into play if you're looking at seasons before and after. So I think that's would be an interesting thing to look at.
We are ahead of schedule, so if anyone wants to ask anything else, please do.
Hey, so I'm just kind of curious, did you look at all at what the eastward shift in the Walker circulation does to the average monsoon season, so not the relationship with ENSO?
Yeah, so that's also an interesting aspect of this, because and that's another part of this paper I didn't have time to talk about, but when you're looking at the future climate between the two models, and you look at across all the CMIP 6 models, even CMIP 5 models, on average, Indian monsoon or South Asian monsoon rainfall gets increases in future warmer climate for various reasons. In both these models, they both get an increase in monsoon rainfall in the future, but the CSM2 has a much smaller increase than E3SM. And this is due in part to the fact that you're getting this kind of change in the Walker circulation, that you're actually getting these warmer SSTs in the tropical Pacific are actually increasing the mean Walker circulation that affects the mean monsoon rainfall and actually suppresses what would be normally a larger increase. You don't get that in E3SM, where you get this kind of very large increase of mean monsoon rainfall for the future climate. So that's another way of trying to interpret these processes and how to say, okay, well, let's just look at the changes in the monsoon. You got to look at all these other things that are happening, especially in the Pacific, and how those affect these east-west circulations.
Great, thank you. So we'll move on to the next speaker. That's Samantha Stevenson on tropical Pacific trends in the last millennium.
It's a long ramp. Yeah, good morning, everyone. Thanks for being here. So I'm actually going to present a combination of results from both studies that have been recently published and a couple that are in prep. So I want to acknowledge all of the co-authors on these various studies. So do I advance the slides with this pointer? Okay, great. Yeah, so just as a brief motivation, so we're interested in understanding tropical Pacific trends, right? And this is something that all current generation models have extreme difficulty with, as you've probably heard during other sessions in this meeting. Right, so just as a brief motivation, here's a figure from Rob Will's paper showing that the recent trend over the last 40 years is something which is not simulated either in an ensemble mean sense or by the majority of ensemble members in most current generation large ensembles. So there's something like 16 large ensembles here. The large dots are the ensemble means. The smaller dots are the ensemble members. And you see that most models simulate an El Nino-like reduction in the SST gradient from east to west, whereas observations show a more La Nina-like strengthening. And you can't account for this strictly due to internal variability, which suggests that there is something fundamentally structurally missing or incorrectly represented in our models. On the other hand, we know that the observational estimates themselves are uncertain, right? So here's just a figure I like to show from a paper that came out in 2017, showing the linear trends in SST from 4 different observational products. And just for context, the boxes that simulate the gradient, or are used to identify the gradient rather, are shown in the black lines. The point here is that over the last century, the estimates of, in particular, the Eastern Pacific SST trend are fairly uncertain, which suggests that mismatches between observations and models are probably due to some combination of issues with the models and uncertainty in the observational estimates. So that's one thing that our group does, is to try to understand the true extent of internal climate variations in SST gradients and ENSO, right? To see, can we improve our observational estimates to increase certainty in the mismatches between models and observations. So I wanted to highlight, I know this is the Climate Variability and Change Working Group, but I wanted to highlight a paleo result just to convince you that paleo matters too, even if you're interested in future projections. So this is a paper that came out in Nature. It was led by a former postdoc of my colleague Bronwyn Konecki. And what we did was we tried to leverage a new paleoclimate product to improve our time horizon of knowledge of the Pacific Walker circulation. So I'm going to kind of alternate between atmospheric metrics and SST-based metrics, but you can kind of like think of them as different expressions of the Walker cell, right? So definitely check out this paper if you're interested. But just from some explanation of what's going on here, what we're showing is the location of paleoclimate proxies that were used to generate this reconstruction. Right, so they have different symbols for different types of natural archives. So you can use corals, lakes, all sorts of things. And these are part of the ISO2K database, which is a new product that's now publicly available. It's pretty easy to download. It's in MATLAB format. It's all standardized. You can compare it with the climate model output like reasonably straightforwardly. But yeah, so we can use this for a wide variety of applications. In this case, and the colors here are the strength of the correlation between individual proxies and the reconstruction product, right? So in this case, we use this to generate an actual statistical reconstruction of the strength of the Walker circulation back to 1200, right? So now we have a longer time history of, it's not exactly observations, but this is data informed, right? So this is our best estimate of what is going on in the real world, right? So there's a lot going on here. I don't have time to explain all the details, but just know that this is a very large ensemble of reconstructions that vary the reconstruction method, so different statistical methods that were used to project the sea level pressure gradient, which is our index of Walker circulation variability, back to 1200, and the observational sea level pressure products that were used to train the reconstruction. So there's a lot of uncertainty analysis that goes into this. So that's what all the different colored lines are. The shading is the kind of range of percentiles across members. And here an ensemble member means just a reconstruction method that varies a little bit again. The black lines are the observations, right? So, this laser pointer does like to sleep, you're right. So this is our estimate of observations. And you can see that now that we have a longer context, the magnitude of the apparent observational trend seems kind of like, by eye, you wouldn't really think much of it, right? And in fact, one thing we did was a lot of statistics to try to see how significant the recent trends in the kind of modern period are relative to this background of internal variability. And one major result from the paper was that if you consider the modern period to be the period since 1850, that is statistically indistinguishable from the background of variability back to 1200. Right? So in other words, if there's a forced response, it hasn't become detectable over the 20th century, right? So we also talk about in the paper the difference between that and the last 30 years. If you just consider the last 30 years, it's kind of on the edge of detectability, but kind of depends on which time horizon you're considering. Right, so basically, these trends are less significant than you might think if you only were looking at the past couple of decades of sea level pressure. So definitely happy to talk more about this, but just my little advertisement for it. So what's going on here? Why might this be not that significant? Well, we can turn to the models for some physical context here. So these are now some results in prep. This is a paper that's being led by my graduate student. And we're looking at isotope-enabled simulations with CESM1. Right? So these are nice because they allow you to directly compare kind of apples to apples with model and paleoclimate reconstructions. But these results are pretty consistent with results that you get from other models. Right? So what I'm showing here is the vertical pressure velocity in the pre-industrial control from CESM1, just to kind of motivate where the ascending regions and descending regions are associated with the Walker cell. Right? So you see negative pressure velocities or atmospheric ascent kind of over the warm pool, and positive velocities or descent over the majority of the eastern equatorial Pacific. Right? So that's what the Walker cell is doing in the pre-industrial. And the nice thing about CESM is you can run it with individual forcings, as Isla just motivated really nicely earlier in the session. And we have this with the last millennium ensemble as well as other simulations, or other ensembles rather. And what you can see is that there's opposing influences on the Walker cell from greenhouse gases and from aerosols. So the top panel, or sorry, actually the left-hand one is just the exact same figure I showed you, just for context. So this is the pre-industrial. And then the point is that greenhouse gases tend to weaken the Walker cell and aerosols tend to strengthen it. So where you see ascent in the pre-industrial, you see descent due to greenhouse gases and vice versa. Right, so one possibility for this limited detectability of the recent trend might be that greenhouse gases and aerosol effects have been compensating over the historical period. And this seems to be true in the CESM2 as well as other models as well. So these are just some more results from the single forcing large ensembles with CESM2 and CAN-ESM5. So as for orientation, I'm showing the time series of the east-west SST gradient. So positive is El Nino-like, negative is La Nina-like. And CESM2 and CAN-ESM5 both show compensatory influences from greenhouse gases and aerosols, but both of those things are much bigger in CESM2, right? So they seem to cancel out to something comparable in the fully forced simulation. So it's something like a, not that big a trend tending towards a weakening in the early 21st century in both models, but it's like a summation of like larger opposing influences in CESM2. And this is not just an artifact of CESM2 in particular, but rather this difference in sensitivity appears to be a feature of many large ensembles. Thanks. So this is just the change in the zonal temperature gradient between the latter part of the 21st century and the latter part of the 20th. The raw values are over here on the left. And my laser pointer, oh no, okay, whatever. Yeah, so anyway, the raw values are on the left, and the values normalized to global mean temperature increase are on the right, and shown as a function of scenario. So what I'm hoping to convince you of is that models, these are fully forced ensembles, I should say, models show different sensitivities of the Walker circulation to climate change. And that seems to be somewhat proportional to the magnitude of global temperature increase, as you'll see in the right-hand plot here. So in this case, this is CAN-ESM5, right? And this one is MIROC 6. And those show a proportional increase, decrease in the SST gradient relative to global mean temperature changes that are very different. Right? So we should understand this, is what I would like to convince you of, right? So just some conclusions, I'll just go through them super quickly. So since 1850, it looks like in the real world, the change in the Walker cell is not that big compared to our internal variability. This might be because greenhouse gases and aerosols are compensating for one another, but until we understand exactly how big those individual influences should be or potentially are across models, we're not going to be able to fully understand how to get this gradient correct for the right reasons. So that's all I had. Thanks so much for listening.
Thanks. Do we have one quick question for Sam? I should say if you're online, I'm paying attention to the chat, or you can raise your hand. I guess I had one question in the context of the last millennium. If you look at, that was all observation or paleoproxy based. If you look at the models, can you say something about whether the variability in the models is represented well?
Variability in the Walker circulation?
Or just in the, I think it was whatever your metric was in that long time series. But I mean, I guess there's a question over whether models are lacking in low frequency variability, and that's why they might be missing the trends that have happened recently.
Yeah, I would say that's entirely possible. The variability in either the sea level pressure or the SST gradient along the equator is going to be dominated by ENSO. So it's as good as the ENSO amplitude is in models, which, as Jerry just presented, is not always great. So that could be one of the reasons why we're simulating limitations with the trend. There's also, it has to be underestimation, as you mentioned, of low frequency decadal to multi-decadal variability across models. So I haven't looked at exactly how big that contribution might be to these trends, but yeah, that's another candidate explanation as well. So.
All right, thank you. So we'll move on to our next speaker, I think is Xian Wu, on pinpointing sources of equatorial Pacific sea surface temperature biases.
So, hello everyone. I will be speaking about the climatological cold tongue bias in the equatorial Pacific. This is a long-standing error across almost all of the coupled climate models. This work is part of a NOAA-funded project led by my postdoc advisor, Andrew Winterberg, and also in collaboration with several GFDL colleagues. First, I'm showing you the mean climate in the tropical Pacific. So in the mean climate, there is a sea surface temperature contrast between the Western Pacific warm pool and the Eastern Pacific cold tongue. Driven by the easterly trade winds, the equatorial thermocline is deeper in the Western Pacific than the East. Below, I will show you the biases in the 1-degree GFD or SPEAR model. SPEAR is a model version oriented for seasonal to decadal climate research. And I'm using the 1-degree resolution model here, it's called SPEAR Low. So SPEAR Low shows 2 strong cold tongue and 2 strong easterly trade winds and 2 strong thermocline tilt. These biases in SST wind and thermocline are strongly coupled and may involve error compensations. Therefore, it has been challenging to isolate the bias sources and correct these issues. Here, we will pinpoint the sources of bias from AGCM AM4 here, OGCM MOM6, and coupled feedbacks via a framework of flux adjustment. So in the unadjusted SPEAR Low simulation, the atmosphere model calculates the surface fluxes of heat Q, wind stress, tau, and freshwater F here using the SST simulated by the ocean model. In the first surface nudging experiment, we will restore the SST in the ocean model to the values based on OISST and Hadley SST with a 2-day damping of the top 10 meters of the ocean model. And we also override the surface wind stress forcing in the ocean model with the ERA interim values. So by doing so, you can see in the nudging experiment, now the SST closely follows the observed values in the equatorial Pacific. When you have the corrected SST, the AGCM will generate a new wind stress in response to that. If the AGCM were perfect, we wouldn't require any additional corrections, but we do here. So there is an explicit correction term here, delta tau added to the ocean model to compensate for any errors inherent to the ocean atmosphere model. Similarly, when we have the correct wind stress forcing for the ocean model, we still need to add additional heat fluxes to the ocean model to compensate for any inherent ocean model biases. Those are time-varying delta terms, the explicit corrections. Then we will calculate the monthly climatologies of these corrections and add the monthly climatologies of the momentum and heat fluxes to a coupled framework to the ocean model. So by doing so, we create a flux-adjusted version of SPEAR Low. In this model version, only the climatological errors are corrected. So model can generate climate anomalies by itself. Here I'm showing the one ensemble member in simulating the time series of the equatorial Pacific SST. Only the climatological biases are removed. So here I'm showing you the effect of flux adjustment on the climatological biases. These are the original biases in SPEAR Low. When we flux adjust the model, it by design removes the SST and surface wind stress biases in the ocean model. And the surface wind stress corrections also removes most of the subsurface ocean temperature biases, except for the Far Eastern Pacific. So this inherent thermocline bias is linked to the ocean mixing schemes and cannot be corrected when we have the wind stress forcing overridden. Also, the SST correction leads to the reduced AGCM errors in simulating like 2 dry cold tongue and some double ITCZ bias in the Eastern Pacific, and also reduce the easterly trade wind bias. However, there are still remaining biases inherent to the AGCM errors, especially the convective rainfall over the Western Pacific. Some of them even gets amplified when we have an SST correction. That indicates there are error compensations between the SST and rainfall simulation in the original SPEAR Low. Next, we look at the annual mean field of the explicit corrections we added to the ocean model for the delta Q heat and data tau, the wind stress corrections. So we need to add the explicit corrections of climatological westerly wind anomalies over the Western Pacific to compensate for the AGCM errors in simulating too strong easterly trade winds. Also, we need to add strong heating in the Eastern Pacific, and the heating is positive right at the equator, but negative off the equator. This pattern resembles the heating induced by the tropical instability waves. So these sub-seasonal waves can pour the cold water from the equator to the off-equatorial region, but brings off-equatorial warmer water equatorward, leaving an overall warming effect on the mean state in the equatorial Pacific. This warming effect induced by TIWs is underestimated in the 1 degree resolution ocean model. So that's why we need extra heating correction compensating that. Here I'm showing the seasonality of the surface climatological biases and heating corrections. And the SST and wind stress biases are most pronounced in the boreal spring and fall seasons. However, they are corrected by different ways. In boreal fall season, both strong heating and wind stress corrections are required for compensating the errors in both ocean model and atmosphere model. While in the springtime, the explicit corrections are weaker. That indicates the initial errors in the two components are weaker, but they are amplified when the models are coupled. We also examine the heating corrections and wind stress corrections as a function of Niño 3.4 index to look into the Ensemble dependencies. So here I'm showing the scatter plot of the net surface heat flux correction over the cold tongue versus the Niño 3.4 total SST. Each dot represents the value of the individual years from the nudging experiment, and the colors here represent the 4 different seasons. Basically, you have more corrections in the September to November, the fall season, compared to other seasons. At the same time, stronger correction is required for the La Nina conditions. This again confirms that the ocean model bias is related to the tropical instability waves, which are most active during the La Nina autumns. In contrast, the surface wind stress correction is not Ensemble dependent, indicates that the errors is more like a mean state error rather than Ensemble dependent error. And I'm sorry I have to skip this slide on TIWs and go directly to the summary slide. So we show that surface nudging and flux adjustments are effective in isolating the biases in coupled SST, not only in the equatorial Pacific, but also in other regions as well. I'm not showing it here. We identify the sources of mean state biases in cold tongue in different seasons and Ensemble conditions. That is important because we really want to pinpoint the sources exactly that can provide information for the future field campaigns when we should collect data and where we should. And those results are very important to understanding other climate variability and changes in the tropical Pacific. Thank you.
Thank you. I think to keep on schedule, we'll not take any questions, but if you have questions for Sham, please catch her at the break. We'll move on to the next speaker, that's Mahdi Hassan, on hemisphere-dependent response of the Hadley circulation to ENSO and eddy forcing.
Hello, everyone. Hi, I'm Mahdi Hassan. I am a PhD candidate from NC State. I'd like to acknowledge my collaborator, Sarah Larson, my advisor, Kay McMonigal, who was a postdoc in our group, now a faculty at University of Alaska, Walton Robinson, and Anant Iyer, faculty from NC State. All right, starting with a very brief kind of overview of Hadley circulation, which you are already aware of, so I'm not going to go into like details, but what I'd like to show or share that the ascending branch of Hadley circulation is co-located with the ITCZ, where we see the maximum climatological precipitation, whereas the descending branch is located with the region where there is a minimum precipitation. So we see that the changes of Hadley circulation is really important for like the tropical hydroclimate variability. And recent observation indicate changes in the Hadley circulation due to climate change. Particularly if we talk about the strength of the Hadley circulation, which I will refer to as ACS, a warmer climate theoretically implies a weaker circulation because of reduced meridional temperature gradient, right? And in fact, the climate model shows a weakening of the Hadley circulation over the historical period. For instance, this is a figure I take from Chemke and Polvani paper where we see like a northern hemisphere Hadley circulation strength over the historical period. In the climate model, CMIP5 model shows by the blue bars shows overall weakening, whereas the reanalysis shows just the opposite of the sign of the trend. So that means there is like a high uncertainty in the historical trend, apart from the biases in the reanalysis, which has been a main focus of this Chemke and Polvani paper. There has been other study that shows that internal climate variability can also contribute to the uncertainty. For instance, like internal atmospheric variability, primarily eddy-driven, can modulate Hadley circulation strength. Alternatively, ocean atmosphere coupled variability, mostly through anomalous wind stress-driven ocean variability like ENSO, can also impact the Hadley circulation. But the relative importance of this true forcing to the interannual Hadley circulation strength variability is not really like clearly understood. So based on that, we try to answer a couple of science questions in this talk. Is what is the relative importance of these eddies and wind-driven ocean modes to the Hadley circulation strength variability? In particular, we'd like to know like how much ENSO alone contribute, and then like do the potential drivers operate in one or both hemisphere? And we answer this using CESM 2 like 1 degree resolution model experiments under pre-industrial settings, so like there is no external forcing. The first model experiment is fully coupled, or FC. We know that it has all the important climate variability like ENSO IOD, Atlantic Niño. The next one is mechanically decoupled model. I will call it as MD. So it is very similar to fully coupled model, except in the global ocean there is like no anomalous wind stress. So like the climatological wind stress is prescribed over the ocean. But note that the atmosphere can freely evolve, and there is like the thermal coupling between ocean and atmosphere. So, because of the lack of anomalous wind-driven ocean variability, there is like no Bjerknes feedback that can, contribute to the ENSO and other wind-driven ocean variability. For instance, if we look the Niño 3-4 index between like FC and MD simulation, we see that the gray color, which is like the MD simulation, does not have any ENSO variability. And throughout this talk, whenever you see the difference between FC and MD, that kind of implies the role of anomalous wind-driven ocean variability. And both of these model outputs are freely available in Climate Data Gateway. I don't want to talk too much on these things because I will be running out of time, but the way I calculate Hadley circulation is based on meridional stream function, and I calculate Hadley circulation strength as a maximum value of the stream function from the corresponding hemisphere. And this is just a fully coupled model, like shows the mean Hadley circulation are very similar. All right, let's talk about like interannual Hadley circulation variability. Looking at the northern hemisphere, we see that the Hadley circulation strength anomaly between two models are pretty similar. So that kind of says that the wind-driven ocean circulation variability is not really important, rather like common, probably atmospheric forcing can drive the variability in the northern hemisphere. In the southern hemisphere, we see quite a different story. We see like anomalous wind-driven ocean circulation may potentially may increase the Hadley circulation strength variability in the southern hemisphere. So So we see the difference in the northern and southern hemisphere. Now going into the northern hemisphere, we just see that the wind-driven ocean circulation is not really important in driving northern hemisphere Hadley circulation strength variability. And we know from the literature like atmospheric eddies can be important. So what we do next is look at the composite mean of like upper atmosphere eddy momentum flux divergence for a strong and weak Hadley circulation. And what we see here is that for a stronger case, there is a divergence of anomalous eddy momentum flux in the subtropic, whereas for a weaker Hadley cell, there is a convergence. And we just further take a look at, like by looking at the scatter plot, we see that both models shows a strong correlation with the eddies and northern hemisphere Hadley cell strength. We also take a look at the southern hemisphere. There is a relation with the eddies, but it's not as much strong as what we see in the northern hemisphere. In the southern hemisphere, we see that wind-driven ocean circulation variability increases the Hadley circulation strength variability. And since ENSO is a big player, and so what we did next is look at the relation with ENSO. So what you see here is a scatter plot between Niño 3-4 and southern hemisphere Hadley circulation strength. What really comes out is like in fully coupled model, there is a like strong correlation. But in MD, there is not, and that makes sense because by definition, MD simulation does not have a ENSO variability. In the northern hemisphere, neither of the models really show any robust correlation with the ENSO because we see that the eddies are really modulating here. So the next question is like, how much ENSO alone contribute compared to other variability, wind-driven ocean variability, and we did further experiment with the mechanically decoupled thing, and we find that the majority of the wind-driven ocean variability that modulate Hadley circulation strength is basically coming from ENSO, we see from the purple bar. So in summary, we see that the eddies are really important in northern hemisphere, but ENSO is the really driver of the southern hemisphere Hadley circulation strength. And yeah, and we believe that the reason for ENSO asymmetric influence is because of ENSO-related heating and precipitation is concentrated in the southern hemisphere. As you see, when we regress SST and precip with the Niño 3-4, the color and the shadings and the contours are mostly concentrated in the southern hemisphere, where the black line is the mean ITCZ location. All right, with that, I'm happy to take any question.
I think we have time for one question. Yep.
That was very interesting. But one of the differences between the northern and southern hemisphere is the southern hemisphere has the South Pacific convergence zone. And that sometimes complicates interpretations of Hadley circulation. I was curious how the SPCZ affected your interpretation of these connections.
South Pacific convergence zone. I'll be honest, I haven't thought about like the role of South Pacific convergence zone onto these, but yeah.
Very much. We'll move on to the next. It's Kai Huang on the QBO modulation of atmospheric rivers.
Morning everyone, I'm Kai Huang. I'm an ASP postdoc working at CGD, and I'm going to talk about QBO's influences on the AI climatology today, and just would like to acknowledge contribution from my co-authors before I start. So a very brief introduction of atmospheric river, or AR. So AR refers to this Pineapple Express of the water vapor transport from the lower latitude to middle and higher latitude. And they are the main engines of water resources in many coastal regions, so it is really important for us to understand AI activities for better water management. So why do we think the QBO may have a potential influences on the AR? First, we see a strong QBO modulation of the MGO in the observations, and based on that, there are already skillful predictions of the California AR landings using the both QBO and MGO indices, and also QBO has shown strong impacts on the northern hemisphere winter storm tracks, which is another important factor for the AI activities there. However, these previous researches only use a single air detection algorithm or focusing on the single season for a single region. So we started to ask our questions. So how confident can we say about the potential QPO's influences on the Northern Pacific air activity there? Or if we do that, such kind of diagnostic, but using different air detection algorithms, will be any differences there? And are there any seasonalities for this potential connection between the QPO and the AR? And we also did the analysis for other regions, but due to the time limit of this talk, I'm only going to talk about the Northern Pacific AR here. So this, to answer these questions, we are using the EF85 reanalysis data and define our QPO phase on the 50 hectopascal with the lunar mean, lunar wind. And we use 3 air detection algorithms as listed here, the Grant-Willser, Montague, and RIT 500 to detect the air activities from the 1980 to 2017. So these animations are showing you the composited seasonal mean air frequency over the Pacific Ocean domain detected by 3 algorithms here, with the lines giving you the results from the QPO westerly seasons, and the shadings are giving you the results from of the differences between the QPO easterly and QPO westerly season. 2 things we notice here. First, there are indeed organized differences in certain seasons over the Northern Pacific region. And secondly, for these organized differences, there are high consistency among 3 selected air detection algorithms. That is to say, AIS indeed influences the, QPO is indeed influences air there, and it is very confident. So to better show you how QPO may influence air there, we created these formula diagrams with x-axis showing the seasons and the y-axis showing the latitude of the air frequencies. The lines here represent all season mean air frequency, while the shadings represent the differences between the QPO easterly and QPO westerly seasons. So from the DJF to the ASO season, we are seeing a decrease of the air frequency around the center of the air climatology and around the northern boundary of the air, all season mean air climatology, we are seeing an increase. That is indicating a poleward shift of the air climatology in the QPO easterly season than in the QPO westerly seasons. And this poleward shift of the air climatology will leave significant impacts on the local air frequencies around the basin. So here, these line plots are the linear correlations as a function of the seasons between the season mean QPO index and the season mean air frequency average around these domains across the Northern Pacific Ocean. So 2 seasons are standing out. First one is the FMA season. So for example, for the Northern California season, So for the Northern California season at the for the Northern California region at the FMA season, we are seeing a significant positive correlations between these 2 indices. That is to see during the QPO easterly phase, we are supposed to still see a decreased landing ARs over the Northern California. And for the Gulf of Alaska region and the northeastern Japan region, we are supposed to see an increase of the air frequency in the QPO easterly phase. Another season standing out here is the ASO season. We are seeing a decrease of the landing air frequencies for the Gulf of Alaska in the QPO easterly phase, but an increase of the landing air frequency over the northeastern Japan region. So what are the plausible mechanisms for the QPO's influences on the air climatology here? The first thing we thought is about the QPO's changes in the background mean state. So here are the composited maps for the selected variables as listed here, and for the seasonal mean differences between the QPO easterly GFM season and QPO westerly GFM season. So basically, during the QPO easterly phase, we are seeing an anomalous day 500 high centered at the northeastern Pacific, which will generate these anticyclonic wind gyres in the lower troposphere, and under the guidance of these wind anomalies, air activities will propagate into the higher latitudes rather than into the lower latitudes, which will contribute to the poleward shift of the air climatology we see for the QPO easterly season, as shown by the last few slides. And another plausible mechanism for such QPO air connection is the QPO's modulation of the MGO teleconnection. So these are the similar composited maps for the same selected variables, but these composites are now done for the Penta 1 and the Penta 3 after MGO convection is detected over the Indian Ocean for the Cubial easterly season and for the Cubial westerly season, respectively. So for the Cubial easterly season, we are still seeing this anomalous D500 high, which could generate these anticyclonic gyres and guide the air activity to propagate into the higher latitudes. For the Cubial westerly season, however, the MGO teleconnection patterns are first very weak, and they could not persist as long as we see during the Cubial easterly seasons. So due to such significant differences between the MGO teleconnections modulated by the QBO, this also contributes to a poleward shift of the air climatology over the North Pacific region in the Cubial easterly season. So finally, some takeaway messages here. One thing I would like to mention here is that other than the Northern Pacific Ocean domain I showed during this talk, we are also seeing some high agreed connection between the QBO and AR for other regions, such as the Atlantic Ocean region, as shown by these animations here. So if you are interested in it, please come and talk to me during the break. And that's the end of my presentation.
Thank you. So Adam's going to walk the mic around, so don't be shy if you feel like you're sitting too far from there. You can ask a question. So do we have any questions? I guess I have a question to start off. I think there's a prevalence of La Niña conditions during QBO easterly years in the observational record. Have you accounted for that?
Yeah, I did not show this figure here, but we did separate the not only the QBO phases, and also the Ensemble phases, only during the QBO easterly and QBO westerly phase composite. In the El Niño or La Niña phase, I don't remember it clearly, but the conclusion does not change much. Yeah.
Any other questions for Kai? All right, well, thank you very much. We'll move on to the next speaker. That is Lucas Ellison on quantifying the roles of structural uncertainty and intrinsic variability in drought over central North America.
Yeah. Hi, I'm a PhD candidate at the University of Hawaii at Manoa. Today I'm going to be talking about some of the work I've done with the help of my advisor, Sloan Coates, where we're trying to quantify the roles for structural uncertainty and intrinsic variability when determining the ocean atmosphere conditions that drive drought in Western and Central North America. So in this talk, I'm going to be comparing simulated droughts to an observed event, and that is the 2011 to 2014 Western and Central North American drought. This was one of the driest and warmest 3-year periods on record at the time. It was formed by a characteristic La Niña conditions where there was a high pressure ridge that formed over the North Pacific that stretched over Western North America. It diverted the storm track, so rainfall didn't fall in Western North America. There were several impacts of this drought, including estimated surface water shortage of nearly 10.7 billion cubic meters, as well as $2.7 billion of total economic loss. Because of these impacts, it's important to be able to effectively simulate these events and potentially predict them in the future. Which brings me to my motivations for my research. These are the main questions we are hoping to answer. First, are simulated droughts effectively representing observed droughts? By that I mean, are the simulated droughts we see in climate simulations, are they at all like observed events as far as the spatiotemporal characteristics like size and shape? Are the drivers the same? Are the impacts also the same? Are the large-scale drivers of the droughts consistent in simulated droughts? So are the ocean atmosphere conditions consistent among simulations? And finally, how much of the inconsistency across droughts can be explained by complete randomness or that intrinsic climate variability that's intrinsic to the climate system, and how much of it can be explained by differences in climate models or structural uncertainty? So to start, I'm going to first talk about how we identify droughts in simulations. So here we have a latitude, longitude, time grid. Each of these is a space-time grid point with a standardized precipitation value. What we want to do is assign each point as to either in a drought state or in a normal state. And we do that by using this drought identification algorithm that we have that leverages the known spatiotemporal consistency of drought. So it takes the standardized precipitation at each grid point, as well as the drought state of neighboring grid points in space and time, and pulls out distinct clouds of droughts from the data. And when you run the algorithm, you get this as the 3D output. Each of these was identified as in a drought state, and while we did apply this to the simulations, what I'm showing here is actually that 2011 to 2014 drought. And we can say a couple things about this drought. First, we can define the size, which is the total number of space-time grid points, which is 818 for this drought. However, size can change for a number of reasons. A drought can be spatially extensive but temporally small, or it can be short in time but very spatially massive. So we define two more characteristics, which is the spatial extent, which is the maximum number of spatial grid points in any month of the drought, and temporal extent, which is at any one location was the largest consecutive number of time steps in a drought. So for this drought, that is 42 and 34. As far as the data that we used for this study, we looked at 19 different climate models and 570 simulations. Those are all listed here on the table on the right. That was 85,000 simulation years, and from that we were able to identify 227,716 distinct drought events. Now what we want to do is narrow those 200,000 drought events down to the ones that are most similar to the observed event. So we first start by defining a location criteria. So in the center here we have the geographic center of mass of the observed event, and we decided that we only wanted to look at droughts that were within 600 kilometers of the observed event, or that outer circle. And after doing that, we narrowed down those 200,000 drought events down to only 4,337. So now what we want to do is narrow down those 4,000 droughts to the ones that are most similar as far as their size, spatial, and temporal extent. And for our study, we used a number of different thresholds, but for today, I'm going to be talking about our 30% threshold. And so for a drought to be selected, it must have a size, spatial, and temporal extent value that is within the 30% closest values to those of the observed event. So what I mean here is, for example, here is the observed temporal extent. That 42 is in this red line here. This shaded box around it is the 30% closest values for temporal extent. And for a drought to be selected, it has to fall within this shaded box for temporal extent, as well as spatial extent and for size. So that's how we started to narrow it down. So those 4,300 then was narrowed down to the 670 most similar droughts as far as size, spatial, and temporal extent. So now we're going to start to look at some of the results. So here we have the average correlation coefficients for the simulated sea surface temperature time series and the observed sea surface temperature time series for those 670 droughts in the observed event. As you can see, the correlation coefficients here are relatively weak. However, we did find that there was 43.2% of the grid points were significant. And so now I'm going to talk about how we define significance, because it'll be important for my results later on. To define significance, we did a Monte Carlo analysis, so where we randomly selected 670 droughts, the same size as that set that was identified. We randomly selected 670 droughts from those 4,000 droughts that were identified at the distance criteria. We then calculated the average correlation coefficients for that random set, and we repeated that 1,000 times. And so for a grid point here to be significant, it means that it was the actually selected 670 droughts had a higher average correlation coefficient than 900, at least 900 of the randomly selected sets. Sorry. But this figure doesn't really tell us anything about the intrinsic or structural variability that we want to look at. So what we're going to do next is break out those 670 droughts that were selected by individual model and perform two similar significance tests. So for the first test, we're going to compare the consistency of each individual model to the consistency of 1,000 randomly selected sets of droughts from the same model that met the distance criteria. And for the second test, we're going to compare the consistency of each individual model to the consistency of 1,000 randomly selected sets of droughts from different models that met the distance criteria. So we're going to look at the percentage of significant grid points when you're comparing droughts from one model to only droughts from that same model, and significance when you're looking at one model compared to only droughts that were produced in other models. And so we'll start to get a sense of structural and intrinsic variability by doing this. So for the first test, when we're comparing only to the same model, we have the average correlation coefficients for all the droughts from each model. So as you can see, there's a wide range of maps here. Some areas do appear to be relatively consistent, such as like the North Pacific. You can see there seems to be higher levels of consistency there. So we do think that that area is important for producing droughts in the simulations. However, the total number of significant grid points varies quite a bit. So in the title of each figure next to each model, that is the percent of significant grid points, and it ranges from about 10% to 35%. So moving on to the second test, where now we're comparing it to the other models. The maps are the same as far as the background colors. However, the stippling is now this second test. In the title, we have The first number is the significance from the first test, and the second number is the significance from the second test. And as you can see, there is most of the models show an increase in significance when you're comparing it to other models versus itself. However, to visualize this better, I have one final figure where we plotted the percent significance from the first test, comparing it to the same model here on the x-axis, and we have the percent significance when compared to other models here on the y-axis. And as you can see, most of the droughts fall above this one-to-one line. So this means there's more significance when comparing against droughts in other models versus droughts in the same model. So we interpret this to mean that for these ones above this one-to-one line, structural uncertainty is playing a larger relative role compared to intrinsic variability. And you would expect intrinsic variability to fall below this one-to-one line. So just to summarize, we identified droughts in climate models using only the precipitation values of each grid point and the neighboring grid points. Droughts in climate models are associated with a wide range of ocean atmosphere conditions. I didn't have as much time to get into this, but we did a previous study that showed droughts can arise from a wide range of ocean atmosphere conditions in climate models. And the main takeaway is that most model simulations show an increased structural uncertainty compared to intrinsic climate variability, suggesting that there is a possibility of eventually reducing this uncertainty and increasing the predictability of these drought events in the future. So, yeah, thank you.
Any questions? Yep.
Thank you. That's a lot of really great work. I'm just curious, have you thought at all about kind of doing that same statistical testing and all of that instead of being in like a number of grid point space in an area space where you can like transform the number of grid points to be proportional to the amount of area of the globe because not every grid point's the same size?
Yeah, no, we haven't done that yet, but that's a good idea. We could try to do it. I haven't thought about it, but yeah,
Okay.
that would be something to think
Just
about.
weighted by the cosine of latitude.
Yeah,
Very
that
doable. Yeah.
would be good.
Any other questions? Yeah.
I missed it. Can you please explain how did you use the precipitation data? Was there some threshold that you used to specify when the drought
Yeah,
condition?
for the precipitation data, we have this in the drought identification algorithm. It looks at specifically grid points that are one standard deviation below the historical mean at that region, and then we also weigh the drought state of neighboring grid points as well.
Okay. And you mentioned that it's only precipitation data. You're not looking at land conditions, for example, soil moisture. Do you plan to use that in
we
any?
have done it. So in this one, it's just precipitation. We've done it with P-E as well as other drought indices, and you get pretty much the same result. The overall results are the same. The shapes of the droughts are a little different, but overall, it doesn't make much of a difference, at least for this region.
Thank you very much. Our next speaker is Kyle Hablum, Renewed Mass Balance Framework for Regional Precipitation Change, leveraging the atmospheric water cycling rate.
Okay, thank you everyone for being here. I'm Kyle Hablum. I am a PhD candidate at the University of Victoria. Today I'm going to be talking about work that we've done trying to better understand what causes spatial changes in mean precipitation globally. Before I do that, I'd just like to acknowledge both the guidance and collaboration from Adriana Bailey, who is a relatively new faculty member of the University of Michigan, as well as Hansi Singh, who is now the CEO of Planet AI. Okay, so I'll start with a little bit of what we do know right now. So what I'm showing here is a figure taken from the IPCC AR6, which shows the multi-model mean precipitation change. What I'm showing here is fall precipitation, but it's essentially the same story throughout the year. Generally, what we can see is that we expect precipitation to change with a very general pattern that's consistent with changes in moisture divergence under warming, where we get this colloquially termed wet get wetter, drier get drier response, where we see wettening within the deep tropics and mid to high latitudes, as well as drying within the subtropics. And so this response sees quite a bit of agreement between models. However, when it comes to anything more specific than that, it's really difficult for these models to agree. So if we look at this figure here, any of this stippling shows regions that have less than 80% agreement across models on even the direction of change. So whether we'll see an increase or a decrease in precipitation. So this is honestly a little problematic as we live on these scales, as we live on these smaller scales. We would argue that part of the reason why it's so difficult to get these models to agree is just because there's so many different factors that result in this precipitation change. Furthermore, because, in our opinion, we still lack very fundamental frameworks for understanding what causes these spatial changes in mean precipitation, it really hinders our ability to decide which models to trust the most. So, in order to try and approach that problem, we asked a set of 3 questions. So first, is there a way that we can develop a more comprehensive and mechanistic framework building upon all of the knowledge that we have now to understand how this spatial pattern changes under warming? Can we understand these changes as a set of intuitive physical drivers? And then which of these drivers are well constrained amongst both ESMs, but also different warming scenarios? So to tackle that, we started with this mass balance framework to understand precipitation that was developed by Hansi Singh and colleagues back in 2016 and in a couple different papers, where we can describe precipitation as the aggregate result of evaporation, both locally and remote, transporting into any given location. So we can constrain that precipitation by knowing the amount of evaporation from each source. We can then weight that by the fraction of that evaporation that results in precipitation at any location. So essentially just taking the linear sum of those fractions in evaporation. So this seems, a little oversimplistic. We're probably just, completely constraining a system. However, this gives us a lot of power because we can then try to understand changes in precipitation via 2 orthogonal drivers. So if we take the linear approximation of changes in precipitation using this framework, we can understand changes as due to changes in global patterns of evaporation and the amount that is evaporating from each of those source regions, as well as due to changes in the relative importance of each of those source regions to each precipitation location. This is essentially telling us what's the change in redistribution from moisture sourced from each location to locations of precipitation. So we can then approximate this fractional contribution term and look at how each of these orthogonal terms influence precipitation within CMIP6 simulations. So what I'm showing here right now is the zonal mean precipitation response to warming in 5 different CMIP6 scenarios. So 2 idealized scenarios, the 1% CO2 and abrupt 4 times CO2, as well as warming from historical and 2 SSP scenarios. Within this, we can see, as expected, we see that deep tropic wettening, drying within the subtropics, and increases in precipitation within the mid to high latitudes. We can then look at the influence from each of these terms. So I left the total precipitation response in those faded dashed lines for comparison. If we first look at the left, we can see the response in precipitation that is due to increases in evaporation under warming. We can see that this is a relatively homogeneous response spatially, that this increase in evaporation tends to increase global precipitation. However, when we look to the right, we can see that this spatial pattern in precipitation change is really driven by this redistribution of moisture from its source region to where it precipitates. So what we argue is that if we really want to understand these shifting patterns, we really need to better understand this redistribution. So for the sake of time, I'm going to skip a lot of derivation and just skip to some results that we have. So it turns out that we can actually really well approximate this spatial redistribution of precipitation using this term here. So eta representing the fractional change in evaporation, alpha representing the fractional change in moisture flux divergence. And what this tells us is that this redistribution can be explained very well just by locally disparate changes in that evaporation and moisture divergence response. If we then make two, admittedly fairly large assumptions and recognize that we can really fairly well approximate to first order this alpha term or the fractional change in moisture divergence using a change in near surface specific humidity following arguments of Held and Soden and many other approximations after that, as well as recognize that both this alpha and eta term are actually roughly constant globally. This allows us to approximate this term even further using this gamma term. So this gamma, okay, going a little slower than anticipated. I'll speed it up. So we can use this gamma term. This gamma term is actually the global water cycling rate. So this is the inverse of the average residence time of moisture in the atmosphere. When we approximate this redistribution using this term, we can see really important features pop out. So we see this subtropical drying, we see increased moisture into the deep tropics, and increased moisture to the mid and high latitudes. Furthermore, this reduction in water cycling rate with warming, as expected, we see consistent increases in moisture transport length. So this is the length that moisture transports from its evaporative source to where it precipitates. So under warming, we see this reduction in water cycling rate, this increase in transport length scale, which is then consistent with this approximated pattern here, where we see increases of moisture leaving the subtropics into the deep tropics and mid to high latitudes. Yeah, I already said that. Something that's really important from this is that this reduction in water cycling rates, as well as this increase in transport distance, is actually incredibly robust across both models and scenarios. So we see consistent changes across them all. We also see fairly consistent changes across these models. So, fairly strong correlation across models and scenarios. Furthermore, this global water cycling rate actually has, at least within simulations, a really strong signal-to-noise ratio. So on the top is the global mean precipitation. As is well known, this is a highly variable metric. Really difficult to see any kind of emergence in the real world. However, with this water cycling rate, it gives us hope to potentially be able to intuit some of these changes occurring. Lastly, and I'll finish with this, I know I'm probably going way over time right now, I think this opens up an opportunity. CSM, or versions of CSM, have the capability to directly compute these water cycling rates. So in this work, we've had to approximate it using global means. These transport lengths are using a very simplistic approximation. However, we can directly compute these within some of our models. So CSM1 has a version developed by Jesse Nussbaumer and a bunch of other people that allows us to tag moisture back to its source region, allowing us to compute these transport length changes, as well as work by Richard Fiorella recently that has put process tracers into CAMP6 to allow us to directly compute water cycling rates, as well as residence time and transport lengths. So that's everything I have. I'm assuming I don't have any time for questions, but I'm super happy to talk to anyone afterwards, or please reach out to me with either of those emails.
Take any questions, but speak to Kyle in the break if you have any. Our final speaker of this session is Rich Neal on teleconnections in CESM and E3SM.
Yeah, so this is some work as part of the NOAA Model Diagnostic Task Force. So we're trying to develop processor-oriented diagnostics to look at the general circulation. And our focus in this set of diagnostics is essentially looking at the rosy wave propagation in the North Pacific and the certain pathways that lead to that from the tropics. There's a couple of examples that kind of illustrate that varies quite a bit. Cam 5 was pretty poor on the bottom left here, but Cam 6 was much improved. And the questions we want to answer relate to internal variability and then model differences. So what are we focusing on here? So essentially, we're going to examine composite Niño 3.4 related quantities in different model versions and reanalyses. And as it relates to rosy wave source, which is key for the PNA pattern and the rosy wave propagation, we really are interested in looking at the diabatic processes in the tropics. And it turns out the kind of three key regions for rosy wave source within the tropics and actually in the initiation region in the Central Pacific are listed here. We will just focus on the two tropical regions. And our kind of serial way of thinking the paradigm of what we're trying to do with developing these diagnostics is essentially moving from left to right. So on the far right-hand side, this is kind of well established about how tropical, barotropic disturbances related to rosy wave source terms related to divergence occur. But we're interested in trying to traverse this space of this somewhat simple, obviously, paradigm. And I myself am really interested in how the individual parameterized processes lead to heating in the tropics, vertical velocity, and the distribution of divergence. And we'll focus just on these two aspects today, given the time. So here we have reanalysis, and in a lot of these figures, I'll be circling the region here in the bottom left, so this is the West Pacific. And we can see that there's pretty good agreement in mean divergence in the West Pacific here amongst these kind of more recent, oh no, that's not true actually, the selection of reanalyses. The Niño pattern makes sense, you're reducing divergence. The Niño pattern also makes sense, you're increasing divergence, but there is disagreement. It's important to know there's a disagreement here in the West Pacific, but generally, mostly agreement. Now, if we look in this Central Pacific region here, which is key, obviously, for the increased the Niño 3.4 SST region and upper tropospheric divergence that's driving the rosy wave source, we can see there's a lot of variability amongst these particular analyses. And even in the mean here, there's a lot of disagreement about whether it's deep convection, somewhat shallow, and mid-level convection implied from these divergence profiles. And of course, in the Central Pacific, this is a region where there's not many observations to constrain the analyses. The Niño anomalies and the Niñan anomalies are kind of consistent here. But it's important to know when we're dealing with this important divergence levels, it does vary related to the anomalies and the climatology. So that prompts us to kind of, if these reanalyses are so uncertain, how uncertain are they in model simulations? And can we look at the multi-decadal variations in El Niño variability and how that's communicated through diabatic processes? So, let's go back again. Yep. So so I'm looking at the different large ensembles here. So CSM1, 2, and E3SM V2. There are 20 ensemble members. And so again, right now we're looking, if I skip something. Apologies here. Sorry, I didn't realize I skipped this. So essentially we're looking 20 ensemble members each for the three ensemble sets. They differ in their oceans, they differ in vertical resolution, and CSM1 differs somewhat between V2, E3SM, and CSM2. So, yeah, just getting back to this. So in the West Pacific, If I plot the divergence profiles and the range and the shaded regions here for the 3 ensemble members, there's little variation, so they agree. And if we compare that to the bottom right there, which is analyses, then in essence, they agree quite well. There are some aspects of the divergent maximum which are different, but in essence, they agree. Now, if I look in this key region here where the Niño 3.4 anomalies are, there's significant disagreement with the observations. So the reanalysis here disagreed amongst themselves, and the 3 different large ensembles disagree also. And that's a reflection, I think, of colder SSTs, poor representation of the deep convection there. And if we look at where the greatest variation is amongst the ensembles, it is in the upper troposphere. And that's obviously the key region where divergence matters for the forcing of Rossby wave there. And now if we look at the actual El Niño anomalies of divergence, we can see that there is even more variation, disagreement amongst these ensemble members in this upper tropospheric region. And again, just to reiterate, this is the key region of where the divergent flow forces the Rossby wave source and the Rossby waves into the out of the tropics and into the North Pacific. And, the greatest variation tends to be in CSM1. If you kind of do my qualitative look at the variations in the Niño 3.4 time series, we can see that it's more regular, it seems so, in CSM2 and V2, but the variations in amplitude and frequency tends to be greater in CSM1, and that's probably explaining that, you can have periods of 25 years where there's different frequency of El Niño or different magnitudes, and that is going to result in different strengths of the divergent response here. And that tends to be different to CSM2 and E3SM, which is a little bit more consistent amongst the ensemble members. Finally, my one plot, what I really want to get into is thinking about the diabatic processes. So here we see the total heating from each of these ensemble members plus the range. One caveat we've got to be careful of here is, the same variable amongst ensembles does not necessarily mean the same quantity. So this is to be ignored because CSM2 and 3 contain the new tendencies from the new club turbulence scheme, and CSM1 does not. But I think just take away that the variation in the heating is much greater, in essence, in terms of magnitude, than the variation in upper tropospheric divergence. And so that's a key. It really tells you that we need to look at how the vertical heating is parameterized, is represented. And another key aspect here is the level of the maximum in this vertical heating profile. And then what I didn't mention before, actually, when you have a higher vertical heating maximum, that compresses the region of divergent outflow. And again, that's super important for how that determines the Rossby wave source. So, in summary, these tropical vertical processes are key to understanding this Rossby wave-related teleconnections in terms of the motivation, and also the reanalysis differs significantly in this region. So I've looked at these vertical profiles in divergence and vertical heating, and I think it's fair to say the ENSO-related divergent profiles is reduced in the newer large ensembles. But again, there's this bias in the tropical Pacific in terms of the vertical profile of divergence, which is probably key to the communication to the rest of the North Pacific. So my next step is to link up what I've shown here with variations in the Rossby wave source, and we need to do further experiments, I think, to break down these diabatic processes that are really lie at the center of determining the vertical profile of divergence. That's it, thanks.
Any questions for Rich? Adam can walk the mic around if you do. Jerry?
So I was a lot of interesting things there, but the level of the maximum diabatic heating between the models was kind of interesting in terms of how different it was, and you said that was important for upper level divergence. And you also mentioned it's hard to pin these things down because there's not a lot of observations. So the question is there a way to get an idea of where that maximum heating should be?
Yeah, absolutely. I mean, there's no doubt. I think people would trust for that region, era 5, I think, and what that's saying. Yeah, I mean, I'm just thinking in terms of what is available for free tropospheric winds in terms of being in the reanalysis. I don't know. I mean, I'm not familiar with vertical profile of winds in the tropics. Right. So I mean, Isla may know better than I do, but like.
There's all the, like, satellite irradiances maybe constraining some things.
To determine winds, though.
I guess it's hard in the tropics.
Yeah. If you look in the if you look in the East Pacific and ITCZ, it's even worse. It's incredible.
Thanks, Rich. You mentioned, I think, that CSM1 was too weak in something, but then I'm wondering, you don't really know, or do you, where the observations lie within its own distribution. So how can you make that determination?
It's too weak, weaker. I think weaker than the other ensemble members. I think, yeah. In terms of upper tropospheric, at least in the West Pacific divergence, which is better constrained. Yeah. I think, but yeah, you make a good point. I mean, I'm leaning more towards era 5 just because I think that's the generally accepted. But MERA
but year
is
A5 could be at its, if you had shading on OBS, which you don't, because we don't have long records, we don't know the actual sample that we had was either where it was.
You can imply from vertical temperature profiles potentially what the underlying circulation is, but and what the anomalous precipitation is doing, but I think it's hard. Yeah, you're right.
I think the point is not so much that the reanalysis might be an error, but that just the random sampling has led to that, and that so if you look at the spread across members, I guess, of the large ensemble, right, then you could see where does the reanalysis variability sit within. I think you're referring to like the PNA part as opposed to the at the very beginning, the kind of motivation.
Right. I mean, that's kind of the link I haven't done yet, is like communicating those variations in the vertical profile of divergence to the performance of the PNA pattern.
All right, well, we're at the coffee break, but I want to say one thing first, and that's that we had a cancellation of the second speaker in the next session, so we've decided to move everyone up. It's reflected on the online agenda. If that's causing any problems with any of the speakers, just let me know, or we can just have a pause. But we thought we'd shift it up to try and leave a bit more room for people going over time and things. But I want to thank all the speakers again in this session for great talks, and we'll hope to see you come back after the break.
The second session of a climate variability and change working group meeting. And the first speaker will be Yueying Zhao.
And good morning, everyone. My name is Yueying Zhao. I'm a postdoc from UT and Austin. I'm based in Boulder.
Could you be a little bit closer to the mic,
I would
please?
like to. Okay, let me restart. Good morning, everyone. My name is Yueying Zhao. I'm a postdoc from UT at Austin and based in Boulder. And I would like to acknowledge my advisors, Clara and Gita, and all other collaborators. I would like to thank them all for the great support throughout the process. And today I will be presenting the work about the atmospheric response to the time-evolving historic anthropogenic aerosol emissions. I will discuss the impact of the patterns of these emissions on the atmosphere, as well as the relative contributions of its decomposition into atmospheric and oceanic pathways. And so the previous work has been primarily focused on the industrial aerosol emissions, and the time slice simulation has been used to study the equilibrium response to the patterns of this emission at the specific study year. And it's worth noting that both the industrial aerosol emissions as well as the biomass burning emissions has distinct spatial characteristics throughout the 20th century. So this work aims to investigate the dominant forcing patterns of the time-evolving historic anthropogenic aerosol emissions. So we consider both the temporal and spatial evolutions of the industrial aerosol, mainly in the northern hemisphere, and the biomass burning in the tropics. And the second goal is to investigate the atmospheric response to the patterns of these emissions. So we can decompose the impact of these emissions into two components. So the response driven by the radiative forcing and the response driven by the SST forcing, which can also seen as the feedbacks to the SST changes driven by these emissions. Well, the studies has been focused on the total impact of the industrial aerosol emissions, and which is dominated by the SST forcings. So this work highlights how the radiative forcing could contribute to the total response through modifying the SST force response. And we use 3 sets of CAM5 AMIP ensembles, and the CMIP5 industrial aerosol and biomass burning emissions from the CESM1 fully coupled large ensembles are used to prescribe the AMIP ensembles, which is called the RAD AMIP. And the SST forcing is estimated as the SST changes driven by the same emissions, and which is estimated as the anomaly of the ensemble mean of the all forcing minus the ensemble mean of the all but AER and all but biomass burning. And the ensembles prescribed by these SST changes is called the SST AMIP. And the last ensemble that we use is driven by the both forcing, so both the emissions and SST changes. So the response in the full AMIP is considered as the full response to these emissions. And I use the EOF method to investigate the dominant forcing patterns of these emissions based on the aerosol optical depths, and I will focus on the summertime for this talk, where the ALD PC1 time series describes a monotonic increase in ALD and explains about 64% of the total variance, and the corresponding ALD regressions on the right describe a robust ALD increase in the low latitude regions. This is associated with the industrial aerosol and the biomass burning in the tropics. So this mode is called as the low latitude ALD mode, where the ALD PC2 depicts a peak around the late 1970s and followed by a reduction, and explains about 31% of the total variance, and the corresponding ALD regression on the right is characterized by a robust ALD increase in the northern hemisphere mid-latitude and a reduction in the low latitude, which is associated with the northern hemisphere industrial aerosol emissions. So the second mode is called as the northern hemisphere mid-latitude ALD mode. So the two modes in together explains about 95% of the total variance of these emissions. So the pattern of the AOD regression is considered to represent the dominant pattern of the radiative forcing. Well, the SST response regression onto each AOD patterns is given on the right. We're in the low latitude AOD mode, so the increase in the AOD cools the ocean, particularly in the North Pacific. And then in the Northern Hemisphere mid-latitude AOD mode, the SST response is characterized by an interbasin contrast with a cooling in North Atlantic and a warming in other ocean basins. So the pattern of the SST response regression is considered to represent the dominant pattern of the SST forcing. So after defining the dominant forcing patterns, so the next steps is looking at the atmospheric response to these patterns. And I will focus on the precipitation response to the low latitude AOD mode, where the total precipitation response, given on the lower left, includes a southward shift of the ITCZ as well as a robust continental precipitation reduction over the low latitude emission source regions, where the SST force response, given on the lower right, where the SST forcing dominates the overall pattern of the total precipitation response, giving their spatial pattern correlation of 0.7, while the radiative forcing also contributes, while most of the continental precipitation change over the emission source region is attributed to the radiative forcing. An example is seen in the East Asia, where study has suggested a weakening of the East summer monsoon circulation, as well as a reduction of the monsoon precipitation induced by the industrial aerosol emission in these regions. So our result may suggest this monsoon precipitation response is dominated by the radiative forcing. Well, the radiative forcing generally weakens the SST force response, as indicated by their spatial pattern correlation about minus 0.4. An example is seen in this tropical region, including the African sector as well as the Indian Ocean, where the SST force response is mitigated by the radiative forcing. Where specifically in the Indian Ocean, a meridional structure precipitation pattern is observed, and the radiative force and SST force response also exhibit a similar pattern, although with reversed signs. So this is a representative of how the radiative forcing could modify the SST force response. And so let's zoom in on this region, where the Indian Ocean is highlighted within the box regions, where the total response is given on the left. And so its pattern is dominated by the SST forcing given on the right, middle right, and as indicated by their spatial pattern correlation of about 0.9. Well, the radiative forcing generally weakens the SST force response, particularly over the Arabian Sea, the southern Indian, as well as Bay of the Bengal, as indicated by their spatial pattern correlation about minus 0.7. Well, the cross-section of the zonal mean condensational heating average over the box regions given on the bottom gives a clear view of the vertical structure of this meridional precipitation pattern. Well, in the full response, so the precipitation increased to the south of the equator, accompanied by an enhanced upward motion, and the precipitation decreased to the north, accompanied by an enhanced downward motion, which is dominated by the SST forcing, as indicated by their spatial pattern correlation. While the precipitation increase to the south of the equator is associated with the southward shift of the ITCZ related to the enhanced meridional hemispheric SST gradient, while the precipitation reduction to the north is associated with the cooler SST near the continent, associated with the local industrial aerosol emissions. While the radiant forcing generally weakens the SST force response, as indicated by their spatial pattern correlation about minus 0.36. Well, it's worth noting that where the Indian is an emission source of the industrial aerosol, which has a net negative radiative forcing effect. Well, the precipitation increase is driven by the radiative forcing over the near and Indian sectors, and this may seem counterintuitive. So I propose this precipitation increase to the northern of the Indian Ocean is driven by the atmospheric dynamic changes induced by the remote emissions as well as the heating from the Africa biomass burning. So anomalous westerly from the East Africa transport the warm air induced by the Africa biomass burning towards the Indian Ocean, so destabilizing the atmosphere. And these response, radiative force response, is also seen in the total changes. So due to the sake of time, I don't include these results here. So I will happy to chat more if you're interested afterwards. So to wrap up, so the transient historic anthropogenic emissions has two dominant forcing patterns. So the first low latitude AOD mode describes the AOD changes associated with the industrial aerosols and tropical biomass burning emissions, while the second forcing mode, the northern hemisphere mid-latitude AOD mode, describes AOD changes associated with the northern hemisphere industrial aerosol emissions, while the atmospheric response to the pattern of these emissions is dominated by the SST forcings, while the radiative forcing contributes through modifying the SST force response on a regional scale. And the meridional structure precipitation response in India is an example of how the radiative force regional response induced by the local emission can be modified by the remote emissions, so which influence the atmospheric dynamic through the atmospheric and oceanic pathway. And that's all about my talk, and I'm happy to take any questions, feedback, and suggestions, and thank you for your attention. Oh, okay.
Speaker will be Xianglin Ren. If you have any question, you can ask her later.
Good morning, everyone. I'm Xianglin, come from UC Riverside, and today I'd like to present my recent work according to focus on the anthropogenic greenhouse gas and aerosol-driven marine heat waves. And this work is working with my advisor, Liu, and also we collaborate with Robert Allen from UC Riverside, and also the Seong Sang from the UCSB. And marine heat wave is kind of the warm extreme event, and we set the 19th percentile of daily SST climatology as a threshold. And when the sea surface temperature is higher than the threshold, persists for at least 5 days, and with no less than 3 days interval, so we say this is a marine heat wave event. And this kind of events have a dramatic impact on the ecosystems, including reduction of the biodiversity and also maybe loss of the fisheries. So here is a figure. The left figure, it shows us the a marine heat wave event happened off the west coast of Australia in 2013. So we can see compare before and after the event happens, we can see the sharply reduction of the kelp population in this region. So the ecosystem here has taken a huge hit, and it may take a very long time to recover. And this kind of extreme events have widely happened across the world since the global warming intensifies. And in the red figure here, it shows us the marine heat wave duration time series, and we can find that since 1980 to the present, the marine heat wave duration shows a very robust increase trend. And we find that this increased trend is temporally consistent with the change in the global mean surface temperature anomalies. And this warming trend can be explained by the effect of the human activities have had on our climate, like the greenhouse gas and aerosol emissions. And CESM1 climate models shows us that the greenhouse gas can trap more heat to cause the sea surface temperature to rise. And on the other hand, the anthropogenic aerosol emissions, so it can cooling the surface by scattering or absorbing more solar radiation, and also they can affect the clouds. And so, therefore, so we want to understand how do the anthropogenic aerosol and greenhouse gas affect the Murray heat waves. So we use the probability density function to help us compare the Murray heat wave under different conditions. So in this figure, so the pink area here represents the likelihood of the Murray heat wave, and the likelihood of Murray heat wave can be extended to the union of the pink and red area by first shift the probability distribution, and another one is by widening the probability distribution. So anthropogenic greenhouse gas and aerosols, so they can shift the mean state SST to change the Murray heat waves. But beside of this mean state shift, so we want to know, can they change the shape of the SST probability, like widening or make the PDF taller to modulate the Murray heat wave events. So we choose the OSST version 2.1 as our observation, and also we use 10 semi-6 fully coupled climate models, and we use the historical simulation and the single forcing simulation experiment. So in our study, so the daily SST climatology is distinct among the three groups of the simulations, and we calculate the daily SST climatology for each simulations. Therefore, our methodology can eliminate the effect of the mean state SST difference on Murray heat waves. So first, we compared the Murray heat wave performance between the observation and the historical simulation. So in this figure, so first column is our observation result, and second one is the historical simulations. So we can find that the long lifetime and strong intensity Murray heat wave events is always happens near the eastern tropical Pacific, and short but strong Murray heat wave events they like to happen near the Gulf Stream and the crucial extensions. And if we compare the observation and the historical result, we can find that so the mean distribution patterns of the Murray heat waves are well captured by our climate models over the past 4 decades. So next step, we look at the global Murray heat wave driven by the greenhouse gas alone. So this the first column here shows us the Murray heat wave in the greenhouse gas single forcing experiment, and second one shows the difference compared with the historical simulation. And if we only consider the anthropogenic greenhouse gas effect, so more persistent and intense heat waves are expected to occur more frequently across the world. And we did the similar thing, but for the aerosol alone experiment, and compare with the historical one. So we found that anthropogenic greenhouse gas, they can anthropogenic aerosols alone, they will weaker and shorter the Murray heat waves, and also the Murray heat wave in global ocean it will become less frequently compared with the historical simulation. And then here is our probability density function analysis result. So also if we compare with the historical one, the green line in the middle, so the greenhouse gas alone, so it shows us the smaller kurtosis, and which can imply that the greenhouse gas alone can foster the occurrence of the Murray heat wave events. And on the other hand, so if you look at the aerosol alone result, the PDF here, so it shows us a larger kurtosis compared with the historical one. And so it means that the aerosol alone can inhibit the occurrence of the climate streams like the Murray heat waves. And so this kind of the kurtosis difference can not only affect the warm extremes, but also for the cold spells. And also we did the quantitative analysis by calculating the 99th percentile of the SST anomalies, and if we compare both in the kurtosis change and the mean state shift, so we can find that the greenhouse gas alone scenarios, it will cause the positive effect to Murray heat wave to the warm extremes. But for the aerosol alone one, so it will have the negative effect on that. And if you compare the numbers here, so the effect of the kurtosis on Murray heat wave is comparable to that by mean state change. And here is our short conclusion. So in this project, we compare the heatwave behavior in the single forcing experiment and the historical simulation. And we find that so the greenhouse gas alone scenarios, it can foster, it can enhance the heatwave all over the global ocean. But for the aerosol alone one, so it will inhibit the heatwave growth. And also we find that the effect of the curtices on the climate extremes is comparable in the magnitude to that of the mean state change. And that's all I want to take for our project. And if you want to get more details, so you can find this paper. And thanks for your attention today.
I have some questions.
For the kurtosis changes, I'm just wondering how much of that is being dominated by the tropical Pacific?
Yeah, so this is a greenhouse gas result. So we can see that in the tropical Pacific, so there is the eastern tropical Pacific, this area, so it's very related with the Ensemble variability. So the Ensemble, the El Niño and the La Nina variability here. So this part in the greenhouse gas alone one, so we can see that it may cause a little bit negative effect on the heatwave duration, but on the frequency one, so it will cause more frequently heatwave happens in this area. But if you look at the aerosol one, so we can see very strong effect, also very strong effect in the heatwave frequency, but we have the smaller effect on the heatwave duration. So these areas, we think that this area should be studied by itself, do some regional study, because it's related with some climate variability. Yeah, thank you.
Next speaker will be Claridizer. Yeah. She will talk about how the different way to generate large ensemble will affect the large ensembles.
Good morning, everyone. So the CSM2 large ensemble, we designed it with really to answer some questions that have not been able to be addressed with previous large ensembles, namely, does the method of initialization, if you do a large macro perturbation or a small perturbation, does that affect the evolution of ensemble spread? And then also, what is the role of an ocean initial condition memory in the evolution of ensemble spread? Sorry, how do I advance? It is this thing? The big button, thank you very much. Okay, and this is work primarily done by Hu Kim and myself, but excellent input from our other collaborators. Okay, so as I've just said, we are able, I'll show you how we can address these two questions. And again, these results, I think, just have bearing on the design of future large ensembles with climate models. Does it matter how they are initialized? And what do we learn as a result? Okay, so the way that we approach this for the CSM2 large ensemble, unlike the CSM1, we decided to be strategic in how we chose to perturb each ensemble member. So we, starting off with this AMOC time series from the pre-industrial control run, so the strength of AMOC at 45 degrees north in the pre-industrial control simulations. So what we did was we chose, just by looking at this time series, these red dots, 4 AMOC states that were, high and low and transition states of AMOC. And then we chose to run 20 members for each one of those initial states using this tiny microperturbation, 10 to the minus 14, for each ensemble member. So we can compute the ensemble spread or standard deviation as a function of time across the 20 members of each of these AMOC ensembles. And then we can average those 4 estimates of spread due to micro perturbations. And I should say there really aren't any significant differences between the spread across the 4, so we can do this averaging. So that's how we're going to address what the evolving spread is when you do these micro perturbations. Then we can take these additional 20 members from the 100-member CSM2 large ensemble, and these were chosen randomly. So every decade we had restarts, and so we just, whatever condition that was, there's 1 member for each of those yellow circles, so we have 20 members total with different ocean initial states. And then as part of the CMIP contribution from CESM2, earlier on, before we designed the CSM2 large ensemble, these were run, and there were 11 members that were submitted to the CMIP archive. So we decided to include those as well, so those are also macro perturbations. And then we can combine the 11 and the 20, so we have 31 samples of macro perturbation members. And again, we can compute the spread, the evolving spread, taking into account all 31. And importantly, we have to subtract the control run drift from each member before we compute these quantities. So there is drift in the pre-industrial control. It's important to remove that before computing these quantities. Okay, so I'm just going to show you a few results. So this is the first decade of the simulations, the 1850s, and this is showing you if there's what the difference is in spread when you compare the macro initialized members versus the micro. And the contours here are the important part, and that is our bootstrapped estimate of when these differences are significant. We do random draws of 31 decades from the detrended control run, form their standard deviation, then do the same thing, picking out 80 random decades, and then do this 2,000 times to get the distribution. And then where you see contours, that means that these differences in the map were unlikely to have occurred by random chance. So not surprisingly, in this first decade for SST, we see that you do get enhanced spread when you do this macro perturbation versus micro, especially in the North Atlantic, parts of the Southern Ocean, Indian Ocean, and North Pacific. Then the next decade, there's not a lot going on, a little bit in the Arctic, so really it doesn't matter once you go beyond the first decade how you do this initialization process. And then I'll just show you a couple more decades, and then that was the surprise. What is happening here in the 4th decade, and that goes away by the 5th decade. So there is some significant enhancement of ensemble spread in this 4th decade when you do macro versus micro perturbation. I'll show you now the same results now for sea level pressure, just an atmospheric quantity. It really doesn't matter. First decade, atmospheric noise, or whether you perturb the full coupled state, you're not going to get any difference in the ensemble spread. So we really don't have to worry, except this 4th decade. And this was such a surprise. We really don't know what's going on, but we have a hypothesis that maybe it was these strong volcanoes that happened sequentially in the Indonesian region and North Island of New Zealand. And just to show you that in a little more detail, these are time series of ensemble spread of decadal means. The top one is for the Western Tropical Pacific region, and the bottom is for the tropical Indian Ocean sea level pressure. And where I've circled in the green there, the macro perturbation spread exceeds significantly, the dots show it significantly exceeds the spread due to microperturbation in this 1880s time period. And furthermore, it exceeds the likely range of the PI control run. So it suggests that there is a role for external forcing in enhancing ensemble spread. Why that's happening just for the macro perturbation and not the micro perturbation members is a mystery. But I think it's important for the community to see this. Okay, and then last moment here, addressing this second question. So again, the way we designed the large ensemble, we were now able to also address sort of this complementary question. So how long does ocean initial condition memory last? And here we're looking at the atmosphere and the upper ocean. And the way that we can address this is, if you remember, we have these 4 AMOC initial states, which had these 20 microperturbation members each. So you form the ensemble mean of each of those AMOC ensembles. That's reducing the atmospheric noise, revealing the ocean memory, and then you compute the spread across those 4 ensemble means to give you an indication of spread due to ocean initial condition memory. And you can compare that with the total spread across all 80 members, and you can test whether the ratio of the spread due to ocean initial condition memory versus total is significant, doing kind of similar bootstrapping based on random draws from the pre-industrial control simulation. So we don't understand these results, but I'm just going to show you what is, I think, kind of very interesting. So this is a Hofmüller diagram of that ratio of how much of the spread is due to the ocean initial condition memory versus the total. So this is zonally averaged SST, and where you see the white contours, that is significant relative to the bootstrapping of the PI control distribution. So this is a Hofmüller going latitude on the y-axis 1850 to 1950 on the x-axis. This is for the global domain. Not surprisingly, at the beginning, we see significant ocean initial condition memory, especially in the northern high latitudes. Not a surprise. But the surprise was something, again, happening 40, 50 years into the simulation, where we get this resurgence of significant ocean initial condition memory in the southern hemisphere. So that's the global domain. We can now look, just do zonal averages over the Pacific domain, and now you can see you have very little initial condition memory at the beginning, but this resurgence of memory 40, 50 years into the simulation is really coming from the Pacific sector in the Southern Ocean, and then subsequently enhancing in the subtropical Southeast Pacific. And here's the Atlantic domain, not surprisingly, because the initial states were chosen based on AMOC at 45 degrees north. The Atlantic really shows this very long-lived ocean initial condition memory. So they're really 2 very different, distinct time periods and spatial expressions of ocean initial condition memory. And I think this demands further analysis to understand the mechanisms for that resurgence. We've done a bunch of other work. I don't have time to speak to it here. Happy to speak individually. So I'm going to leave it at that. Thank you very much.
Thank you. I think it's very interesting, and I guess we have a lot of questions, but we have to move on in terms to keep us on schedule. So if you have questions, just ask Clara afterwards. Next speaker will be Ivan Vitebsky.
Hi, everyone. I'm Ivan Mitevsky. I'm a postdoc at Princeton University, where I work with Gabriel Vecchi, and I'm here to present some ongoing work on the North Atlantic oscillation at very high CO2 forcing scenarios. So just to get up to speed, the North Atlantic oscillation is one of the primary mode of atmospheric variability in the North Atlantic region, both in winter and in summer, and it's associated with the variability in the eddy-driven jet, and it's pretty much this high here in the Azores and the Icelandic low. So in the historical period, there has been a positive trend of the NAO from 1950s to 1990s, and then reversed in the early 2010s. And there hasn't been any clear signal due to historical greenhouse caused warming. And in the future scenarios, some merge system models project a more positive NAO under high emissions scenarios, but there is a signal-to-noise paradox in the North Atlantic where the signal-to-noise is quite low in model response. So here we ask two questions. How does the summer and the winter NAO mean state and variability change at very high CO2? If we cannot get a good signal-to-noise ratio at low CO2 values, what if we go very high scenarios? For example, 8 times CO2. And the second is, are there any structural changes in the NAO, for example, a spatial shift? To do that, we use very high CO2 forcing scenarios, doubling of 2, 4, and 8 times CO2. And we use monthly data for DJF for winter and JJA for summer. And we use 12 long-run MIP models from Rubinstein et al., which have experiments which are run for at least 1,000 years. We used 3 of our own model, which is the CSM1, large ensemble version, the GIST model, and the GFDL model. And we use additional 24 SMIP6 models, which are mostly for 4 times CO2. So we define the NAO as the 2-box index, which is simply the sea level pressure between the box over the Azores and another box over the Icelandic low in DJF, and then in JJ the box is shifted a little bit over the British Isles and the in Icelandic low. And results are not sensitive to the exact choice of the boxes. However, traditionally NAO has been defined as the leading EOF within the domain. So the way we assure that our 2-box index actually does a proper job in capturing the variability is we regress the SLP with the 2-box index on top here in DJF, for example, for PI values, and on the bottom is the EOF1, and we can see that they're quite similar. If you look at the changes at 2, 4, and 8 times CO2, they're also quite similar. So that's how we sort of assure ourselves that we could continue to use this 2-box index to study the NAO. Now, here we plot the 2-box NAO index as the mean NAO change in hectopascals for DJF for 2 times CO2, where every bar is a different model. And we see that most models project a positive NAO at 2 times CO2. Then at 4 times CO2, similarly, we have most models to project a positive NAO. And the black line is just the model mean. And then at 8 times CO2 as well, we have a more positive NAO. Similarly for JJA, we have more positive NAO at 2 times CO2, similarly at 4 times CO2, except we have some models that say that otherwise, which project a more negative NAO, and then similarly at 8 times CO2, more positive NAO. Next, we'll look at the variability, which we define just the 1 standard deviation of NAO. And we find that in DJF at 2 times CO2, we have a less variable NAO. The variability goes down. Similarly, at 4 times CO2, across most models, we see that variability drops, and same for 8 times CO2. For JJA, we also have a decreased variability of NAO at 2 times CO2, similarly at 4 times CO2, although it's a weaker signal than in DJF, and same for 8 times CO2. And because we are defining this as a 2-box index, we can go in the individual box and we can check this more positive NAO at 2, 4, and 8 times CO2, which is shown here in the gray bars. What part of it comes from the strengthening of the NAO high versus the weakening or the deepening of the low? And the blue here is the low, and the red is the Azores high, and we can see that pretty much in all DJF at all CO2 scenarios, we have roughly similarly strengthening of the Azores high and the weakening of the Icelandic low that gives us more positive NAO. In JJA, the attribution shows that most of the strengthening of the NAO actually comes from the deepening of the Icelandic low. We can do the same decomposition for the variability, which is the 1 standard deviation. again, we show that the variability goes down of NAO at 2, 4, and 8 times CO2, which is shown here in the gray bar. And decomposing it to the Icelandic low and the Azores high, we see that it's roughly half and half. So variability goes down, roughly half because variability over the Azores decreases and the variability over the Icelandic low decreases in winter. And in summer, it's actually variability decreases mostly at 8 times CO2, mostly due to the high, and the British Isle high, and then at low CO2 is a little bit different. So next is because we use this 2-box index, we have to naturally ask, is there any spatial shift of the NAO? And if so, should we continue using these 2-box metrics, or should we be careful about it when we go to high CO2 values? So here we show, this is the EOF1, and the dots, blue is 1 times CO2, which is the average, is the centroid of all the individual maximum that occurs at every model. And we see a slight shift in DJF looking at the EOF1, slight like north-east shift. And similarly with the SLP regression of the NAO, we see that there is this slight northeast shift of the NAO, the winter NAO. And if we look at JJA, we actually see a stronger shift of the EOF1, the northeast shift, from PI all the way up to 8 times CO2, and we get a similar response with the SLP regression. Just to summarize, we found that the NAO is more positive in both winter and summer at high CO2 forcings. Meanwhile, we found that the NAO variability decreases in both winter and summer. And although the NAO is more positive, the variance has decreased. So the extremes may not scale linearly with the mean. And the spatial structure also changes. So with the summer low, especially shifting northeast, so we have to be careful when we use the 2-box method, because we might underestimate some of the changes. Thank you.
Great talk. I'm just curious, so you have less model for like 8 times CO2, right? And in DJF, I see there are like some variability across the models. Some models show positive, trends. Some models show negative trend. But in JJA, all the models show positive trend. I'm just curious. Do you know like why some models have a negative trend in DJF?
Yeah, I think there's less clear signal in JJA than DJF. I think it's the different season. Part of it has to do with AMO collapse, especially at the 4 times CO2 scenarios. That's where the weaker signal in JJA, because when we have an AMO collapse that induces cooling in the North Atlantic, and that causes the NAO low to strengthen, to actually become higher, so pressure goes up. So that's why. That's one part of the reason. I didn't show it explicitly, but yeah, that's part of the reason why in JJ we have a higher spread than in DJF.
So like some of the models that show like opposite trend in the DJF, do you think like these are like AMO collapse are different in those models?
Yeah, AMO collapse is different, and there is some SST cooling in the North Atlantic. Yeah. Thanks.
Okay, next talk will be given by Jessica Wan.
Hi, my name is Jess Wan, and I'm a PhD candidate at Scripps Institution of Oceanography at UC San Diego. Today I'm going to be presenting on some work that was recently submitted in collaboration with John Fasulo, Nan Rosenblum, Jack Chen, and my advisor, Kate Rickey, on whether targeted marine cloud brightening could potentially be used to dampen El Niño. So as most of you in this room are probably already aware, we are currently experiencing the compounding effects of both steady anthropogenic warming and the 2023-24 El Niño, which has manifested itself in extreme storms and record-breaking heat already this year. While on regional scales, the societal impacts of El Niño can vary. On net, it has been found to be economically damaging on the order of trillions of dollars. And so with these impacts expected to worsen under future warming, it would be really great if we could do something about these damages. And so that's where solar geoengineering comes in, which was originally proposed as a way to moderate warming by increasing the amount of reflected sunlight back out to space. There are many different types of approaches that have been proposed, but the main one I'm going to be talking about today is marine cloud brightening, or MCB, which is operating down here by introducing some sort of aerosol into the lower atmosphere to increase the reflectivity of low marine clouds. And solar geoengineering and marine cloud brightening were originally proposed as a way to reduce sort of the long-term global warming. It could potentially also be used as a way to target short-term events instead. And so that leads us to the question I'm answering today. Could regional marine cloud brightening be used to instead target seasonal phenomena such as ENSO? And this research question is really motivated by some work done by John and colleagues on the 2019-2020 Australian wildfires, where they basically simulated sort of a natural cloud brightening event that they linked to enhanced La Niña-like conditions. And I'll just summarize that work briefly here. So basically, biomass burning aerosols were emitted from Australia and transported all the way across the South Pacific. This in turn brightened the subtropical stratocumulus cloud deck off the coast of South America, which led to a series of dynamical effects, including the drying of the boundary layer and cooling across the equatorial Pacific, which then shifted the ITZZ northward over here. And the idea here is that potentially this wildfire case could serve as an opportunistic experiment for regional marine cloud brightening in that region in this subtropical cloud deck. And so to do this, we are using the Seasonal to Multi-Year Large Ensemble, or SMILE, which I'm sure you've heard about at some point over the workshop. And we start by developing MCB seeding masks in this subtropical region in that blue box. And we increase the cloud droplet number concentration here to 500 particles per centimeter cubed as our representation of marine cloud brightening in CESM2. And we do this for a variety of different initiation months and durations to really get at this question of whether MCB could be deployed after the spring predictability barrier and still have an influence on that impending El Niño or La Niña event. We then select 3 historical ENSO events to test the influence of MCB. So these are the 2020-2021 La Niña to sort of validate those wildfires from John's work. We also do the 2015-16 El Niño to test how effective MCB could be at weakening El Niño instead of inducing a La Niña. And then we also test the 97-98 El Niño, but I'm really only going to focus on those first 2 for this talk. And then lastly, we're running a 10-member ensemble for each of these MCB strategies and ENSO events to really characterize MCB's influence on ENSO. Okay. So the first result here is that we find MCB is able to enhance La Niña conditions, essentially reproducing that observed cloud brightening response from the Australian wildfire event. And so what I'm showing here is those sort of same plots from before with the shortwave cloud forcing on the left, precipitation in the middle, and the temperature response on the right from the wildfire work from John. Now what I'm going to show you on the bottom is if instead we had done marine cloud brightening during the peak shortwave cloud forcing from those wildfires, but we're not doing the wildfires, just marine cloud brightening in that black box. And what you see is we're able to reproduce a lot of those same responses from the wildfires, which suggests that the wildfires are actually a good natural analog for marine cloud brightening in this region. But you can imagine that a real-world hypothetical deployment of marine cloud brightening wouldn't have to occur during the Australian wildfire season. It instead would probably be limited by some sort of physical constraint, such as the spring predictability barrier. And so that leads us to our follow-up question. Could we deploy MCB after we have better forecasting capabilities to deliberately weaken El Niño? And so now I'm just showing you a standard Niño 3.4 SST anomaly time series simulated by SMILE. If we just zoom in on the 2015-16 event, and I've shown here the spring predictability barrier and the dotted line, and then if we assume the ENSO peak is sometime during boreal winter, you could imagine a scenario in which marine cloud brightening is deployed as soon as the spring predictability barrier ends, all the way through the peak event as sort of a full effort strategy to try and mitigate some of the impacts of El Niño. You could also imagine a scenario in which marine cloud brightening is just deployed during the peak of the El Niño event, a sort of an 11th hour or last-ditch attempt at reducing just those worst impacts from El Niño. And then you can imagine some variety of strategies in between, which is what we ultimately ended up simulating for this project. Okay. And so now I'm showing you that same Niño 3.4 time series, but instead of bars, I'm showing lines for each of those MCB strategies. And what I want you to focus on here is the full effort case in the solid red line is essentially able to restore neutral ENSO SSTs during a peak event. Whereas that 11th hour strategy is kind of hiding in this control error bar, which suggests that it's not really doing much to weaken the El Nino event. If you want to look at this spatially, you can see how SMILE reproduces the 2015-2016 El Nino, and then what this full effort MCB is doing to the temperature. And we're getting a really strong cooling within that seeding region, but then it's also extending into that Niño 3.4 region. And so that suggests that we can dampen El Nino with some of these really strong MCB strategies, but the responses depend on the timing of the intervention. But ultimately, whether MCB is deemed as beneficial will depend on if it can reduce some of those harmful impacts that are typically associated with an El Nino event. And so, lo and behold, we are able to ameliorate some of these remote teleconnections. You've probably seen some sort of version of this map before by NOAA showing El Nino impact regions. We generate our own version of that using the SMILE hindcast, and we calculate the percent of the 2015-2016 El Nino impact that is either ameliorated or exacerbated by marine cloud brightening. And that's shown in these bars for all these different impacts. And what I really want you to focus on is the left bar for each of these plots, which is that full effort marine cloud brightening case. And you'll notice all of them are green, which means we're able to ameliorate all of those impacts under this strategy. Okay, so just some conclusions right now. We showed we were able to exploit this experiment of opportunity for model validation using the Australian wildfire event. We then established a link between that observational analog and a welfare-relevant climate risk, which is El Nino. And then we demonstrated physical feasibility within the constraints of ENSO predictive capabilities by deploying MCB after that spring predictability barrier and still having an influence on El Nino. Okay. Thank you for listening. I'll be happy to take questions.
Thanks for the great talk. I noticed that even though you could ameliorate El Nino, you exacerbated the following winter's La Nina, which has, terrible consequences as well, drought and otherwise. So how would you address that?
Yeah, that's a really great question. These are only 2-year simulations, and I think future work definitely would be to extend some of those simulations to see what happens to not only the next year's La Nina, but if that influences maybe the next year's El Nino. I don't know if we see it here. Yeah, some of them kind of return back to within the error bars of the control, which is in that black line. But yeah, it would be really great to run these a bit longer to understand what happens beyond just this 2-year simulated. We don't know what happens after. Yeah, for sure.
Hi, Jessica. Very nice talk. I was wondering if you look like on a similar notion to Clara's. You do seem to ameliorate ENSO, but you just from eyeballing your plots, you do seem to be having some teleconnections with the North Atlantic oscillation, which was what Ivan was talking about before, and you do seem to end up with having just eyeballing more positive NAO and more Eurasian warming. I was wondering if you look at it.
Yeah, that's also a great question. We haven't looked at those effects on the North Atlantic, but that would be something to look at in the future.
Okay,
definitely.
cool, thanks.
Yeah.
Thank you. I think just move on. Next speaker will Jack Chen.
I'd like to first acknowledge my collaborators. And the work just recently got published on GRL. And this is about rethinking MCB strategies, as you'll see later. Basically, this is pretty controversial and pretty provocative. So I probably can skip this because Jazz just gave a slide on this. So there have been several solar climate intervention proposals the last few decades, and they aim at reflecting more solar radiation back to the universe to give you cooling. So for the purpose of this talk, I will focus on two. The first one is SAI. So you inject sulfate aerosols into the stratosphere, mimicking volcano eruption. And the second is MCB, marine cloud brightening. You inject CESL particles into the marine clouds in the boundary layer. And to achieve cooling for MCB, basically through indirect effects. The first effect is the tuning effect. By injecting CESL particles, enhance the cloud jump number concentration, so you can reflect more solar radiation. And the second effect is the Albright effect. By reducing the particle size, you reduce precipitation. The cloud will be more persistent. And just a few words about traditionally where we deploy MCB. Typically, we target the cloud deck over the eastern flank of the Pacific Ocean, the stratus-cumulus region. And I will demonstrate it's extremely problematic when you do that. And unfortunately, it's all over the literature for MCB. So here's the result we got from CSM. So I will first talk about this panel. This is the future surface temperature against the present day. So this is a global warming scenario. And you get a bit more warming in the polar regions. And this is the future temperature under MCB deployment, the more traditional approach against the present day. And you see the cooling is mostly concentrated in the lower latitudes. And in addition, you get blobs of warming, which actually the temperature will be even warmer under global warming scenario. Additionally, you barely get any cooling around the Antarctic. In comparison, if you look at the SAI simulations, Glenn's published in 2018, this is the map, like this map. This is the map for the future under the deployment of SAI against present day. If you have a white map, it tells you you manage to restore future temperature to the present day condition. So it's doing a fairly good job, I would say. And this is an even more recent publication by Yaga. This is a RICE SAI. Same thing for SAI. So this is pretty problematic. And to illustrate what's in the literature, I pick out several studies here with MCB. This is Jones et al. 2009. You get this La Nina state. This is a study I was involved in 2009 with Phil Rash using CCSM4. This is a more recent study by Haywood et al. 2023. The top two panels are the composite of the top 5 La Nina episodes from nature compared with the MCB deployments. Just to give you a perspective, this is mega La Nina. And this is by Hiroki, also using CSM. You got the same thing. And I have a graduate student at UC Santa Barbara helping me to analyze my simulation, and there will be a paper submitted fairly soon. We're basically stuck in La Nina forever when you deploy MCB. And that will create a lot of conflicts in the world, to say the least. So that motivates this work. So over the, right after I came back from the AGU last December, I thought, okay, what if I move away from the traditional school of thought? This is a seeding mass based on month. The red is the more traditional approach. If you look at JJA, for example, the traditional approach points to the stratus-cumulus region in the northern hemisphere. But I say, what if I move to the least susceptible grid points over the ocean? That points to the Southern Ocean in JJA. So instead of focusing on the summer hemisphere, The least susceptible approach focuses on the winter hemisphere and moving away from the subtropics. We move to the mid-latitudes. So you are going to create much weaker local cooling. And we'll see what happens. The black curve on the top, this is the time series of the global average surface temperature. This is from the CESM SSP 245. You see the global warming scenario. The red is the most susceptible approach, and I managed to get back to my temperature target by the end of my simulation. And the 4 blue lines show you the 4 least susceptible approach simulations. By seeding over 10%, 20%, 30%, or 40% of the ocean surface. But the key is like, okay, so if you see over 20% of the ocean surface in this new approach, you also manage to restore the global average surface temperature. But that's not the key. The key is actually the bottom surface temperature map. This is the global warming map. This is the top 5% MCB map. I already showed this earlier, so you get this La Nina state. And this is a new approach. So over, like in early January, when I showed this map to my postdoc worker, he was like, are you sure you're not showing me a SAI map? This is not SAI, this is a new MCB strategy. And this is precipitation, fairly similar story. And just to give you a perspective, this is the precipitation difference due to global warming. And you can see the response when you deploy MCB using the more traditional approach. And now with the new approach. So I'll summarize. So following the traditional approach to deploy MCB, you will be stuck in La Nina forever. And there's actually evidence that such MCB deployment will get us stuck in mega La Nina forever. And then now if you move away from those regions, instead of focus on the very small region giving you very strong cooling, you move away from those regions, you're able to induce very uniform cooling. So that's all I have for today.
Yeah, any question?
Thank you. That's really interesting. I guess from my perspective, the reason why those traditional regions were selected is you can kind of get the most bang for your buck. Like you can get the most cooling for less marine cloud brightening. Have you thought all about it, done anything to quantify with your kind of proposed idea just how much more infrastructure would be required, how much more marine cloud brightening you would actually have to do to get the same amount of cooling out of it?
Yeah, that's a question I constantly get, but I thought to answer that question is like, okay, the traditional approach is a no-go. So it's a dead end. So I will worry about the technical aspect later. But to put this work out there basically tells you we should move away from what we've been doing because it's a no-go. And I can also add a few words about why we got what we got. Because when you deploy cloud seeding in the subtropics, you modulate the subtropical high dramatically. And the temperature pattern you see here, like the La Nina state, is probably a reflection of like displacement of the subtropical high. And that's not our intention. Our intention is to induce uniform cooling. So if you hit the system with a huge hammer, you might get it really quickly, but the consequence is that you disrupt things you don't intend to do.
Isn't there already a lot of aerosol over the Southern Ocean because of the high wind speeds and things? Are you able to really make a difference? Is it not already very well seeded?
I think, say for over the Southern Ocean, I think the air is relatively pristine, pretty clean, I think. would be like, will we be able to achieve the cloud number concentration we target at? That's an open question. But this would at least, provide, a different way of thinking. It's like we probably need to move away from what we've been thinking.
Hey, thank you. Let's move on to the last talk, maybe given by Ilaria. The Quagilia? Sorry.
Okay, I'm Ilaria Quaglia, and I'm a postdoc at Cornell, and I'm working with Daniele Visioni on this project where we're trying to explain the anomalous increase in temperature that we observed in the summer of 2023 as a consequence of the changes in international shipping emissions. So what happened is that in 2020, the International Maritime Organization prescribed a new limit of sulfur content in ship's fuel, reduction from 3.5% to 0.5% globally, with the aim of getting a cleaner air and healthier planet. And by reducing the amount of sulfur and so of sulfate aerosols in the atmosphere, we would expect a cleaner air, but on the other side, a reduction of the scattered radiation and an increase of the Earth energy imbalance. And there are some estimations from Partner et al. In 2013, which expected an increase, actually not a decrease, of the effective radiative forcing due to shipping emission from minus 0.43 to minus 0.06 watt per square meters. And on the other side, a reduction of 96% of that due to lung cancer or other pulmonary disease. There are still some open questions about the impact of these regulations. As for example, if we can detect the compliance to the regulations by observing changes in shipping tracks, as they are the visible manifestation of the interaction between aerosol and clouds. And what they observed is that a decrease, the red line here is the time series of global mean sulfur change emission, sulfur emission, and a change of 80% in 2020 would result in a decrease of only 25% of shipping tracks, which is occurring, of course, where ship tracks, of course. And the other open questions regards the quantification of the global effect on radiative forcing, and most studies agree that is of the order of 0.1 watt per square meters. And if we can attribute any of the observed climatic changes in the last few years to the IMO regulations. And here I'm showing the time series of the global average temperatures change compared to 1950 period in Berkeley. And we see these anomalies in this anomaly peak in 2023. Here we're trying to answer these last two questions with this work that we have published on, we have submitted on ESD, and is now under review. And what we have done, we use the CESM 2 large ensemble simulation. We use 50 members of the ensemble, and as we heard before, it it covers the historical period up to 2014, and use the SSP3 7.0 scenario for post-2014. And as you can see here, this is showing the global sulfur shipping emission time series and the change compared to the reference period that goes from 2000 to 2007. And you see that this is not including the reduction in shipping emission in 2020. So we performed 10 additional simulations where we reduced the emission of 90%, which is in agreement with the data set from CEDS. And we, to answer the first question, where we want to quantify the radiative forcing due to shipping emission reduction, we first look at the absorbed solar radiation at the top of the atmosphere, which is defined as the difference between the incoming solar radiation and the scattered solar radiation. And we compare that with observation from satellite observation from CIRIS in black and reanalysis from ERA5 in gray. And what we can see is that there are discrepancies between the two data sets, but what we are interested in is that this increase after 2020 in the absorbed solar radiative forcing can be reproduced in CSM only if we reduce shipping emission, which is given by here by the green line. And the other thing that we and this reduction, the forcing due to shipping emission change is around 0.5 in the short wave. And as we can see from this map, which show the cumulative absorbed solar radiation over the period 2021-2023, the increase, which is statistically significant, is observed over the regions where the change in shipping emission is significant, is occurring. And when we look at the net radiation at the top of the atmosphere, we found, again, discrepancies between the two data sets, and that, again, the observations can be reproduced in CSM only when we include the reduction in shipping emission. And this contribution is of, over the 2020-2023, is of 0.2 watt per square meter, in agreement with the previous studies. And something that I'm not showing here is that the main contribution comes from the cloud forcing, both for observations and but what is the impact on the temperature? Again, we are comparing our simulations with observation from Berkeley in black and ERA5 in gray. So apart from the fact that there are huge differences between our simulation and the observation, what we want to point here is that this increase in temperature in 2023 can be explained by natural variability. And the other important thing is that with CSM, we predict an increase of temperature during this period, 2020-2023, of 0.2 Kelvin. And as we can see from this map, this increase in temperature is consistent with the increase in the net radiative forcing, except this region, and maybe the presentation that we heard before can be an explanation for that. Okay, but how can we explain the likelihood of occurrence of these temperatures? We first the trend, temperature anomalies, defined as the difference from the 1980-2000 period for each month of the year. For simplicity here, I'm just showing the month of August. And we are doing that for Berkeley in black, and for the CSM simulation, without the reduction and with the reduction in shipping emission, given by, in this case, the green line. And we calculated the probability density function for each month of the year based on the large ensemble simulation without changes in shipping emission. And we calculate the likelihood of occurrence of temperatures in 2023. As the right tail of the distribution. So the black line here represents the temperature in anomalies from Berkeley in August 2023, and the likelihood is equal to 0.65%. And we define these other two values as the temperature anomaly if we didn't include the change in shipping emission. The dark line for the higher estimate of shipping emission impact, the light red line for the lower estimate of shipping emission impact. When we look at the all-time series of the trended global temperatures, we observe for Berkeley that the increase is statistically significant, is above 1 standard deviation when the 3.5 years after the IMO regulations. While in CSM, here, now that we have the trend and this is analyzed the temperature anomalies, we also observe that the increase is significant, so for the lower and higher estimate of shipping emission change impact, 3 years after the IMO regulations. And this translates in this time series of the likelihood of occurring temperatures. So what does this mean? That for all the months of June after June 2023, these temperatures anomalies fall above 2 standard deviations. And if we remove the effect of shipping emission, they would fall between 1 or 2 standard deviations, except September 2023, which means that shipping emissions are an important contributor of explaining temperatures, these temperatures anomalies. So wrapping up, our study confirmed the previous findings of top of atmosphere radiative forcing. So we estimate a radiative forcing of 0.2 watt per square meter and an increase in temperature of 0.2 Kelvin over 2020-2023. And these anomalies can be partially attributed to the IMO regulations. And something that I didn't show is that the radiative forcing is mainly due to changes in cloud optical properties. Thanks.
Thank you. In the interest of time, we just move on. Thanks. Before I open for the discussion, I just make one announcement. And right now, we're organizing a AMS name symposium. That's a Jerry Mill symposium in January 2025. The day is on Tuesday. And that's Yaga Rister from NCAR, and Dave Bader from Lawrence Livermore National Lab, and Xiangping Xie from Scripps, and Antonita and Kanta Kanatadi from NOVA. So, and you're welcome to submit abstract to this symposium, and also you can help us to spread out the word to either you attend it in person or just tell people to join the symposium. Thank you. And now we are going to start the open discussion, and Ella will lead it.
We have about 10 minutes. Yeah, this is really an open discussion if anyone wants to bring anything up. It's kind of a free-for-all, but I guess one of the main things we would like to hear some views on is any new simulations you'd like to see the working group do in the next allocation. And I've written a few things up here to get us started in the discussion. I think since we're CSM3 will be available in the coming cycle, an obvious thing to do is to do some of our standard runs with that new model. So an ensemble of AMIT members, maybe some pacemaker simulations. I think we've heard a lot this week about these new high resolution versions of CSM1 where the quarter-degree atmosphere and 10th degree ocean seems to make quite a big difference. And I know that Pedro and others are advocating for us to kind of build out that hierarchy a bit more and see the relative roles of the ocean and the atmosphere resolution. So that's probably something we can contribute as well. I think we've done quite a lot of work recently on regionally refined simulations. I think we need to spend a bit more time looking at those to know what the next steps would be, but I think that's another avenue we can move forward with as well. So Adam, have you got the mic? Or okay, so please, if you have any thoughts, raise your hand. If you're online, I am paying attention to the chat, and you can also raise your hand and speak out as well. And so, yes, anyone have any thoughts? Pedro. Yeah, take them. Well, but the people online can't hear. So.
I think we have to build a hierarchy to understand why the simulation of climate variability and change improves so much in the full high-res simulation by mixing up what Ayla included there. I have a poster outside. I talked with a bunch of people on Monday, and the plan is to have a meeting on Zoom during the summer just to start coordinating how to build it with several computing resources. So it's great that the working group can contribute to perhaps some computer time. These simulations are very expensive to run, so perhaps the only way we can build a hierarchy is collectively. So that's the motivation for doing this, and perhaps propose a grassroots working group to do this down the road. But first we have to identify the problems that are interesting for the majority of the community.
Yep. Clara and then Dylan.
Just have a related comment when you said things are improved with the high resolution. ENSO is degraded. ENSO is very weak and has a periodicity beyond 7-8 years. So I think we really have to pay attention to, variability, trends, forced, internal, etc. And it's not a silver bullet at all, and it's super important.
So I was saying that I agree with Clara that the weakest point of the fully high-res ocean, high-res atmosphere configuration of CSM is that ENSO it's clearly degraded relative to the great ENSO simulation that CSM1 has at standard resolution. So it's probably also a challenge for this community, and that could be addressed. I've heard that Axel Timmerman has somewhat fixed this on some of their version. So it's something to research and should be addressed. Perhaps, I don't know if there's other questions I can keep. So the biggest critique that I've received, because I've talked to a lot of people about this, is why CSM1 and not CSM3? There's plans to do, but CSM3 is going to be a lot more expensive to run, so perhaps building a hierarchy will become prohibitive with CSM3. And there's a lot that we can learn with CSM1, which is a great model.
So I guess just a comment about Clara and Pedro's discussion, and then I have questions as well. I haven't looked at CSMHR enough to know about ENSO being weak. That was the first time I had heard about it, talking with Pedro about it. But just as a single data point, looking at these high-resolution model analogs that we've shown for the Northeast Pacific, you still do get a nice ENSO teleconnection. So even though ENSO is weak, you're still getting some real-world forecast skill for like the California current system. So I do think that is a positive, even though the variability seems to be too weak or in the wrong frequency band. There is still a positive there, and it could still be useful. And then my other question was, I just can't remember from the initial slide you showed, Isla, but are the regionally refined simulations, are they coupled or are they just AMIP?
They're AMIP right now, yeah.
Okay, and I'm going to ask with complete ignorance about how hard this would be. Is it possible to couple them?
I believe so. I think Adam is working on some couple configurations, but I don't think too much has been done with that.
Okay, then I guess that would be something I would advocate for, is a nice middle ground to expensive global high-resolution runs, or a fully coupled, regionally refined over CONUS, including like all the large marine ecosystems. Then you could do some really nice oceanographic work, but also the atmospheric work as well over land.
Yeah,
and long runs, like pre-industrial control long runs in regionally refined would be really nice.
Yeah, and maybe not just CONUS, but focusing in on regions where we think the resolution has mattered, like in the Southern Ocean and for the tropical Pacific. I think before going back to Pedro, John, did you have a comment? And then, unless Pedro is yours directly following on?
It was just, it's worth thinking about whatever you decide here, the amount of effort that you choose to, thinking about that conversation, but other things as well, the amount of effort you try to develop a high-resolution version as opposed to run a high-resolution version and hope it works. And so when you're thinking about the plans, and that involves computer time, of course, as well. So what's the right balance of investing in the computer to try and get the best simulations at those scales versus kind of hoping, I guess, is the other alternative.
And I think, like Steve showed some interesting results yesterday about CSM2 decadal predictions doing a lot better than CSM1 in some of these regions where high resolution has made a difference. So it seems like, yeah, maybe it's amazing with CSM3 and high resolution, and it's worth moving forward as well as doing, but I think, yeah, for long-term large ensembles pulling apart the role of resolution, I think it will be essentially impossible to do what Pedro is proposing with CSM3 at this point, but I think we should do both.
Yeah, so Clara's talk nicely illustrated how the initial states for the large ensemble were chosen and the consequences of that. But didn't address why. So why the AMOC was chosen as the thing. And a lot of the recent work has illustrated the role of the Southern Ocean, especially with high resolution models. So if you're going to do a future large ensemble, why wouldn't you, have you considered looking at other regions, maybe the Southern Ocean, maybe tropical Pacific? Why are we going to keep a priori choosing AMOC as a thing?
Yeah, I think when it comes to large ensembles, I think we have many things we need to think about. For example, do the high-res runs, is there a point in doing a large ensemble when we know that resolution seems to make such a difference? Should we be doing a smaller ensemble with high resolution? Should we be doing perturbed parameter ensembles? Yeah, and the initial conditions. I think this is, when CSM3 is ready, we definitely will need to be thinking about what's the optimum thing to do, because I think there's many different paths we could go on.
I don't have much to add, exactly. And, you know, we chose AMOC just because at that time that was considered the likely source of long-term initial condition memory, but I agree in hindsight, the Southern Ocean is a very prominent candidate, and I think it actually came out in what I showed at the end, that it's really the Southern Ocean that has this even longer timescale memory. But these are all, right, just now opened up for how to design the next generation of large ensembles.
Edward, did you have something more you wanted to say?
Yes, you can run the couple viable resolution couple.
Okay, Pedro was saying that yes, you can run coupled variable resolution. There's just not so much has been done with it so far, I think. Okay, yeah, Clara.
I think the strength of this working group is also, you know, the bread and butter AMIP toga pacemaker, and that we have large ensembles of those, because we really learn a lot by realizing, you know, what the sampling variability is. And I think, don't forget, this working group has such a strong role to play in that arena that the other working groups do not. So we should not at all abandon the baseline.
Yeah, I definitely think we need these basics for the new model runs. Yeah. Okay. Any more questions? Or I mean, thoughts? No, we can try and be first in the lunch queue. All right. Thank you all for coming. And yeah, if any of you have just not spoken up or you want to think about it more, definitely get in touch if you're thinking of things for the working group to do in the next cycle.
say I'm excited, and I'm sure I will get to know everybody pretty well soon. Before we, actually, I'm going to go up to the thing. All right, so we just have this little intro, and then we have discussions at the end of the morning, or the first session and the last session, and some of these topics might come up in there, so you'll probably see these slides again. But we just wanted to give you a quick overview before we really started, about where we are in terms of CESM 3, and lots of thanks to Dave Bailey, because he's been doing a lot of the actual testing of stuff in the code and running simulations. But we have the advanced snow physics in the code, we have landfast ice in the code, and we have CEIS running on the C-grid. Those are all already into the CESM 3 development code. They will require tuning once we actually get the final CESM 3 version, so we don't exactly know all the details yet. I will point out, I think what's going to come after the July 31st code freeze along these lines is landfast ice that uses subgrid scale bathymetry from MOM6. We don't have that working yet, and we're kind of pushing on other things. And that while CEIS runs on the C-grid, we are not coupling with MOM6 on the C-grid. So we will do that into the future. The two things that Dave is working on most studiously right now are putting in some melt pond parameterization improvements from David Clemens Sewell. So I think we're at the point of we're testing those, and that's looking pretty good. And then the one that's the most uncertain, but we would really like in the code, is the flow size distribution wave ice interactions. And so we're really working with external collaborators, primarily CC Bits at UW and Letty Roach, who's currently at Columbia, to try to get a version of that into CESM 3. And we're really pushing to have that done by July 31st. And then other things that are going to come up after that, so in CESM 3.x, who knows what, is we are hoping to have improved ice radiative transfer, improved ice conduction, and the perpetual sea ice biogeochemistry. We really would like to have that in there. We're waiting right now on hearing back from proposals, so hopefully we might get some money to actually do it. I think let's just stop at that for now. Some of the other things are better discussion topics. So we'll go ahead and start with our first talk.
Thanks, Alice. Welcoming Ash Gilbert to the stage.
Ash Gilbert. Sorry. Hi, my name is Ash Gilbert. I'm a PhD student at CU Boulder working with Dr. Jen Kay. And today I'm going to talk about isolating the influence of temperature-dependent cloud optics on infrared radiation within a model hierarchy. This work is in preparation for submission to GMD and is funded by an NSF Graduate Research Fellowship and the NASA Pre-FIRE mission, which launched just last week to study polar far infrared emission. So I'm just going to give you a quick primer on the optical properties of a liquid droplet. So liquid droplets neither scatter or absorb radiation, and how much droplet does of each is a function of wavelength and is represented by the complex refractive index, or CRI. Now, CRI has a temperature dependence for supercooled liquid water, as shown here when we see the 300 Kelvin CRI in black. Which is what is normally used in climate models to represent liquid water optics. And we also have here 3 sets of supercooled CRI, 240, 263, and 273 Kelvin. And crucially, in the atmospheric window, highlighted in pink, the supercooled CRI scatter and absorb more long-wave radiation. And in case studies modeling a single supercooled liquid cloud, this has been shown to produce higher downlink long wave at the surface, about 1 to 3 watts per meter squared. However, this has not been evaluated, these optics have not been evaluated in a global climate model. So what we wanted to know was, how can we assess the importance of a cloud optics change, like adding temperature-dependent optics, and are the effects of temperature-dependent liquid water optics on long-wave radiation substantial enough to be incorporated into model radiation schemes? I'm going to answer the first question by describing the methodology for our study. And we decided to focus sort of our study on the Arctic, given the prevalence of supercooled liquid clouds there. So the method we used to assess the importance of this cloud optics change is a model hierarchy of increasing complexity, or increasing model complexity, starting out with a simple conceptual mathematical model called a two-stream radiative transfer model, then moving up in complexity to a single column atmospheric model, then to a freely evolving global climate model that ran for several decades, and finally to a wind nudged global climate model where we constrained the dynamic variability so that the non-dynamical signal of the optics change would be amplified. So first, let's jump into the two-stream radiative transfer results, where we answered the question, do we see an effect with a conceptual model on a spectral scale? And to do that, we modeled downlink long-wave spectra from a single supercooled liquid cloud with a temperature-dependent set of optics and a temperature-independent set of optics. Independent optics are like the CRI at 300 Kelvin. I'll also refer to them as control optics. So here we have two spectra modeled by the two-stream model with the temperature-dependent optics at 240 Kelvin in red and the temperature-independent optics at 300 Kelvin in black. As you can see, over most of the model spectral domain, which was 750 to 1,000 wave numbers, which also corresponds to that atmospheric window I was talking about earlier, the temperature-dependent optics have higher downlink irradiance. And if you integrate this difference over the entire model domain, you end up with a flux difference of 0.35 watts per meter squared, which is a fairly small effect. All right, so stepping up in complexity to the single column atmospheric model, where we answered the question, do we see an effect with an atmospheric model at a single location on a daily timescale? For this model, we use the single column version of CESM CAM6 called SCAM, and we forced it with 17 days of observations from an Arctic field campaign to replicate the Arctic climate. So here we have the downlink long-wave flux at the surface from 4 SCAM runs, one with the CESM control optics, which are temperature independent, and 3 temperature-dependent optics runs at 240, 263, and 273 Kelvin. We took the difference in flux between the temperature-dependent and control optics runs. And as you can see in sort of the below panel, it's hard, the differences are unclear, and it's hard to attribute them to the optics change. So we decided to look at the downlink long-wave data only when we had supercooled liquid clouds present, because they were the cloud type for which the effect would be the largest. So here we have the median of the temperature-dependent optics data sets and the control data set, and the difference between each optics set and the control. And as you can see, we find a optics effect on the similar scale from the two-stream radiative transfer model, about 0.11 to 0.41 watts per meter squared. And we also did some statistical significance testing, and these differences are not statistically significant. So moving up to the, again in complexity, to the freely evolving global climate model, where we asked, do we see an effect with the global climate model over the entire Arctic on a decadal timescale? To do that, I ran CESM2 with in atmosphere-only mode with pre-industrial climate for the control optics and for 2 sets of temperature-dependent optics for 40 years. And so here we have the 40-year average downlink long-wave control at downlink long-wave flux to the surface. And then on the right, we have the 240 Kelvin and 273 Kelvin averages minus the control optics. So the rest of the graphs are going to look like this, just FYI, with the downlink long-wave flux average on the left and the differences between the temperature-dependent and control optics long-wave averages on the right. And as you can see here, the optics had an effect of about 1 to 3 watts per meter squared over most of the Arctic, but we did do some statistical significance testing again, and stippling would indicate that we had found flux differences that were statistically significant, and given that there is no stippling, the optics effect was not statistically significant for this experiment. So now, finally, at the last step of our model hierarchy, we wanted to dynamically constrain our model so that contributions to the flux differences from the dynamics would be reduced. And to do that, we implemented wind nudging, where model winds are pushed toward reanalysis winds, in our case, ERA interim winds. And we did that so we could answer the question, do we see an effect with a dynamically constrained global climate model over the entire Arctic? And to do that, I ran CESM in pre-industrial climate mode, nudged with winds from 1980 for 2 one-year 10-member ensembles. And both the wind nudging to 1980 and the ensembles helped to increase the signal-to-noise ratio of the optics effect in the long-wave radiation. And I also ran one of the ensembles in atmosphere-only mode and one of them in coupled mode, just to sort of explore the effect of coupling. So let's first take a look at the atmosphere-only mode. I ran with the control optics, 240, 263, and 270 Kelvin optics. And as you can see, the optics had an effect of about 1 to 7 watts per meter squared over pretty much the entire Arctic. And as you can see by the stippling, the optics effect was statistically significant. So yay, we found the we're at a level at which the optics effect was substantial. However, let's take a look at the coupled ensemble, where I ran control and 263 Kelvin optics, and you got about a 1 to 3 watts per meter squared effect over most of the Arctic, but again, no stippling, so no statistical significance. So here we think that adding the coupled ocean and ice components reduced the effect back down to an insubstantial level. And then finally, we decided to extend our wind nudge runs to a decadal timescale. So asking, do we see an effect with a dynamically constrained global climate model over the entire Arctic at decadal timescales? And to do that, we ran CESM2 in atmosphere-only mode with pre-industrial climate and nudge winds from 1980 to 2018 at the 39-year run, 3 ensemble members. And then here I ran it with control optics and 263 Kelvin optics, and you can see we have a very widespread 1 to 2 watts per meter squared effect. And some of that effect is statistically significant. However, the effect on this timescale is kind of small compared to climate variability. So wrapping up and addressing the main research question, was the effect of the temperature-dependent optics on long-wave flux substantial? For the two-stream radiative transfer model, we did see an effect, but it was very small. And we saw a similar size effect for the single column atmospheric model, but only when we looked at supercooled liquid clouds, and that was not statistically significant. And then moving up in complexity to the freely evolving global climate model, we saw a larger effect, but the interannual variability in the model was too large to say it was substantial. And then finally, to the wind nudge global climate model, we did see a substantial effect with the atmosphere-only years-long ensemble, but the more realistic coupled ensemble did not show a substantial effect. And finally, in our decades-long ensemble, we did see a small but reduced effect, but again, it was likely because of interannual variability both in the model and in the nudged winds themselves. So I want to leave you with 2 takeaways. 1, the effects of temperature-dependent optics are not substantial enough to be a first priority for model parameterization development. And second, a model hierarchy that includes wind nudging is a powerful model development tool to assess the importance of model physics chains. Thank you for your time, and I'll take any questions.
Questions?
I have one. I know you talked about this before, but you applied this only in the Arctic. I mean, is there an impact if you apply it in the Southern Ocean, other parts of the globe?
Yes, potentially, because again, Arctic is another place where we have a lot of supercooled liquid clouds, so that is definitely an area for future research to go do wind nudging in the Arctic and see if that has an effect there.
I have one. Your second takeaway is about using wind nudging as a tool for model development. Do you think that this, I guess, procedure of doing wind nudging whenever there's a kind of a new model physics change could be, I guess, how do you envision that being used in the future for CESM?
I guess you'd pick your optics wherever your physics change, and then you'd run it through this hierarchy, and you'd sort of pick whatever output variables you wanted to sort of look at to see what would affect, and then just check to see how it affects those, and if it's sort of creates a substantial effect, I guess. Yeah. I don't know.
Awesome, thank you. Our next speaker is Yuchi Lee.
Hello everyone, I'm Li. I'm currently a second-year graduate student at the University of California, Riverside. Today I'll be presenting our recent work on exploring the effect of AMOC weakening on Arctic amplification. So this work is a collaborative effort with my advisor, Walil, and the other three co-authors, Alexei Fedorov, Nicole Fadel, and Patrick Tyler. Okay, so the Arctic amplification refers to the phenomena where the surface air temperature in the Arctic warms at an enhanced rate relative to the rest of the globe. And it was first identified in 1975 by Manabe and Weatherald. It is one of the most robust features of the climate system's response to external forcings like the greenhouse gas emissions. So the figure on the right shows the significant warming trend in the Arctic from both the stational best observations, the TOPIS 1, and real analysis data, and as well as the climate model simulations. So although the Arctic amplification has been recognized for decades, that is actually that this drastic warming is only a recent occurrence. So the figure on the left comparing the shows the surface air temperature anomalies comparing the Arctic and the global average, highlighting the striking change in post-1980s in the Arctic compared to the global average changes. And the figure on the right shows the rapid transition from cooling to warming in the Arctic, which marks the significant climate shift in less than a decade. In addition, the Atlantic Meridional Overturning Circulation, the AMOC, that will transport a huge amount of heat northward and has an important role in regulating the climate. With the observed weakening in the Atlantic Meridional Overturning Circulation, this study aims to understand the role of AMOC weakening in Arctic amplification. So we used two sets of fully coupled simulations from the CESM model, that one with the weakened AMOC and one with the stable AMOC. Both simulations use 5 ensemble members, and the experiments are branched from 1980. So the difference between the free and the fixed AMOC simulations indicate the impact of the AMOC weakening. So here the figure shows the time evolution of the AMOC strength and the Arctic surface air temperature changes. So from the top panels here, where the blue line represents the free AMOC simulation, showing a decrease in the Arctic in the AMOC strength over time, whereas the red line represents the fixed AMOC simulation. So we could see the AMOC strength is stable over time. And from the Arctic surface air temperature anomalies, that we could see the gap in warming between the free and the fixed AMOC simulations get wider after 2030s and peaks by the end of the 21st century here. And hence, for this study, we will focus on the last 2 decades of the 21st century. So here shows the spatial pattern of the surface air temperature changes from the free AMOC simulation, fixed AMOC simulation, and the difference between the 2 simulations. So for the difference that we could see, there is a general cooling in the Arctic, which implies that the Arctic tends to stay cooler when the AMOC is weakened. So the figures below shows the zonal average surface air temperature changes and the amplification factor. So the amplification factor is defined as the ratio of Arctic to tropics temperature changes. So from here, that between 2081 and 2100, that shows a weakened AMOC is projected to reduce the Arctic warming by 1.37 degrees Celsius, and which corresponds to a 0.36 decrease in the amplification factor. From the annual cycle showing on the right side here, that the AMOC-induced cooling is most pronounced during the cold seasons. So we use the CAN5 radiative kernel to identify the main feedback processes. panels on the upper panel shows the annual mean partial temperature contributions from the free and mark simulation and the fixed and mark simulation. So we could find that for both free and fixed and mark simulations, that the effects of the individual feedback mechanisms are similar, and the difference is only from their magnitudes. So for both simulations that we could find the surface orbital feedback serve as the primary driver to the Arctic warming, followed by the Planck feedback and the lapse rate feedback. On the other hand, that the shortwave cloud feedback and ocean heat uptake act as cooling agents. So the lower panel shows the difference between the two simulations in annual mean and boreal summer and boreal winter. So we identified the three major contributors to this EMAC-induced cooling. One is the surface orbital feedback here, and the ocean heat uptake, and third are the temperature feedbacks. So we could find that this EMAC-induced cooling through surface orbital feedback is most prominent during the boreal summer, while the ocean heat uptake is most pronounced during the boreal winter. On the other hand, that the atmospheric energy transport and shortwave cloud feedback would slightly offset this EMAC-induced cooling. So here we show the spatial pattern of the annual mean partial temperature contribution from each radiative feedback. We first focus on the orbital feedback. So we can see a general cooling from the orbital feedback in the central Arctic. And the figure in the middle shows the difference of the sea ice concentration changes in annual mean, boreal summer, and boreal winter. So we can see, even though that the EMAC-induced reduction in sea ice concentration is most pronounced during the wintertime, but with the limited solar radiation, that the EMAC-induced cooling through the orbital feedback is more prominent during the boreal summer. So we further analyzed the ocean temperature heat budget, which are shown in the upper panels. From left to right are the temperature tendencies induced by advection and diffusion, and induced by surface heat flux and the net ocean temperature tendencies. So from the temperature tendencies induced by advection and diffusion, which implies that the EMAC weakening will lead to an ocean heat transport divergence and the whole depth water cooling, which are shown in the negative value here. And on the other hand, that we could find an atmospheric energy convergence from the, I forgot to introduce the lower panels are the radiative fluxes at the top of atmosphere at surface and the net fluxes into the atmosphere. So from the net fluxes into the atmosphere here, we could find atmospheric energy convergence over largely over the North Atlantic warming hole region here, so which are the positive values showing here. But however, that the cooling induced by the ocean heat transport divergence outweighs the compensation from the atmosphere and results in a net cooling tendency in the ocean temperature, and which further will reduce the sea ice loss. So next will be the temperature feedbacks. So from Planck feedback that we could see a general cooling in the central Arctic, but a warming in the North Atlantic warming hole region. As for the lapse rate feedback, that we could find a general cooling in both the central Arctic and the North Atlantic warming hole region. As for this EMAC-induced cooling through the lapse rate feedback, the figure on the right shows the vertical profile of the difference in the air temperature changes. So we could find that this EMAC-induced cooling through lapse rate feedback is mainly because of the strong cooling of the surface and lower to mid troposphere and the relatively weaker cooling in the upper troposphere. And in the North Atlantic warming hole region, that the warming from the Planck feedback is largely offset by the cooling through the Lapsride feedback. So the last one is the shortwave cloud feedback. So the AMOC-induced cooling will be slightly offset by the shortwave cloud feedback. So we could see that there is a general, slightly or general warming in the Central Arctic from the shortwave cloud feedback and cooling in the North Atlantic warming hole region. So the figure on the right shows the difference of the cloud friction from low-level clouds and mid to high-level clouds. So we could find that the warming induced by the shortwave cloud feedback is mainly because of the reduction in the low-level clouds in the Central Arctic, which will further reduce or decrease the reflection to the solar radiation and hence warm the Central Arctic. So in summary, that the AMOC weakening will lead to a slower increase in Arctic surface temperature, reducing the projected warming by 1.37 degrees Celsius or 0.36 in amplification factor by the end of the 21st century. And the main drivers of this reduced warming are from the surface orbital feedback and ocean heat uptake changes, which are stronger during boreal summer and winter respectively. And also that AMOC slowdown will induce ocean heat transport divergence at the North Atlantic warming hole region and causes the ocean to absorb more heat from the atmosphere and finally resulting in surface cooling. And also that the AMOC weakening will lead to a strong surface and lower to mid troposphere cooling through the Lapsride feedback. And on the other hand, that these AMOC-induced changes in the shortwave cloud feedback will bring about a slightly warming over the Central Arctic. So I will stop here. Thank you for your attention.
We have time for one quick question.
So thank you for a nice talk. The ocean modelers back in this corner are intrigued and how the heck you keep AMOC constant.
Oh, okay. Okay, no, there's no, okay. So we will gradually remove the fresh water in the North Atlantic northern than 50-degree north. So it will be gradually removed. The freshwater flux will be gradually removed in that region to fix the AMOC stress.
Thank you. Our next speaker is Ian Baxter.
Hello, everyone. My name's... Oh, sorry. Okay, that was my presentation. Sorry. Hi, everyone. My name's Ian Baxter. I'm a grad student at UC Santa Barbara. And today I'm going to talk about sources and land capacitor effects driving Arctic moistening and warming. I want to thank all my collaborators listed there, as well as acknowledge the critical role of the CESM Polar Climate Working Group in really getting these runs started. And a lot of what I'm going to talk about today was really inspired by discussion at the last Polar Working Group meeting. What we're really looking at is looking at this increasing trend in water vapor within the Arctic. So here, what I'm showing is total precipitable water during summertime, so JJA within the Arctic, so from 70 to 90 degrees north. And I'm showing it from ERA 5 in magenta, the CESM 2 in blue and gray shading, and as well as some ICSM 1 simulations that we did. When I say ICSM 1 simulations, I'm referring to using the isotope-enabled CESM. And we're really focusing on using its water tagging capabilities. And what we did is we combined it with a nudging approach. So we constrain UV, the horizontal winds, as well as temperature T. And the idea here was to really try and capture the changes in water vapor that we see in Aero 5, which, so we can look at the observed changes in water vapor within the Arctic. And so you can see that with the nudging, it's doing a pretty good job of doing that, where this black line, in terms of the trends and in terms of the year-to-year changes, it matches really well with Aero 5, despite this kind of stepwise bias between them. To go into more depth about what the water tagging is doing, and so you can see, hopefully more visually, what we're trying to do. What we do with the water tagging is we can define certain source regions where we're putting the tags. So in this kind of simplified case, we have 3 tags here, one in the tropics, one in the mid-latitudes, and one in the Arctic. And when water vapor is evaporated from each of these regions, it gets a tag specific to that region, and we can track it through its entire life cycle. And what we are interested in doing is looking at the Arctic change. So we'll follow those water vapor parcels until they're precipitated out within the Arctic. And so first, one of the first things that we looked at was looking at how the water vapor is transported into the Arctic. And to do that, we're looking at atmospheric rivers. Previous studies have shown that atmospheric rivers can account for about 80 to 90% of poleward moisture transport, especially at high latitudes. And so here, using the Guan-Walliser atmospheric river detection and tracking algorithm, we were looking at these ARs. And so here I'm showing summertime, or JGA, AR frequency or occurrence in the shading. And these are the trends from 1981 to 2022. The black contours are showing the trends in 200 hectopascal geopotential height, so this is our circulation. And then the red vectors are showing the trends in integrated vapor transport, which is being used again to calculate those atmospheric rivers. And so what we see when we look at this is that the shading with the blue, showing an increase in atmospheric river frequency or occurrence, is really concentrated along these very narrow pathways on the western side of these anticyclones. So there's one here west of Greenland, boxed by that magenta box. And we also look at this one over Northern Europe and another one over kind of Central Eurasia here. If we compare this with the CESM2 large ensemble, here we looked at 40 members with the smooth biomass burning from the CESM2 large ensemble. And if you compare the difference between our ICSM1 simulations, which are almost identical to Aero 5, with the ensemble mean here, you can see there's a very big difference in the pattern, where the CESM2 large ensemble mean, which is representative of our best estimate of the force signal, is fairly uniform. So you have this kind of uniform green increase in atmospheric river occurrence all across the Arctic. And if you look at the black contours, which is showing our circulation, that too is fairly uniform. One of the things that we noticed when looking at the red vectors here, which is showing integrated vapor transport, the transport here is very zonal. So it kind of comes from the North Pacific and it goes all the way around, maybe to the Atlantic. This is very much in contrast again to what we see in the reanalysis and in our simulations, where it's very meridional, especially if you look like here over Central Eurasia, and it's very concentrated. We also try to look at the spread and try to account for internal variability that might be accounting for those trends and the pattern that we see in the reanalysis. So what we do is we're looking at specifically this corridor here, west of Greenland. This is because there was actually a recent paper that came out on Monday that was showing that models across the board from CMIP6 struggle to capture these long-term trends in atmospheric blocking over Greenland. So this is one of the places that we pinpointed as probably having a difference between the model and between reanalysis. So what we did is we looked at this area inside that magenta box, and we found 2 members out of the 40 exhibit a statistically significant trend within that region in terms of atmospheric river frequency. But again, if you look at the integrated vapor transport shown by the red vectors, we can see that the vapor transport seems to be coming from the North Pacific and traveling across North America and then into this region, which is very different from in the ICSM-1 simulations, where there's this disconnect between the Pacific and the Atlantic, and a lot of the vapor transport is coming more meridionally and from North America. We can show this a little bit better utilizing those tags from the ICSM-1. So here, what we're showing are those same trends from 1981 to 2022, but it's showing the contribution from each of these tagged regions. So we have 54 here, and those are the numbers that you're seeing. And it's their contribution to Arctic, so 70 to 90 degrees north, total precipitable water. And what we find when we do this is that a lot of the regions that are most important coincide really well with those atmospheric rivers. So in this case, region 47 over North America, region 43 and 44 over Western and Central Eurasia. Here, what we find is that the remote sources, so the regions where we've tagged outside of the Arctic, so below 70 degrees north, are accounting for about 2/3 of the moisture changes within the Arctic. Here, our value is a little bit lower, I suppose, because here what we're doing in addition to that is we're normalizing the contribution from each region so that regions with a greater area don't have a greater contribution to those changes within the Arctic. If we don't do the normalizing, that contribution from remote sources jumps up to about 85%. But then with this, we wanted to take it a step further. And so here the tagging is kind of telling us a lot of the moisture is coming from, say, North America or Central Eurasia. But we know that it's difficult for these kind of land masses to sustain this kind of water vapor transport over the course of 40 years or 4 decades, like we're looking at. So what we do is we take it a step further, and we focus on these two regions, so 47, and then I'll combine 43 and 44 over Eurasia. And first, looking at North America, what we do is then we look at the tags and we look at we do the same kind of process as we did looking at the Arctic. So we're gonna look at the contribution to, in this case, it's precipitation over North America. And so we're gonna kind of leapfrog and assume that a lot of the precipitation coming into North America over region 47 is then getting transported into the Arctic. And so when we do this, we look at precipitation from winter through summer this time rather than just during summertime. And we find that a lot of the precipitation that was fueling the transport into the Arctic is coming from, say, the tropical Atlantic down here, or the Caribbean Sea, and then it kind of leapfrogs onto the continental US and then to northeastern North America before going into the Arctic. We break this apart into the different fluxes here on the right. And so the first column is looking at precipitation over North America, which is shown by the shading on the left. And we've split it into spring in blue and summer in red. And what we find is that over North America, a lot of that precipitation is actually still coming during summer. So it's quickly kind of recycled or re-emitted from the surface through, in particular, this column here, E-veg-T, which is showing plant transpiration. So a lot of the precipitation comes in and then the plants kind of emit it out before it makes its way into the Arctic in this case. The final two columns here are showing precipitation over the Arctic associated with any of the moisture tagged from that region 47 over northeastern North America. And this kind of shows that the role of the circulation diverting a lot of that moisture transport into the Arctic. So here the increase on the left. And a lot of that is going into the Arctic as opposed to going elsewhere. We also look at Eurasia, and this one seems to be very different, I would say, in comparison to North America. So we're looking at this region here at the top, so 43, 44. And when we look at, in this case, we're looking at winter through spring precipitation because there was a very big difference between winter and spring precipitation versus summertime precipitation. And when we trace the precipitation back, we see that a lot of the moisture here is actually coming from the Mediterranean Sea. So it's region 37 here. and to a lesser extent, it's coming from the kind of tropical Atlantic in regions 35 and 36. The panel on the right is showing again those kinds of fluxes. So again, the first column is looking at precipitation over regions 43 and 44. And we can see that really big increase in precipitation occurring during winter and spring. This is really coming during February and March. And then the following column is showing the decrease in precipitation during summertime. The middle columns are again showing evaporation. And again, we see that there's a very big increase in evaporation during springtime, coinciding with that increase in precipitation. But if you skip to the last two columns and look at the blue bars there, we can see that a lot of that evaporation that comes out during winter and spring doesn't make its way into the Arctic. It's getting pushed somewhere else. If we look at summertime, we saw that there was these two kind of anticyclonic circulations over Western Europe and one over Central Eurasia. And these two kind of patterns defer a lot of the moisture transport coming in, reducing a lot of the precipitation over the region during summertime. However, we still get an increase in evaporation, particularly through this plant transpiration, which is shown by E-veg-T. And this fuels a lot of the transport going into the Arctic during summertime, where we see that the circulation pattern with these two anticyclones diverts a lot of that moisture transport into the Arctic and reduces that transport that would normally be going somewhere else. And so just to kind of give you a schematic overview of this idea, which we're kind of referring to as a land capacitor effect, what we find is that a lot of the evaporation occurs during winter and spring from the tropical oceans, where it gets transported over the high latitude continents and gets deposited over kind of Western and Central Eurasia, as well as Northeastern North America, where it gets emitted by plant transpiration before being transported into the Arctic during summertime. There's also a component of those tropical oceans that goes at higher altitudes, as some of Handi's past work has shown, during summertime that has a contribution there as well. And so, just to summarize, what we've looked at here today is changes in storage and transport, where we find that circulation induced by the nudging in the model drives atmospheric rivers over Northern America and Eurasia. However, these kind of pathways do not seem to be captured so well by the CESM2 large ensemble. And even when the CESM2 seems to capture maybe the correct circulation pattern, perhaps the sources aren't quite right. And then we looked at those sources, and we find that a lot of the moisture is coming from the tropical oceans, but it comes earlier in the year as opposed to directly during summertime, and it's transported over the high latitude continents where it's re-emitted by plant transpiration into the Arctic. And so, thank you, and I'd be happy to answer any questions.
Ian, any questions for Ian?
Hi, really cool talk. Thank you. I understand this is going to take a lot of speculation, but I'm curious on your thoughts on, under a warming planet, presumably these high latitude continental regions will be snow-free longer, maybe with increased greening. Do you think that'll have a knock-on effect to precipitation over the Arctic, or is it water limited enough in those regions that it might not?
Not too sure about how water limited it is. However, I do think if there's more, like an increase in vegetation, maybe an expansion northward, I think that will have a really big impact in terms of at least how much is being emitted and being transported into the Arctic. It would also depend, I suppose, on the large-scale circulation trends and how those might change in the future as well. Because they do seem to be playing a really big role in terms of transport into those regions and the emission out as well. Thanks.
Eric?
Yeah, thanks. Just following on, it seems to me as though, you got this kind of half of the Arctic in your picture has a little slab on it, which represents sea ice. In a warmer world where that slab gets smaller or goes away, I would think there'd be a lot more just precipitation recycling in the Arctic itself. that in the Arctic would rain more, even if you only had the same amount of transport into the Arctic, because you can now evaporate locally. I mean, is that something you could look for in model simulations?
We can look at that. However, I think a lot of the past research on this has kind of suggested that that's likely not the case to happen. So even as you decrease the sea ice, there's still very weak air-sea gradients within the Arctic and pretty strong stability, I'd say, reducing those kind of fluxes from the surface. So you're not getting a really big response, and there's not that much coupling, I would say, between the atmosphere and the surface in that regard during summertime. During other months, that might not be the case. It might be opposite, but during summertime at least.
Thank you, Ian. Our next speaker is Jen Kay.
Hi, good afternoon. I'm Jen Kay. I'm going to talk a little bit about some work that I did during the pandemic that is actually finally seeing the light of day, which is kind of fun. Sea ice feedbacks cause more greenhouse cooling than greenhouse warming at high northern latitudes on long time scales. But before I do that, I just want to show some observations because I feel like it's always fun for this group to see what's actually going on up in the Arctic. And 2023 was a remarkably warm year globally. It was not a particularly remarkable year in the Arctic, though. I mean, 2012 is still our record low for sea ice. It wasn't the warmest year up in the Arctic. So kind of some interesting things to think about for this group. And also, we haven't seen a really large record minima in the Arctic since 2012, which makes me kind of nervous. I don't know how you all are feeling. But I think we're going to see a record soon, or we're going to have some explaining to do. And so this dates back actually to some work that I did with Marika and Alex in 2011, and there's been a lot of follow-up work on it too, just looking at how long you can go without seeing a decreasing trend, right? How long can you go? 10 years is fine. Oh yeah, plenty of internal variability. 20 years, not so much in a warming world. So we're at this spot right now where it's been pretty flat for like 15 years. So maybe I need to remake this plot with 15 years, but something interesting is gonna happen over the next 5 to 10 years. And all I gotta say is, welcome to the ride. It's gonna be interesting to see. Okay, but what I really was here to talk about was actually these experiments where we're doubling and halving CO2 concentrations. And this is actually really pertinent to thinking about future model development in addition to really fun science. Because the experiments that I'm going to talk about are actually abrupt halving and doubling of CO2 experiments, and they made it into the fast track. So we're going to see these experiments from multiple models. We saw a bunch of them, these experiments in the last CMIP generation. And one of the motivations for this is that we know the LGM is a really good constraint on climate sensitivity. And Jongju's work in the paleoclimate group, which is unfortunately meeting at the same time as us, has really shown, CESM2, the climate sensitivity, equilibrium climate sensitivity is too high, and the LGM provides a good constraint. So you might think, okay, having CO2 simulations easier to set up, maybe we could learn something from those that relate to constraining climate sensitivity. But the challenge is many of those experiments only run 150 years per CMIP protocols. And so one solution might be to just extend those existing experiments. And here's where the pandemic comes in. We're just sitting around, not as much to do, have some computer time to burn. Let's just get these runs going longer, which is a super easy thing to do relative to starting a whole bunch of new runs. So we kept them going. And the thing is, this has been done a lot for the doubling of CO2 experiment. It has not been done as much for the halving of CO2 experiments. And so I think it'll be interesting to see what we see. So here are our experiments. We're working in CESM1. That was the model we had these experiments for. It's also a lot cheaper to run for a long time, so we just kept it going. And we have a doubling and a halving experiment that we extended out 1,000 years. So the first result you can see from this table is we calculated just some e-folding timescales. How long does it take to see, 1/e of the response kind of thing? And you can see for tau global, that's the global response timescale, it's about double, more than double for the halving than it is for the doubling. So it takes longer to cool than it does to warm. And that especially, that signal is pretty large if we look in the high northern latitudes. So now you can start to see where we might be thinking about some sea ice creeping equatorward. We might think about the timescales that would affect that. You have to go to a lower latitude ocean, which, you know, has a little bit more depth you have to mix through. So you can see some reasons already physically why the doubling might be faster than the halving. So yeah, long runs are more important for the cooling than for the warming. So I'll just run you through a couple of the figures from the paper. This is just the first one, showing time series of the annual mean surface temperature responses. I would just focus on the top where we have, you know, the global and the high northern latitudes. And we can see, you know, after 150 years, we have more warming globally than we have cooling. And what's happening in the Arctic is about the same between these two in terms of absolute response. But if we go out 1,000 years, the cooling just continues. It continues to get colder and colder and colder. And there's some punctuated periods where the cooling kind of accelerates, but it's still cooling after 1,000 years. We just stopped at 1,000 years. But in contrast, the warming just kind of stabilizes. It seems like it kind of does its thing and it's done. So 150 years here looks really like not long enough to really know what the response is going to be for the cooling especially. So then we can just move up in complexity in terms of the plots. Here I'm just looking at the zonal mean through time, and the top is just the cooling. So you can see, you know, not much happening in the first 150 years, but then, you know, by the year 400 or 500, it's really started to cool a lot. That signal continues to kind of propagate towards the equator. And then on the bottom, I just have the difference in terms of the absolute response, warming minus cooling. So you see, obviously, more warming in the high northern latitudes where you lose sea ice and things. But that cooling signal in the mid-latitudes really starts to take over, and you get more cooling than warming, basically on these high northern latitudes. Then we looked at some maps, and this was actually really fun. This is where the sea ice signal really comes out. So the top, we just have maps of the warming and the cooling, and it's the warming over the first 150 years in like A, and then the last part of the run, you know, years 850 to 1,000 in B. You can see A and B look pretty similar. But if you start looking at E and F, they start to look more different, and those are for the cooling experiments. So the cooling, spatially, a lot of this cooling seems to be associated with expansion of sea ice. And the land signals looked relatively small. And so the bottom, you can just kind of see the sea ice loss or gain signals, and you see strong co-location of where the cooling and sea ice change is happening for. So why more cooling than warming? I first want to say it's not the CO2 radiative forcing. Actually, the CO2 radiative forcing is a little bit larger for a doubling than a halving. So these are some values that we had computed from a different paper. So it is all about the feedbacks. That's what's going on here. And it's the sea ice associated feedbacks that are really driving this cooling in the mid to high northern latitudes and leading to more cooling under halving CO2 than warming under doubling of CO2. So that would be the surface albedo feedback and the lapse rate feedback. So here I'm just showing the two of those, another one of these kind of zonal mean through time plots. The top is the albedo feedback in the cooling experiment, and then the bottom, the difference between the cooling and the warming. And then here's the lapse rate feedback, similar type of plot where the halving lapse rate feedback is on the top. You can see, you know, the positive lapse rate feedback going all the way to 45 degrees. And then on the bottom, the difference. So a quick summary here. If we looked at 150 years, we saw more warming than cooling, and that was due in part to the stronger CO2 radiative forcing from a doubling of CO2 and more positive 2 times CO2 feedbacks on those timescales. If we went out 1,000 years, we saw more cooling than warming. And this was really due to these slower feedbacks associated with sea ice expansion, positive lapse rate, and surface albedo feedbacks. We did look at other feedbacks too, but they were not really as big a part of the story here. And I think the open question, and one that I'm continuing to chat with people, and I know Zhangju and Betty Otto-Bliesner have thought about this as well, is how do we use these halving experiments with the LGM to constrain climate sensitivity, and do we need to just really encourage modeling centers to run the cooling experiments longer than 150 years? Because if we're not seeing the full story, it has a lot of implications for what we can interpret from those experiments for climate. So thank you.
Questions for Jen?
So does this mean that the feedbacks will be even weaker for quadrupling as compared to doubling of CO2?
No, I think the cooling, the difference between cooling under halving and doubling warming is there's a bigger asymmetry there than if you keep going up. And actually, Yvonne is in the back of the room and could probably talk about that, because he's done a lot of these experiments where you look at different rates of warming, doubling, quadrupling 8 times or whatever. Those seem more stable after 150 years, whereas this cooling one seems like you need to run longer. Yeah.
Yeah, thanks, Jen. Really interesting. So I'm very intrigued by the cooling aspect for clouds, because as we all know, clouds are a big feature of some of the findings from the LGM simulations and climate sensitivity and these things. And so we could potentially learn some things by looking at a cooling impact. So what did you see in the cloud feedbacks? I'm so curious.
The cloud feedbacks were really small in this model, but this is CESM1, which has pretty anemic supercooled liquid water in it. And so there's some model biases that I think contribute to why the cloud signal was not very strong. I think just in terms of a general research question, maybe not with these simulations, but understanding what the clouds do when the temperatures change that much is super interesting to me, right? Like mixed phase clouds taking over the planet, right? So I think that could be really fun intellectually to think about. But I don't think we can really look at the clouds in this experiment to get a lot of insights into how those changes might affect the coupled system, because the clouds just aren't good enough.
Hi, Jen. Nice talk. So in the slab, there has been previous slab ocean experiments where CO2 has been halved, and then we get to a glacial state where the sea ice just creeps all the way to the equator. And in this case, it seems that the cooling is not stopping. And if we continue the rounds for a few thousand years, it is likely that we're going to get to that state. So the question is, how, I guess, realistic is the sea ice growth in this experiment? Because it sort of jumps at like year 400, 450, it just creeps down. So how realistic it is? Because we have the LGM, which is roughly half times CO2, and we weren't in a glacial state. What are your thoughts?
I don't think we're going to get to a glacial state in this model. I think the slab ocean is kind of ill-poised for the half CO2 experiments. I'm happy to talk about that offline. I've seen those snowball Earth simulations too when putting in mixed phase cloud changes. Like, it's just a pretty sensitive configuration. But yeah, I think some of this may be model dependent too, like just how much cooling do we get when we have CO2 and keep going. So I think we have some learning to do about that and the physical mechanism. I will say I thought someone was going to ask me about AMOC. So I did look at AMOC, but it was also kind of a small story. Oh, I didn't actually put it in. Anyways, it was a small story. Oh, there it is. And AMOC is pretty stable in these runs, but like for example, what's happening at year 400 or whatever to sort of accelerate that ice loss, I think I want to look a little bit more at what the processes are that are driving those kind of steeper cooling time periods versus flatter cooling time periods, to just see what the processes are and have a sense of that. And maybe that could get some insight into like whether it's a physically reasonable thing we might expect or not.
Awesome. It sounds like there's some more discussions to be had later. Thank you so much, Jen. Our next speaker is Led Linitsky. Jed. Why does it say, of course, landscape emissions, the transport of these chemicals aerosol in the atmosphere, the chemical forces acting upon these species in the atmosphere? Sorry, Jed.
It may have been my fault from the beginning. Cool. So yes, I'm going to be talking about future changes to the North Water Polynya in a few different simulations of CSM1. And this work is currently under revision for publication and environmental research letters. So the North Water Polynya, abbreviated to NOW, or Pikialysis as it's called in Greenlandic, is the most productive ecosystem in the Arctic Ocean, and it reaches an average seasonal size of around 80,000 square kilometers, which is approximately the area of South Carolina. And it's formed by two different mechanisms. The first is northerly winds, which continuously advect sea ice away from the Nares Strait, creating open water and large latent heat fluxes. Additionally, these northerly winds lead to offshore Ekman transport and upwelling along the coastline of West Greenland, and leading to the upwelling of warm, salty Atlantic origin waters and sensible heat fluxes. And so, in addition to its ecological importance, we also really care about the NOW because it's a nexus point of transports of sea ice and fresh water between the Arctic Ocean and subpolar North Atlantic. And if we look at a schematic of the North Atlantic, of the subpolar North Atlantic circulation, and the left panel shows a zoom in of Baffin Bay and a kind of the approximate area, this kind of larger North Water Polynya region in black, we can see that there are kind of two main pathways for kind of fresh polar surface waters into the North Water Polynya. The first is via the Canadian Arctic Archipelago, and directly through the Nares and Barrow Straits. And then there's another pathway of these fresh polar surface waters that exit the Arctic Ocean via the Fram Strait, circumnavigate Greenland, and then flow northward into Baffin Bay along the West Greenland Current. Additionally, you have these modified Atlantic waters in the Erminger Sea. I don't know how the pointer works, but yeah. In southeastern Greenland, and these are warm, salty, nutrient-rich waters, which also round the southern tip of Greenland and flow northward into Baffin Bay. And so this talk really has three guiding scientific questions. First is, how does the size of the North Water Polynya change under different global warming scenarios? Second is, how do oceanographic conditions in the North Water Polynya change under these scenarios? And three, what are the implications of these changes on biological productivity? So for this project, we focused on 30-year means at specific warming levels instead of time. So we compare changes at different warming levels to the CSM1 large ensemble for 1980 to 2009, and we use this as our historical period. And then we also have a high warming level, or warming greater than 3.5 degrees Celsius, which we take from the CSM1 large ensemble from 2071 to 2100. And then over the same time, we also use two different low warming simulations, which were branched from the CSM1 large ensemble in 2009 by Sanderson et al. 2017, which use a custom greenhouse gas forcing to limit global temperature increases to 1.5 and 2 degrees Celsius. And so, how do we calculate the area of the Polynya? So in red, this is kind of our North Water Polynya region, and and the Polynya area is defined as the total area of all grid cells in which sea ice is less than 70%. But a Polynya isn't just open water. A Polynya is open water surrounded by sea ice. And Baffin Bay experiences a large seasonal cycle in sea ice. So we also have the second region to the south. And when the average sea ice concentration in the southern region is less than 50%, the Polynya area is defined as 0 because it's just open water. And when it's greater than 50%, the Polynya is present because there's open water surrounded by sea ice. And so on to question 1, how does the size of the North Water Polynya change under different global warming levels? So this plot shows the seasonal cycle of the North Water Plinia area under our different warming levels, with the NSIDC observations in black. And we can see two key features. The first is that as warming levels increase, the area of the Plinia increases in the spring, especially in March and April. And secondly, the Plinia disappears earlier, and this is due to increasing areas of open water in southern Baffin Bay. And we can see that clearly if we look at the cumulative probability of a given Plinia area in the spring and summer. An easy way to kind of interpret this plot is that the further along the x-axis you are, the increased likelihood of a larger open water area. And you can see in April and May that as warming levels increase, you have a larger probability of more open water. And then interestingly, in June, we see a similar pattern, but there's approximately a 50% chance of the Plinia not even existing in June. And this is because around 50% of the time, sea ice in Baffin Bay has retreated earlier, and therefore you don't have a Plinia. But when there is sea ice in southern Baffin Bay in this high warming level, the Plinia areas are larger in June compared to lower warming levels. And so question 2, how do oceanographic conditions in the North Water Plinia change? And we also see kind of two key changes. The first is an increase in stratification at the surface. And so this plot shows temperature and salinity profiles at 2 different locations in the North Water Plinia, one in the west and one in the east. And we can see in June, and this is true for many months in the spring and summer, that with warming you see increasing surface temperatures and then also decreasing salinities, but then at both locations. But we also see increasing temperatures and salinities at depth, and we associate this with the increasing intrusion and presence of this Atlantic origin West Greenland Erminger water. And so what physical processes are driving these changes? So surface stratification is a little bit more straightforward. In a warming world, we expect ocean surface temperatures to be warmer, but then we also have increased land runoff, of fresh water, which can reduce surface salinities, and we can see in our different simulations pretty substantial differences in the amount of runoff, between warming levels into the North Water Plinia. And we can also see, and there are also remote drivers of surface salinity changes. So Jan and Leho 2020 found that freshwater import into Baffin Bay through the Nares Strait is projected to increase in both under these low and warming, and under these same low and high warming simulations. So an increased freshwater transport from the Central Arctic Ocean can also help explain these decreasing surface salinities. And then in terms of the changes we're seeing at depth, Jackson et al. 2021 found that when you have increased stratification, you isolate surface waters from those at depth, and that allows for this increased intrusion of these warm, salty Atlantic waters further north into Baffin Bay and the North Water Plinia. And so, what are the implications of these ocean changes on productivity in the now? So this plot shows the seasonal cycle of NPP summed up over the entire region, and we can see that productivity is similar for all warming levels in January through May. Under lower warming levels, peak NPP shifts from June to July, and under higher warming levels, we see a similar shift in the timing of NPP and a slight reduction. But as I'm sure you would expect, productivity is not spatially uniform throughout the Plinia. And we see productivity is actually highest in regions where sea ice retreats earliest in the spring, which makes sense because when sea ice retreats earlier, you have open water and you have more available sunlight. And so we focus on these 2 regions in the east and west, which are the same regions we saw the temperature and salinity profiles for earlier. And so if we first look at the west, we can see that productivity is similar for all warming levels January through April. But under lower warming levels, peak NPP shifts from June to July. And under these higher warming levels, we also see a decrease in peak productivity, which we attribute to increased stratification, which reduces the ability of nutrient the mixed layer to be replenished in nutrients throughout the growing season. And then in the west, we see we also see kind of roughly very little differences in January through June. But interestingly, under lower warming levels, we actually see an increase in productivity, which we attribute to kind of this increased prevalence of this really this warm and nutrient-rich water mass at depth, which also given this location being situated on the West Greenland coastline, is a key region of upwelling from these northerly winds. But under higher warming levels, stratification is too strong for these for these nutrients to actually reach the surface, leading to a reduction in productivity. So there's kind of a complex balance here between increased nutrients at depth and stratification at the surface, which kind of limits the ability for those nutrients to actually reach the surface mixed layer. So just to summarize quickly, under increased climate warming, the now will open and disappear earlier. Surface stratification will increase in the Arctic due to freshwater input and land runoff. And warm, salty, nutrient-rich West Greenland Erminger waters will intrude deeper into the North Water Polynya. And under low warming scenarios, productivity may increase due to more available nutrients at depth despite increased stratification. And under higher warming scenarios, stratification is too large to make use of increased nutrients at depth, leading to a decline in productivity. And in sum, these results point to the need to limit global warming to 2 degrees C in order to prevent substantial and adverse environmental impacts in the North Water Polynya. And so thank you so much for your attention. I'm happy to take any questions.
Questions for Jed? I have a question. Okay, so my question is about the fact that the sea ice doesn't currently have proper biogeochemistry. And so what putting BGC into the sea ice, like what might you hypothesize? Like would you have different findings? I'm just curious. Like how much does the BGC in sea ice contribute to the answer?
I'm not sure, just because I'm not really an expert in kind of BGC sea ice interactions. But I think at a first glance, there's a lot of I think one kind of major limitation of kind of this study is that we don't have an ice arch. And so, so here we can have the observations of the Nares Strait of sea ice fluxes through the Nares Strait in black, and then this is kind of over our historical period. So I think we're kind of thinking from like a modeling sense. I think they're kind of putting in a more realistic ice arch would kind of do much more in kind of constraining these findings than kind of I think maybe BGC sea ice would kind of be a second order kind of thing to kind of look at compared to having a more realistic kind of in terms of kind of looking at like the full realism of sea ice. I think, there would be other places to go first, but I'm not an expert, so I'd be open to hearing other people's thoughts on that.
Awesome. Thank you, Jed.
Thank you.
Our next speaker is Renee Wingard.
Okay, I'm going to share my screen. I hope you can see it over there. Okay, so my name is René Wijngaard. I'm a postdoctoral researcher at Utrecht University. And here I would like to present some of our work on the impacts of regional grid refinement on climate extremes over the Arctic in storyline-based VR CESM simulations. So why are we doing this? Now, the Arctic environment is a rapidly warming environment, and it's most likely that climate extremes will change towards the future. So in order to improve understanding of future changes in extremes over the Arctic, we think storylines could be helpful, as storylines are more like plausible future pathways that could be more representative for the regional climate change over the Arctic itself. And instead of using greenhouse gas emission scenarios that have a large spread and making it also more difficult for decision makers to develop adaptation and mitigation strategies. So our objectives are to understand future changes in temperature and precipitation extremes over the Arctic by means of these climate change storylines, and also to understand the impacts of regional grid refinement. So how did we do that? For that, we applied the variable resolution community Earth system model. And in order to do that, we did AMIP style simulations with CSM version 2.3. I can hear someone else talking.
We don't hear anyone else in the room. We just heard you.
Oh, okay. Yeah, I can hear some echo sounds, but whatever. I will continue. Okay, so we did AMIP style simulations with CSM version 2.3, applying interactive atmosphere and land surface models, and prescribed daily SST and sea ice from either ERA 5 or CMAP 6 models, depending on the scenario. We did model runs with both uniform grid and a bipolar VR grid with regional grid refinements up to 28 kilometers over the Arctic and Antarctica. But in this specific simulations, we mainly focused on the Arctic. Okay, this is the experimental design. First, we started with kind of observational control present day simulations, where we forced our model with ERA 5, SST, and sea ice. And then we did the storyline simulations, both for present day period and for a far future period. And those storylines are developed by a colleague of mine and are mainly looking in the drivers that can explain best Arctic climate change, namely the strong a combination of polar amplification and SST warming and the Barents scarcities. So the first storyline, which is also a bit shown in the maps over here in the first column, is a combination of strong polar amplification and weak SST warming. And even we can see some SST cooling over the North Atlantic. And the second storyline is actually based on strong SST warming over the Barents Scarcity, which can be shown in the second column. And that is also accompanied with strong sea ice loss. So how does it work out? Now, first I would like to show you some of parts of the evaluation. I cannot show you everything, but this is what I would like to show you. Just focusing on the annual temperature and precipitation, we can already learn, if we compare it with ERA 5 or the newest JRA reanalysis data set, is that CSM is much colder, particularly over the sea ice dominated regions, but also over the northwestern part of Canada, and that this bias gets slightly smaller with refinement. If we look into precipitation extremes, the bias compared to this data set is relatively small, but you see that there are more regional differences. So particularly over the mountain regions of Norway and the southeast Greenland and along the Pacific coast, you can see that there are some distinct features, and that also that in the refined simulations, the precipitation increases over these regions. So now looking into the extremes, in this slide and in the following slides, I would like to show you how the temperature extremes and precipitation extremes look like for present day and the future. Here you can see the present day temperature, for the annual maximum temperature and the annual minimum temperature for both unrefined, that is in the first column, and refined simulations, that is in the second column. We learned that the annual maximum temperature patterns are similar between the unrefined and refined simulations, and that these patterns are also similar for the annual minimum temperature, but these simulations get slightly colder with refinement. For example, over Siberia, you see that there's some cooling. For the future changes, I would like to show you some bar charts, and those bar charts illustrate changes in extremes and precipitation and temperature extremes, and they are representing changes over land, sea ice, and ocean. And then for both storylines and unrefined and refined. So this, the storyline 1 is then in the first two bars, so to say, and the second storyline is in the third and the fourth bar. And then the unrefined is the lighter color and the refined is the dark color. And what do we see is that the annual maximum and minimum temperature increase in both storylines, and that the increase is much stronger in the second storyline, presumably because of the larger loss in sea ice in this specific storyline. If we look at warm spells and cold spells, which is defined as the annual number of extreme warm or cold days in intervals of at least 6 consecutive days, we see that during present day, warm spells are more frequent in the unrefined simulations, particularly over Alaska. And if we look into the future, we see that warm spells, of course, become more frequent in both storylines, where the second storylines increases are stronger. For the cold spells, we see that they are also more frequent in the unrefined simulations, and then it happens more or less, particularly over the Barents-Kara Sea region, where they are much stronger. And if you look into the future, then we see that cold spells become less frequent, except over the ocean. And as you can remember in the few slides before, we saw an SST cooling over the North Atlantic, and that could also explain why we see here an increase in cold spells over this particularly region. Then the precipitation extremes. For this, I looked in extreme precipitation and the highest 5-day precipitation sums. We see that the both extreme precipitation and 5-day precipitation sums are higher in the refined simulations, particularly because of the better resolved topography, but also because of increased convective precipitation, as for example, is visible along the edge of the map over East Asia, for example. And if we look into the future, we see that they are both increasing in both storylines, whereas also the second storyline increases tend to be a bit larger, which is presumably because of the SST warming that causes an increase in atmospheric moisture content and thus more precipitation. Then if we look in heavy precipitation days and consecutive dry days, we see that heavy precipitation days are more frequent in refined simulations, and they are more or less follow the same patterns as the extreme precipitation. So they are also stronger in the refined simulations. And that, of course, they are also increasing in both storylines. Consecutive dry days are a bit higher in the refined simulations, but the patterns more or less resemble. So you see that the greatest number of consecutive dry days appears over the Arctic and to some extent over East Asia. And you see that the consecutive dry days decreases over land and sea ice and increases over the ocean. And that brings me to the conclusions. So we see that present day annual maximum and minimum temperature are mostly similar between the refined and unrefined simulations, and that the annual minimum temperature is a bit lower in the refined simulations. Cold warm spells occur less frequently in refined simulations. If you look to the future, we see that annual maximum and minimum temperature increase in both storylines, that warm spells occur more frequently and cold spells generally occur less frequently. Precipitation extremes, we see that present day precipitation indices are higher in the refined simulations, and that heavy precipitation increases in intensity and frequency towards the future. Consecutive dry days decrease over land and sea ice and increases over the ocean. And that is my contribution for today. Thank you very much.
Questions for Renee? Okay, let's keep going because we are running a little bit behind. Thank you, Renee.
Thanks.
Our next speaker is Maddie Smith.
Okay, can you see my slides okay? Can you hear me?
Yes.
Okay, good. Okay, yeah, it's been super cool to hear what people are working on, and yeah, here's some updates. I'm gonna take us really small scale, so hopefully that's okay. I am mostly an observationist. I think a lot about like sea ice and upper ocean stuff in the Arctic, and so yeah, I want to talk a little bit today about some observations from Mosaic in 2019 to 2020, which I was a part of, and provide us this really nice comprehensive set of observations of the sea ice, upper ocean and atmosphere over this annual cycle. So of course, this is just a point in space and time, and so some challenges in comparing with the model. But I think that we think that these observations can help evaluate aspects of the sea ice model, and so particularly I'm going to be talking about some aspects of the summer mass balance and freshwater storage. So in this context, analysis really centered around the freshwater budget, very local to sea ice in the upper ocean, so ignoring general freshwater from other basin sources. And the goal here is to understand how much freshwater does sea ice and snow produce locally, and where does that go? So the meltwater can be coming from snow and sea ice melts from both the top and the bottom, as well as freshwater potentially from precipitation. So those all contribute to really local sources of freshwater. So that's on the left in the budget. And then on the right, we have different sinks where you can conceptualize this freshwater potentially sort of spreading across the heterogeneous sea ice cover in a thin layer. So this can include sort of three primarily fresh locations. So melt ponds on the surface are something that's very obvious and really important and more commonly studied, but then we can also potentially have thin layers underneath the ice and in leads between ice flows. The rest of this is probably then mostly incorporated into the upper ocean, into the mixed layer below. So without getting too much into detail of the methods of the observations, the kind of general results that I'm going to present from our set of observations from this big campaign combine a lot of different ways of measuring how the sea ice and upper ocean are changing to get at, to the best that we can, each of these terms and how they're evolving kind of over this area in the central Arctic, where we're on a piece of ice that represented both second year and first year ice kind of in the central basin. And so it allows us to characterize kind of how these terms all sum up over time at this point in space. And so especially looking at the sources on the left, we can see that cumulative freshwater over the course of the summer. The total is growing, so that's the black line, and then we can separate it out into the terms of sea ice melts. So in particular here, I think the kind of most striking thing is that the surface melt of sea ice, and the teal is providing the largest fraction of that freshwater during summer. And then in comparison on the right, we have the quantification of the different sinks that we were able to measure. So the total is the black line, and then that includes contributions from melt ponds on the surface of the ice in the blue, and then the pink and purple are these sorts of thin layers in the upper ocean that we kind of uniquely were able to observe here. And then the brown is actually how much is like in the ice, so like in the brine internal structure of the ice as it's kind of flushing. The main point here is actually that all of these terms are quite small compared to the total on the left. So if we look at that total at the end of the summer in the sinks, that's only 0.25 meters compared to almost a meter in terms of sinks. So most of that fresh water is actually making into the ocean. About 75% is kind of getting incorporated into the ocean throughout the course of the summer. And the fresh water that's retained in those other sinks, including melt ponds in particular, which I'm going to focus more on, is small, but still likely really important to capture. And the fact that it's small may in some ways make that even harder to capture. So I'm going to talk in the next slides a little bit about some of the comparison with model representation of some of these same aspects. But just as a note, so, we're looking at a flow which was hopefully representative of the broader area and was a pretty large piece of ice, but it's still small in the scale of what we're looking at in CSM2, where we're picking one grid cell to compare with. But this flow is still about thousands the size, the area of that individual grid cell. So thinking first about the freshwater sources, so this actually comparing on the left is actually comparisons with a prior campaign, so Shiba, which maybe many of you are probably familiar with, which took a similar approach to quantifying these meltwater sources and had some differences, but actually sort of a generally similar story where we had kind of about a meter by the end of the summer with the largest fraction from surface melt. So then on the right is the cumulative freshwater from a CSM2 run, which had the appropriate outputs to compare with this sort of partitioning from the observations. So this is actually a historical run, so it's covering a slightly different time period, but that is actually basically between these two campaigns, but at a similar point in space to Mosaic. But what we can see, so in total, the meltwater sources, the black line, are about 30% lower in the model compared to the observations. But I think what is more notable is the partitioning of these different sources. So a much higher fraction of that is coming from this bottom melt, so that's actually going directly into the ocean, so can't get trapped in these sort of surface sinks like melt ponds. Yeah, with the surface melt is a much lower fraction in the model compared to our observations. Okay, so next comparing the melt pond. So I think we heard a little bit at the beginning. A lot of you have heard a lot about the kind of potential improvements to melt pond parameterizations, and there's, I think, been a lot of motivation for why these are really important. And so wanted to kind of compare how the model is representing the storage of freshwater in particular as this kind of fractional storage of what's available. So the plots here are looking at the fraction of surface freshwater, so calculating that volume basically in ponds as a fraction of the volume that's available, so from surface melt and snow melt. So the left, I'm actually again comparing from these two campaigns. So Sheba, the kind of in the 90s, is in the dashed line compared to Mosaic. And I think this is really interesting because they have sort of different temporal evolution. They're in different locations on different types of ice, but we actually see generally like a similar range of values covered from kind of minimum around 5%, but up to around 30 or more of the total freshwater stored in ponds. This is interesting then also when we compare it with CSM2 on the right, where you can see that in general, CSM2 is estimating a substantially lower storage of that freshwater in ponds. So the maximum here is much lower than in our observations from either campaign, and also has a pretty different evolution over time. Yeah, so but of course here we're looking at this coupled model, CSM2, with all these different components that are evolving. And so it's kind of hard in this comparison to really separate how much, both in this and then in the prior slide, how much of this is due to both to forcing or the physics representing these processes. So I'm not going to dwell too much on these results, but I think one really good way to diagnose this is with using these forced 1D comparisons. So David Clement Sewell has done a lot of work thinking about melt ponds, but also generally how we can use Mosaic to better understand the representation of sea ice. And so he's created this one-dimensional forcing using the 1D component ice pack from the sea ice model in CSM2 to represent how these different terms evolve over time. And so just kind of, these are two plots from his work. And so the left, I think, kind of shows, is just maybe a quick way of seeing that in these forced 1D comparisons, the meltwater production compares pretty well. Similarly, the mass balance evolves fairly similar to the observations. But on the right, again, we see that the melt ponds don't. So the melt pond kind of equivalent freshwater value is peaking in the model at about 0.02 meters compared to the 0.05 to 0.45 meters that we had in the observations. So from kind of isolating it in this context, we can really see that the differences in freshwater sources maybe, which were, a smaller order of magnitude, but that to some degree may be a result of the representation of climate, but the melt ponds are likely a result of the processes. And so, yeah, just to sort of kind of conclude, I think the main points that were from this work and some of the other work that David has done is that obviously melt ponds are really important, and that the underrepresentation of melt ponds is a really key target for improvement. And so, yeah, as was mentioned at the beginning, some of those suggestions for how that might be improved are hopefully making it into the new version of the model, and hopefully will be really important for how we represent a lot of other processes. Thin layers in melt ponds, but then also in the upper ocean are really important for a lot of different processes. Better representing melt ponds can impact a lot of feedbacks, but there may be other things that are represented with how we, that are impacted by how we represent and where this freshwater is ending up, that could be potentially parameterized in other ways for future versions of the model. Okay, that's all I have. Thank you.
Questions for Maddie? Okay, moving on to our next speaker, Kate Hedstrom.
Share screen. How do we? There we go. Okay, play. Sorry. Yeah. Hi, I'm Kate Hedstrom. I'm a staff scientist at the University of Alaska in Fairbanks, and I'm here representing mostly the work of Andy Mahoney's lab, where they had a field program up in the Arctic, looking at the landfast ice, and this is also the work of the GFDL group. They're working on the regional MOM6 model, and most of the support here is the Bureau of Ocean Energy Management, supporting that landfast ice observational effort. And let's see. The domain I'm running on is this regional Arctic model, shown here at 12 kilometers resolution. And it's the MOM6 ocean CIS2 ice enriching from the ice pack library, forcing with JRA 55DO and open boundary conditions from the GLORIS European reanalysis. And the rivers also come from their products, and except in the Gulf of Alaska, where we have David Hill's improved runoff. We have tides and the cobalt BGC tracers, so we're still trying to get those tuned. We're using the DuPont landfast ice parameterization, and it wants more than the default 5 ice categories, so we're using 10. And this is a hindcast effort from 1993 to 2019, mostly. Looking at the ice extent compared to the satellites, we have a bit of an overestimate, but it's stable from year to year throughout this 20 some odd years. So could be worse. So the landfast ice parameterization, Jean-Francois Lemieux came up with a parameterization that's suitable for one single ice category. And the premise is that each grid cell has some fraction of ridged ice, and where you have the ridge, you also have a keel, and you figure out how deep you think that keel is, and then you know the ocean bottom depth in each grid cell, and if the two intersect, then you apply a bottom drag to the ice. And then DuPont, just a few years ago, came up with a scheme saying, well, you don't have just a single ice category, you have more information about the ice in each grid cell. So some cells have thick ice and some don't. And you look at the ice thickness distribution in each grid cell, and you fit a curve. So that's shown by the black line here. And on the left is a grid cell that has a bunch of thick ice. And on the right, you have a similar ice distribution, except there's no thick ice. And then meanwhile, this yellow curve is the distribution of the bathymetric roughness in that grid cell. And so you have a mean depth as well as some knowledge of how much that varies. And so you carry around not only the depth field, but a bottom roughness field to use to fit a curve. And then you look at the intersection of the yellow curve and the black curve here to decide whether or not to apply the bottom drag. And so comparing to a Canadian product that I received from Lemieux back some time ago, for the Arctic, for the entire Arctic, Pan-Arctic region, comparing to I've got a bunch of different model runs here. And so we're not doing too badly. And this year of minimum ice extent is because their product was not showing, I don't know, somehow they blanked out the Canadian archipelago. So each year, much of the landfast ice is in the Canadian archipelago. And if you skip it that for a year or two, then I'm not counting it. Anyway, that's what's going on Pan-Arctic wise. The Bureau of Ocean Energy Management is more interested in what's going on in the Beaufort and Chukchi Seas specifically. And so that here's the north coast of Alaska, the Beaufort Sea, and then the Chukchi Sea is here. And you can see there's some shallow bits, Herald Shoal here and Hannah Shoal, as well as this island, Wrangel Island. It's over in the Russian waters. And so here's how I do in the Beaufort Sea compared to the black observed product. Again, not terrible. For the Chukchi, I'm doing much worse. I'm overestimating the amount of landfast ice. And it perhaps should be that in the model, you have to pick some velocity threshold, and maybe I need to just pick a lower velocity to count something as being landfast. So that's something I need to check. But Lemieux picked 0.5 millimeter a second as his cutoff over a 2-week average, and that's what I'm using here. The Andy Mahoney's group has been studying the landfast ice in this region for many years. And they have a different way to evaluate whether it's landfast or not. And they're using RadarSat and other such products, more similar products, using synthetic aperture radar in part. And they look at vectors going from the shore to offshore and looking at how thick the ice is, or how thick the motionless ice is. And so instead of looking at an area metric, they're looking at a distance metric. And they're also looking at the timing. So first ice would be some here in November. This is a typical grid cell. And then later there's the onset of breakup in May. And the last ice is here in June, July. And you can look at the timing of that throughout the years. And see that the landfast ice time duration each winter is getting shorter. And there was this especially bad year, 2016. So Chukchi and Beaufort Sea. And in the Beaufort, the typical ice that happens, so the most landfast is bottom fast. If the ice freezes all the way to the bottom, that's happening just at the very closest bits to the shore. And then the next most stable part of the land, or the ice, is sheltered landfast ice, where there's barrier islands along here and also along Prudhoe Bay. And so that protects the ice there from the offshore waves coming in and disturbing it. But you can also get landfast ice beyond these barrier islands. And so this is what's more susceptible to storms coming in and causing breakout events. And that's shown in this hash area. And this is the width for the Chukchi and the Beaufort through time. And this is another metric. They're looking at how variable it is along that coast. So like in the Beaufort, you can measure it at each of those vectors I showed, and how much variability is there along that with time. And then here's another metric for looking at the landfast ice stability. So this is probably a bathymetric feature causing the ice to be more stable inshore of that. That's what these yellow ellipses are showing. And again, another, this is by decade. So the earliest decade had wider landfast ice extent, and then it's just gotten thinner with time. And this is a climatology of the landfast ice observed. So it's, you forget the first landfast ice in October, it gets thicker. So October, November, and then in March it's the maximum extent, and then it starts melting away, and then by July it's more or less gone. Comparing to the model, these are two different model runs using different ice ocean coupling physics. So the run 56 is a kind of an experimental thing that's not quite right yet. So let's focus on run 51. And the different colors show using different speed cutoffs for what you consider to be landfast. And you can maybe it's somewhere between this these two slowest speeds that gives about the right, well, yeah, the right amount of ice here in Kotzebue Sound, for instance. So in summary, this is a nice data product, and so that's available from the Geophysical Institute here at UAF. And the model can capture some of the landfast ice features with these parameterizations, and it's sensitive to the speed you pick. So what's important to the natives is whether you can trust the ice. And Mahoney's lab is using a 500 meter length scale from the coast, and I just can't resolve that with my 12-kilometer model. So I'm not getting the right timing of the onset and ending of the landfast ice for these coastal areas. Thank you very much.
Questions for Kate? Dave has a question.
Just a quick technical question. In the probabilistic stress formulation, are you using a constant standard deviation? Or are you reading that in from the bathymetry file?
Yeah, I'm reading it in from a bathymetry file.
Okay.
So Alistair has a 2013 paper where he describes how to compute that. So there's code out there that Nikki Zada put out on GitHub, how to compute from the GEBCO. So that's what we do. We have a field of the bathymetric roughness.
Okay.
Thanks so much, Kate. Our last speaker before break is Ed Blanchard Rigglesworth.
Hi, everyone. Hopefully you can see me and hear me. More importantly, see the slide. Great. Thanks, Alice. Okay, I know I'm between you guys and break, so I'll try and be concise and brief. I do want to start by saying I've struck through my original title. I wanted to be a little bit more maybe optimistic, but I really liked how Ash opened the session showing the promise of nudging simulations, and I think that I'm definitely a big proponent of these sort of simulations for understanding many aspects of model physics, but also the observations. So this is my new title that I'll let you read, and I'm going to focus on the Arctic sea ice loss case study. I do want to acknowledge my co-authors, especially Sam Brenner, who's the co-first author, and anyway, I'll dive right into it. So we're focusing on this, what I think is a very fun and fascinating and interesting case study. This is the record January 2022 Arctic cyclone. I show on the left in black contours the sea level pressure on the 24th of January. And this cyclone reached a central depth of 932 millibars, which is the lowest by far sea level pressure recorded or estimated in the Arctic. In the shading in red, that is the loss of sea ice concentration between the 21st and the 27th of January, so the 6 days, so right before and right after the storm. And if you integrate that sea ice area loss, this resulted in the largest 6-day change in sea ice area for this region of the Arctic, and that's the histogram on the right. So we have a record cyclone resulting in a record sea ice loss, and we wrote a paper in 2022 kind of highlighting and diagnosing the cyclone. And one thing we mentioned is that the atmospheric heat fluxes from the cyclone cannot account directly for this sea ice loss. The storm, it was warmer than climatology, but it wasn't that warm, and you just can't melt or lose all the sea ice just with the atmosphere. So we thought that the ocean would be doing something interesting. Since then, we found we've kind of gone deep into this case study, and we found one Argo float, which very conveniently was sort of in the key center of the Barents, and this is shown on the left, where this Argo float was located in January 2022. So it was under the sea ice, but right in the kind of marginalized zone, really close to where the center of the cyclone passed over on the 24th of January. And that's on the left. Shown on the right are the temperature and salinity profiles from this Argo float throughout that month. And in blue, I've highlighted the dates before the cyclone, and in red, we've highlighted the dates after the cyclone. And the bold dashed lines are the means of the profiles before and after the cyclone. So you can just pay attention to the bold blue and the bold red, and you can see in the temperature profile that there was significant cooling of the whole ocean below the mixed layer depth. So between depths of about 60 meters down to the bedrock at 200 meters, the whole ocean cooled. And if you look at the salinity, you can see that the mixed layer got a little, this salinity increased, but below the mixed layer, the salinity decreased. So that is evidence of mixing of the whole column and sort of salinity being transferred from below the mixed layer into the mixed layer. If you do a kind of quick back of the envelope calculation, the ocean cooling is enough heat to melt 0.5 meter of sea ice. So I think this is pretty strong evidence, combined with the fact that the atmosphere can't account for that sea ice loss, that it was basically the cyclone led to ocean mixing, which then led to heat flux to the sea ice and melted a little of this sea ice. So we were curious to see how CESM would do, and we've done this with a nudging. So we have replicated the observed cyclone in a fully coupled set of simulations by nudging the winds above the boundary layer to the winds from 2022. And we've branched off the CESM lens runs. All the forcing and physics is exactly the same as the CESM lens runs. And we've done this in 4 different mean states, present day or 2022, and then 20 years into the future each time. So 2041, 2061, 2081. And the 4 panels on the left, they show, again, the black contours sea level pressure on the 24th of January. And then the shading is the difference in sea ice concentration between the 21st and the 27th of January, so right before and after the cyclone. And again, I'm showing the observations on the right so you can compare directly. The bottom line is that even though the model is sort of replicating the cyclone very well by design, because we're nudging the winds, the sea ice reacts very weakly. There's a little bit of sea ice loss to the east of the cyclone centers along the sea ice edge, and there's a bit of sea ice gain to the west of the cyclone center. But on the whole, there's much less loss than in the observations. And what's interesting that as you actually go into future climates, so in 2081, the magenta is the sea ice edge, and that ice edge is actually quite a bit further north from the cyclone center, just because of global warming, and we get even less loss in that time period. But on the whole, sampling these 4 different mean states shows that we never sample or we never replicate the observed sea ice loss. Looking at the sea ice thickness difference shows a similar story. So in the observations, an estimate of sea ice thickness comes from the ESMOS satellite, and this showed significant thinning all over the Barents, Kara, and West Laptep seas. This is shown in the panel in the top right. And again, showing the changes in thickness in the model in these 4 different nudge simulations. Overall, on average, doesn't show much change. It does show a few regions of either sea ice thickening or sea ice thinning, but it's mostly due to dynamic changes. You can see they're mostly kind of around the coastlines where you either blow in sea ice into the coastline or away from the coastline. And this is confirmed looking at the splitting the changes. Now we're focusing on the nudge simulation of 2021, but the other 3 case studies or the other 3 different mean states show similar results. So I'm just focusing on this one run from 2021. We're now splitting the total changes in sea ice concentration and sea ice thickness into the dynamic and thermodynamic component. Now, I have said that the changes in sea ice are quite small, but we want to see what's producing those changes in the model. And the bottom line, it's mostly the dynamics. So the panels on the left are the dynamic changes in sea ice concentration and sea ice thickness. And if you compare those 2 panels on the left with a panel on the far right, which is the total sum, those 2 look very similar to each other. The thermodynamics tend to, for sea ice concentration, they actually counteract the dynamic changes, which is kind of to be expected anyway. And then quite importantly, if you look at the bottom middle panel, this is the thermodynamic change in sea ice thickness. There's very little anywhere in the region. It's close to 0. So the model is not melting any sea ice thermodynamically in terms of the thickness, either from above or from below. Now, when we look at the ocean response in the nudge simulations, this shows a very different result to the Argo profiles. So now I'm showing temperature and salinity profiles. The temperature profiles are in the middle panels, the salinity profiles are in the right panels, and these are average over the grid cells shown in the left panel. So the top row is the sort of the sea ice edge area that had a little bit of dynamic sea ice loss, like retreat of the sea ice edge from the winds. The bottom is just kind of focusing where the same region as the Argo float, but there's not really any difference across the 2 regions. The bottom line is that these profiles do not change with the cyclone. They change very little. So if you look at the temperature profile, it's almost identical between before the cyclone and after the cyclone. So the ocean, the model ocean is hardly responding to this cyclone. So it's not mixing and it's not fluxing heat to the sea ice from below. At first I thought, or originally we thought, well, this might be because we don't have waves in sea ice in the model. But to try and pinpoint this, this again shows the directly the comparison in the temperature profiles between CSM and the Argo, and then the salinity on the right. And the stratification in this region is salinity driven. So for that purpose, maybe the panel on the right is very relevant. That we know CSM is too strongly stratified in this region. Compared to the Argo float. So finally, to try and get a bit more understanding of the differences between these sort of initial conditions or how the biases in stratification affected how the sea ice responded to the cyclone, this is work that was led by Sam Brenner, and we run a 1D ocean sea ice model called the General Ocean Turbulence Model coupled with the 3-layer Winton model. And what we did is we ran this simple 1D model, but once it was initialized with the Argo profile, the Argo temperature and salinity profile, and that's shown in the left column. And then we ran the same model, but initialized with the temperature and salinity profile from the CSM column, like before the cyclone. And the top panels show the amount of sea ice melt you get in each experiment. And we get, quite a bit of significant sea ice melt when we initialize the model with the Argo profile, and close to no melt, or no significant melt when we initialize with the CSM profile. The middle and bottom row show the temperature and salinity through time between the 21st and the 29th of January. And you can see evidence of mixing in the GOTM model, in the 1D model, when we initialize with the Argo profile, but not with the initialize with the CSM profile. Now this model is forced with the ERA 5 data, so they have the same atmospheric forcing. So the forced with the same kind of wind stresses, and so they're seeing the same cyclone overhead or above them, but there's very different ocean responses, which then leads to a very different CS response. And this is just sort of one last slide on these results, where we tested this simple model with very different turbulent mix and parameterizations, either shear-driven or surface wave-driven, the Langmuir turbulence, and these 6 different choices of parameterization. They don't give a massive sort of range of results. They basically, when you initialize with the Argo, you always have quite a bit of mixing of the ocean column. But if you initialize with the CSM initial conditions, you get hardly any mixing and very little melt. So this, this kind of really helped us understand that the bias in the sea ice loss it's probably not coming, or I don't think this whole waves in sea ice, which was my original sort of hypothesis, it's probably a second or third order sort of factor. It's mostly that it's just the ocean's very stabilized, very stratified in CSM, and we're not getting those fluxes from below. And this made me think, this is my last slide, this is very much a high frequency case study of one single storm, but it made me think, okay, would this have an implication for the low frequency, like long-term trends in sea ice loss, say in the Barents Kara in this region? And it made me think of this result from a couple of years. Letty Roach and myself, we wrote this paper where we did a very similar experiment. We nudged the model to the observed winds, but instead of just doing it over a month of January 2022, we did over the 40 years of ERA 5 or ERA interim at the time, between 79 and 2018. And one thing we noticed that even though the model, once you nudge the winds, you really simulate the loss of September sea ice really well. In the winter, you still had a pretty strong bias. So I just want to highlight the bottom left and the bottom right panel. These are the sea ice concentration trends in March. Bottom left is in the observations, and then the bottom right is in the nudge simulation, right? And we get a lot less sea ice loss in the Barents in the trend in the nudge simulation, even if it has the same trend in southerly winds as the observations by design, right? Because we've been nudging the winds in it. And so I think this is an open question. I wonder if the similar processes that even if it's in the right winds, maybe the loss in sea ice is too weak, because maybe the ocean is sort of like making kind of wanting to get the sea ice along because because this issue of the heat fluxes. But anyway, with that I will end, and thanks for your time.
Questions for Ed?
Hi, Ed. Sorry. I have 2 related questions. First, when you nudge your lens experiments, what do you do with waves? Is there wave watch in CSM? Second, how do you determine Langmuir circulation and Gordon if you don't have wave information, in the case you don't have wave information?
Thanks, very good questions. The first one, there's a wave watch is part of the model, and I believe we had it active in the nudge simulations, but in CSM1 and so far in CSM2, although there's a lot of development work, the waves, or the ocean waves, once they reach the sea ice, it's we don't simulate the wave sea ice interaction, so it's like they reach the coastline or like a wall, right? So there's no wave propagation into the sea ice in these CSM simulations. So we're missing any impact that the waves might have in observations. The model, those physics are not captured. And secondly, you asked me how we input that into the Langmuir. So we actually have waves and sea ice data from observations for this event from ISAT-2. So we had a transect, an ISAT-2 transect fly over this region, and we actually measure really high waves in sea ice penetrating into the ice pack really far. Because this strong cyclone, I didn't show the figures, but it's in the 2022 paper, there were 8-meter high waves in the ocean in the Barents, and because of the winds, a lot of them were traveling right into the ice pack. So we did see these really big waves with ISAT-2 actually penetrating the ice pack, which is one of the reasons why originally we thought, well, if they're helping you get all that sea ice loss, we don't have that physics in the model. Maybe that's the reason for the bias. But I think this new work has really shown how important the ocean stratification is.
Hi, Ed. Nice talk. So
if the model's too stratified in terms of the ocean, are sea ice variability in the Barents Seas probably also too low? Have you looked at that?
Yes, and it's the one slide I skipped because I knew we were running slow. And I won't share the screen again, the presentation again. But yes, so we actually looked into this in 2021. We looked at the high frequency variability of sea ice extent in observations and the models by different bandpass windows. So like less than 10 days, 10 to 20 days, 20 to 30 days. And we noticed that in the Arctic, of Arctic sea ice extent, all CIMIT models undersample observed variability at these weather timescales, like less than 10 days, also extending to 20 days. We weren't able at the time to look further into the mechanisms, but it seems that this recent result with one case study is sort of consistent with that more diagnostic analysis that that maybe even if the atmosphere has the right, say, storm track and the right sort of atmospheric force in that, if these biases are generic and not just in the Barents but sort of all around the sea ice edge, then you could end up having damped sea ice, high frequency sea ice variability, even with the right atmosphere, right? But I do know this, this issue about ocean stratification. There was a paper, I forget the name of the first author, but they looked at this throughout CIMIT, and other models showed biases in the opposite direction, where maybe the stratification is too weak. And in other regions, the biases seem to be going the other direction. So maybe in those regions, the model might have too high sea ice variability, but I definitely think, I hope it's helpful at least for me personally, it's really kind of sort of given me a new perspective, right? When I think about sea ice variability, and maybe as an atmospheric scientist, I've always been thinking about kind of the atmosphere, sea ice, but now I'm definitely going to be thinking a lot more about the ocean underneath and these sort of physics.
Thank you, Ed. Let's take a break. See you soon.
We start again at 3:30.
afternoon, everybody. My name is Ben Smith. I'm a project scientist here at Sorry. Oh yeah, no, I didn't just introduce myself. Rebecca. Okay, so anyway, yeah, I'm Ben Smith. I'm a project scientist here at the Econ Lab at NCAR. I'm going to be looking at some preliminary evaluation of CESM pharma with a couple of Asian Monsoon airborne field campaigns. I want to emphasize this is kind of preliminary and ongoing work that we're doing right now. Of course, helpful comments and insights. So I always like to start out by talking about why
We have some technical things.
So this is actually a 3D rendering from the NCAR musical model of carbon monoxide during the summer 2022 season. You can see actually the pronounced amount of CO in the boundary layer that's being wafted into the upper stratosphere with convection, sort of spiraling around in a large scale anticyclone at that level.
All right. Thank you. I think some wrong links had been sent out, so there was a little confusion.
This, I think, provides some context for why Asian Monsoon is worth studying to understand sort of how this boundary layer is redistributed.
Maya, you can go ahead and share.
Perfect, thank you.
All right, folks, welcome back. So our next speaker is Maya Willard-Steppen.
Hi, everyone. Thank you for your patience. I was in the wrong Zoom link. Yeah, I'm really grateful to be here. I'm going to be talking about something a little bit tangential from all of you, but Earth system modeling is near and dear to my heart. I come from a atmospheric and environmental physics background, and so recently I've transitioned into energy, and I'm kind of taking like an interdisciplinary perspective on it. And so I'm really excited to discuss with all of you. I'm currently in my first year of my master's at University of Victoria, studying under Canadian Research Chair Dr. Christina Hoyka, and my research is ongoing, and so I will not be presenting any final findings right now. But the title of my research is Energy Landscapes, Exploring the Spatiality of Clustering Renewable Energy for a Low Carbon Future. So as I'm sure I don't need to tell this working group, the global increase in energy demand is led to a rapid rise in CO2 emissions from particularly fossil fuels. And so transitioning to low carbon energy is very necessary in the coming years, especially considering the fact that a large majority of the world is still experiencing quite a bit of energy poverty. And so not only are we seeing an increase in demand in more developed nations, but we're also seeing, as different nations exit energy poverty, a large uptake in areas that didn't have previous energy demand, have energy demand. And so there's kind of like a two-tier problem to the energy expansion right now. We need to transition current fossil fuels, and we also need to increase renewable energy capacity in those areas exiting energy poverty and using more energy than before. There's a lot of really complicated interdisciplinary challenges with the energy transition, some of which are physical, including the amount of land required to produce energy. For example, so there's different energy resources require different power densities. And so you need significantly larger land to power the same system with solar than you would fossil fuels. And so this can create different competitions between land needs, such as agriculture, and solar panels is a very common challenge right now. Another more social aspect of the energy transition is known as carbon lock-in, which is a theory that explains the sets of institutions, networks, and social understandings that keep us in a carbon-centric system. This includes, different funding and subsidies for fossil fuel companies, current infrastructure, which can be very difficult to incorporate renewable energy into that's used to fossil fuel energy. And additionally, even just like current social norms, like frequent flying, status things like owning multiple private cars. And finally, what I'll be focusing on a little bit today is how customizable your energy system can be to the place that you need it to serve. And so when you're dealing with really different densities of populations and quite different environmental areas, the challenges are going to be really place-based and unique. So when you're discussing energy systems in Morocco versus the Arctic, the energy transition required there and the power balance and what the energy system is going to look like and how many people the energy system needs to serve when is going to be quite different. And so these systems that we come up with in design are going to have to become quite customizable based on place need. So fortunately, there's been a lot of innovation and creativity in the past few years around renewable energy, and it's increasingly involving the implementation of more small, flexible energy systems that can customize to different places. So the work that I do involves studying a phenomenon called energy clusters, which is a collection of smaller renewable energy systems using multiple types of technology in geographic proximity to another, functioning as one energy system. So an example can be solar panels, a backup biodiesel when there's not enough sun, and a battery system, or different windmills connected to a hydropower plant. The benefit of this is that any limitations of one technology can often be balanced by the benefits of another, and the type of land demand or environmental demand required for one is not so consuming for the energy system. You can serve more people without taking up quite a bit of land or requiring a certain environmental factor. So these really position this type of clustering as an ideal model for varying landscapes and community needs across the globe. The challenge right now is that most of energy clusters have been pretty extensively modeled through engineering, but there's very little verification of what's happening in practice, and especially when something is so socially embedded like energy and has economic implications, political implications, engineering models are not necessarily going to be sufficient to capture what's actually going to happen when these systems diffuse and how they're able to serve different communities' needs. And additionally, there's really not any scholarship on if and how these energy models of these renewable energy clusters are being customized to varying landscapes and needs. Because if we're looking at a low carbon future, we need to be able to serve all areas of the world, and that includes a really high variation of population density and environmental systems. So my research seeks to understand how and if clustering renewable energy technology creates the potential for customizable energy systems that facilitate this low carbon future that we're hoping for. SRECs is the acronym. It's Shared Renewable Energy Clusters. And so from my kind of Earth systems background, I like to look at what types of environments and landscapes that these renewable energy clusters are forming in. And if there are common factors between currently, we know they actually exist and they're actually serving people, operational renewable energy cluster projects. And if there are common factors, can they be encouraged in future potential projects to increase the success of these projects? In order to incorporate, the social, ecological, and biophysical and technological kind of lens that I'm going to be looking at, I'm taking, as I mentioned, an interdisciplinary approach, including land energy nexus literature, which is more of a sustainability-based literature, renewable energy and energy geography, as well as ecosystem service approaches. So the first step of my research was to review all pre-existing literature that determines different factors that can impact interactions between different energy systems and really permits or blocks the customizability of how and where these systems can succeed. And secondly, the Reset Co-Lab at University of Victoria under Dr. Hoika has been creating a very large database containing every documented case of a renewable energy cluster that we can find globally, in all walks of life, in all types of environments. And so from this kind of long data set, I'm constructing a geospatial database of clusters and combining this data with publicly available land and demographic geospatial information, as well as climate reanalysis information. The types of data and questions that I'm looking to answer through different testing is that what a range of different resource combinations does every single cluster need solar panels, for example? Is there always storage, or are people finding creative ways to do load balancing between different types of storage? Is there a resource or required actor for clusters to function currently? What kind of environments do they exist in? Is there a limitation to this? Do they exist, not far north or not far in inland? Is there like a water requirement? And are there flexibility measures required? Do we need to see things like load balancing or smart grids to be able to succeed in these projects? And finally, are there different actors? We're including information about who's involved in these projects, whether that's government, a co-op of farmers who decide to purchase a bunch of windmills together, or federal funding. And are these clusters being formed in places that have competition potential with different other necessary environmental resources such as agriculture or clean water? So an example that we study includes the Colville Lake cluster, just to get a sense of what, how varied these systems can look at. But this is a 200 resident community in the Northwest Territories of Canada. And before installation of this cluster, relied exclusively on diesel generators, which, as I'm sure several of you know, are extremely expensive and not necessarily reliable if you can't get sufficient power. And so there were large challenges with power outages before installing this system. And so the local government, community members, and federal government created, through funding from the federal government, created this energy cluster, which includes these 2 solar arrays, which you can see an example of on the left here, 3 batteries, and a diesel generator. And so what this really allows for is during the summer months when there's significantly higher sunlight, the diesel generator is not necessary. And in the fall months, the battery combined with the solar can really be beneficial for not still decreasing the amount of diesel. But when the temperatures drop down and batteries are no longer going to be very efficient at those lower temperatures, and obviously there's not going to be enough sunlight to produce, then the diesel generator can be relied on. And so this is a really good example to me because it shows that, the system isn't perfect in terms of renewable energy, but it significantly reduces the annual power outages. So for the first year that it was installed, the power outages went from 51 the previous year to only 10 the following year. It's significantly more affordable for the community and has also really increased the reliability of this type of technology and decreased the carbon emissions of this community. And so, the way that these are showing up are all, we're trying to see how unique can they get? How can these be customized to different needs? Because the needs of a city such as Barcelona is going to be quite different from Colville Lake. And so that's what we're currently working on understanding. So right now, the challenges that we're working through is that we've been using convenience sampling because the population of total clusters in existence around the world is unknown. And so in order to understand what the typical biases is from our data sources, I've been conducting multi-source cross-comparison within different sources gathered from the data. So these are typically NGO databases, government, peer-reviewed articles, and then private sector reports, financial reports and such. And so doing different cross-comparison to understand if the results are statistically different between the two, to understand where our information is coming from and what's being prioritized. The database has been converted into a GeoJSON file, and I'm currently working through Google Earth Engine via a Python API to combine with the external climate reanalysis and landscape type datasets, and conducting regression analysis between actor energy type and external environmental factors as the independent variables to understand different patterns that are arising. Thank you.
For Maya. I have a question, Maya. Thank you for talking about this. So the example you gave was in the Northwest Territories, which you said is really remote. Have you found that there are more clusters
so far I know it's preliminary, but have you found there are more of these clusters in like remote Arctic communities compared to, say, more urban parts of Canada?
Yeah, so I would say I wouldn't necessarily say more Arctic than other rural, but certainly one of the benefits of these clusters is that they operate successfully without the reliance of a grid, which can be really expensive and complicated to put in, especially in areas that have difficult terrain. And so Arctic communities are especially challenging, especially when discussing renewable energy transition, because there just isn't the type of technology that we rely on is just not consistent throughout the year because you're dealing with extreme weather variations. And it's one of the considerations, especially with climate change, is that a lot of places will be dealing with other types of extreme weather. And we have to create systems that can use multiple types of energy rather than always relying on storage, because batteries are their own challenge. And so, yes, we have seen like a significant number of the clusters are in rural or remote areas. And so those that are in Canada typically have been found in the north. We found very few. I think there's a couple in like central British Columbia and a few in Ontario, like southern Ontario, that use solar and then have a grid connection. And so rely on like nuclear basically in Ontario as a backup. But like they're predominantly in the United States and Canada in northern areas.
Great, thank you so much.
Thank you, Maya. Moving to our next speaker, Courtney Payne.
Hi, thank you so much. Can everyone hear me okay?
Yes, we can see your slides.
Okay, great. Yeah, so I'd like to start off by thanking my collaborators, Nikki Lewandowski, Marika Holland, Kristen Crumhart, and Alice DeVivier. So as many of us are aware, the Arctic is a place where we can see really large phytoplankton blooms. This is a true color or ocean color image from just off the coast of Norway. We can see a big phytoplankton bloom generated here. And this phytoplankton net primary production is really important to supporting a diverse and dynamic food web. So we can see phytoplankton here, and they indirectly go on to support cod, which is a commercially viable fish species, as well as humans who, of course, are reliant on the marine organisms that live in this region for a lot of their food sovereignty, as well as for cultural practices. And when we look forward to future climate change in this region, there's an expectation that Arctic fisheries will see some really big expansion in the Arctic shelves. This is a plot of net primary production from 2010 to 2012, and it shows that in regions that are currently just outside of the Arctic in the sub-polar regions, that there's really a tremendous amount of net primary production on average generated there. And these are currently the places where Arctic fisheries, sub-Arctic fisheries are really large. But in the future, we anticipate that net primary production is going to increase largely in the Arctic shelf regions, and that's going to lead to likely the expansion of big fisheries on the Arctic shelves. And going forward, as we try to manage, as fisheries managers, probably not me, I hope not, are anticipated to have to manage fisheries in these difficult regions. They're going to need a lot more information than we have at present about the future, the near future of each of these regions. And so one potential way that fisheries might be managed effectively is by predicting on a short-term basis primary production and changes in primary production year in and year out that could influence how much food should be safely harvested from the region in years to come. So I and my collaborators are really interested to assess if Arctic net primary production is predictable, and also how that predictability might change in the near future as sea ice continues to be lost from the region, as well as what regions are the most predictable and what physical drivers control predictability in the region. And in order to answer these questions, we used the CESM2 large ensemble, as well as 2-year perfect model forecast simulations. And similar to the large ensemble, these were initialized with microperturbations in atmospheric temperature. And they were initialized every other month, so January, March, May, in both 2010 and 2012. And we evaluated the predictability of NPP using potential prognostic predictability, or PPP, which is a metric that relies on just two variables. The variability of perfect model experiments. Here I show the standard deviation of kind of an example perfect model experiment. And also the variability of the climatology, which is provided by the large ensemble. And you can imagine that close to the initialization of each of these simulations, the variability of perfect model experiments is really small. And so this PPP value is close to 1, and we have a high degree of predictability. But as time goes on and the spread of variance in a variable, like net primary production, increases, that we'll start to see the variance in perfect model experiments and climatology be very close to one another, at which point PPP is 0 and we don't really have any predictive ability. So using this metric, we analyze predictability on a pan-Arctic scale, which we defined as being greater than 50 degrees north, to include those kind of subarctic seas that are so important for fisheries right now. And also we looked at predictability on Arctic shelves, which we defined as being north of 66.5 degrees north and shallower than 1,000 meters deep. And we did this for both the 2010s and for the 2030s. And now I'll show you some results for the kind of pan-Arctic portion of this work. So I've got PPP. I'm going to show PPP plotted here from January of 2010 to October of 2012. And you'll see that I've kind of got a gradient in the background of this figure. Not shocking to probably most people in this room, net primary production is really seasonal in the Arctic. We get a lot of production in like the month of May on a pan-Arctic basis, but very little in December and January. And so I want you to focus on the lighter colored sections of this plot, because that's where predictability matters. It doesn't really matter if we're really good at predicting the complete lack of production that's happening in December. I also I've also got this dashed line here, which represents the statistical significance line, which is at 0.2344. And so values above that statistical significance line, we consider predictable, and values below that, we consider not predictable. So when we look at the 6 different initializations for 2010, all these different colors here. If you look at any given one, you'll notice that it starts off with a really high PPP value because variance is low, and then that declines. And then we see kind of an emergence of like a sawtooth shape where PPP gradually rises through the summer and fall months, peaking in November or October, and then declines really rapidly in the winter. And this kind of shape continues through the 2 years that we've run these simulations. And if we focus in on those predictable months, we kind of see that MPP is a little bit predictable in the summer months, but not incredibly, maybe not as much as we'd hope. When we look forward to the 2030s, we maybe start to see the same sort of thing, that sawtooth shape again. And it maybe at first glance appears to have a very similar degree of predictability in the summer months. But when we actually look across each initialization, at the most productive months, so just May through July of each of the 2 years that it's run, we see that in the 2010s, on average, each simulation has only 2.8 predictable months. But in the 2030s, we actually see 3.7 predictable months per initialization, which actually indicates that there's a significant increase in the number of predictable months we get in the 2030s relative to the 2010s. And that maybe is best highlighted with looking at the summers of 2011 and 2031 here. So you can see that in the summer of 2010, May and June have only one initialization month where we have predictable values. But in July, a number of other simulation months are also predictable. However, in the 2030s, we can see that quite a few simulation months are predictable in May and June, and all of the initialization months are predictable in July. So overall, this demonstrates to us that NPP is likely to be more predictable in the 2030s than the 2010s. I also wanted to look at Arctic shelves, this region where we know that fisheries are going to expand in the near future. And not surprisingly, perhaps, the Arctic shelves have an even tighter kind of seasonality than did the Arctic as a whole. They're quite productive in June and July, but really have very low productivity in other months of the year. So we're going to, again, focus in on June and July exclusively. And when we look at predictability for June and July, we actually see that it looks pretty good. For example, if we focus in on this summer of 2011 and 2031, we see that almost all months in both of these periods are predictable. So this demonstrates to us that the Arctic shelves can remain really highly predictable for at least 2 years, which maybe could be helpful information for fisheries management. We were also curious about what drives that predictability. So phytoplankton growth is controlled by 3 variables: by light, temperature, and also the availability of nutrients. And so we looked at the limitation terms for light, temperature, and nitrogen, which is the most limiting nutrient, on a pan-Arctic basis. And we found that in those most productive summer months, that temperature is the most limiting kind of driver, and thus it controls phytoplankton growth the most importantly during those productive months. We also wanted to look at predictability. And when we compare light, temperature, and nitrogen, they all start off relatively predictable, but light and nitrogen limitation terms really lose their predictability by the end of the first year of the simulations, while temperature remains predictable over 2 years of these forecasts. So overall, this work shows us that phytoplankton net primary production in the Arctic Ocean is likely predictable for at least 2 years, and that's due largely to high predictability on Arctic shelves. We also found that ocean temperatures, the most important limit on phytoplankton growth during the productive summer months, drive much of this predictability, and that NPP may become more predictable in the future as more sea ice is lost. So I think this maybe demonstrates that predictions of NPP for a shortish term basis could be usable for management of Arctic resources in the future. Thank you so much.
Questions for Courtney?
Yeah, really interesting. I was wondering, you looked at it like over all the shelf seas. Did you look at it all spatially? Are they all equally predictable, or do you see like hotspots of predictability?
Yeah, so we looked at it by large marine ecosystem, which is particularly useful for fisheries managers. The Chukchi and Barents Seas were not particularly predictable. That's a real shame because that's maybe what American managers would most like to kind of predict. But a lot of the Russian shelves were pretty predictable, and the Beaufort Sea was also relatively predictable. In the Canadian Arctic, I think Baffin Bay was reasonably predictable as well, but I can't fully recall. But we have generated the results by LME, so we could look into that more.
Thanks for that talk. I'm curious if you've looked at how well your ensembles can track the particular member of the large ensemble that you initialized from, because of course, for prediction to be useful, you want to track the actual state of the Earth system, not just reduce the uncertainty relative to sort of a hypothetical spread of, internal variability that we can get from a large ensemble. You actually want to be able to predict the trajectory that you're on. So it might be worth, looking at how long you can track with each of your different initializations the member that you started from.
Yeah, that's a really great point and not something we had previously considered, but I think it would be really valuable to add to the analysis. Thank you for the suggestion.
Thanks, Courtney.
Thanks.
Our next speaker is Marika Holland.
All right. Hopefully I can figure out how to use this. Is there a pointer? Never mind. Okay, okay. Good afternoon, everyone. So I'm going to be following on this theme of predictability that Courtney just spoke on. I'm actually going to be using the same simulations that she talked about, but I'm going to be talking about multi-year predictability of the anaerotic sea ice and implications for ecosystems. So, all right. So anaerotic sea ice. So this shows on the left, you can see the simulation of anaerotic sea ice annual cycle in the CESM1 and CESM2. And then there's observations on there as well. So this is from a paper that Hansi Singh, sitting over there, wrote several years ago analyzing the CESM2 runs. And you can see that we get a pretty good annual cycle of anaerotic sea ice. What's shown on the right on the maps is the observed sea ice in 2023 in February, so the seasonal minimum on the top, and in September, the seasonal maximum on the bottom. And so you can see that there's an enormous annual cycle in anaerotic sea ice. And what this means for prediction is that where the sea ice anomalies are changes dramatically by season. And so you have to think about this when you're trying to understand what the predictability is in anaerotic sea ice and the mechanisms that can drive it. So I'm showing here on the top, that's the observed variations in the February sea ice area, and September is shown on the bottom. So we have a lot of variability in the sea ice. We'd like to be able to predict this variability. The maps on the right show where the anomalies are in sea ice that lead to that total hemispheric sea ice area. So you can see in February, the anomalies are really close to the continent. So if you're trying to think about processes driving variability in sea ice or predictability in that month, you really need to think about what's happening close to the continent, whereas in September, the ice anomalies are all at the ice margin. And so this regionality is important in terms of thinking of mechanisms. So this is I'll come back to this in the analysis of our simulations. So observations do suggest that there should be predictability on seasonal and longer timescales. This is some work that Laura and I were involved in several years ago, looking at just the anomaly, the correlations of sea ice from observations to the Amundsen sea low. And so you can just see the lagged correlations shown on the upper panel, suggesting that you should have persistence in sea ice anomalies, and that should give you some predictability. Model studies have also suggested predictability in anaerotic sea ice. So what we're going to be exploring here is mechanisms that drive predictability, and also the regionality of predictable signals in the anaerotic sea ice, and then impacts on ecosystems as well. And I have to do this in like 8 minutes, so we'll see how this goes. So I'm going to be using the same simulations that Courtney was analyzing. So these are perfect model, initialized predictions. Courtney did a great job of introducing them, so I'm not going to go through this in much detail. I'm only looking at the 2010 simulations that we've performed. Okay, so this shows the predictability. This is the anomaly correlation coefficient of the hemispheric total sea ice area in these simulations. And so this is shown over the 2 years of these integrations. And you can see the different initialization timings when those lines start. That's when they were initialized. So for all the initialization timings, there's some common features in this anomaly correlation coefficient plot for sea ice area. You see that they all have high predictability for the first several months, maybe first month, but then they all lose predictability pretty dramatically during the ice retreat season as ice is melting back to the continent. That predictability then reemerges during the ice advance season, and you have high predictability through the winter. And those things happen regardless of the initialization timing, and they happen over this 2-year timescale. So that was the total hemispheric sea ice area. So now we're going to look at the predictability of sea ice, but regionally. So you can see the continental outline at the bottom of the plot. So this is the ACC of the sea ice area, but now shown as a function of longitude. And upward on the y-axis is over the 2 years of our simulations. I'm only showing the September initialization runs here, but you see similar features in the other runs. So this loss and reemergence of predictability is evident here. You can see that we have minimal predictability over the summer months, January through May, and then you have this reemergence of predictability in the fall and winter. And again, that happens over the 2-year timescale. But you also see that it's very regional. So the predictability is really dominated by what's happening in the Bellingshausen and Amundsen Sea, and a little bit of the Ross Sea as well. So the color contours here are actually the sea ice, ACC. The lined contours are the ACC for sea surface temperatures along the sea ice edge. So you can see that those are very closely aligned, suggesting that sea surface temperatures is providing the predictability to the sea ice. So if we instead look at sea surface temperatures along the winter sea ice edge, so the plot on the left is with evolving sea surface temperature anomalies in terms of space, right at the ice edge. The right is the sea surface temperatures, but now along the winter ice edge. You see that this loss and reemergence signal is much reduced. And instead, you have sort of consistent predictability happening through the 2 years of the simulations. There's a small kind of loss in the summer, but overall we have predictable sea surface temperatures along the winter ice edge in the Bellingshausen and Amundsen Sea region. Okay, so what's going on here? So I'm going to walk you through the mechanism and why you have this regional dependence and seasonal dependence in the predictability of sea ice. So what I'm showing here is the September sea ice edge, the black line around the Antarctic continent. And then the green areas are where sea surface temperatures are highly correlated with sea ice conditions in different regions. So the lower area is where sea surface temperatures in September are highly correlated with Ross sea ice area, and the upper is where they're highly correlated with Weddell sea ice area. So this is what the September conditions look like. This is actually, those green shaded regions are taken from the CESM2 large ensemble, where the correlation coefficient is above 0.4. Okay, so then we march 6 months into the future. The ice has melted back to the continent. You can see the March ice edge shown on the plot there. And those sea surface temperatures are still highly correlated to the sea ice conditions 6 months prior, but they've now been advected eastward. So those green blobs are still present. That's where you still have high correlations at this 6 month lag. But they've been advected eastward, and the sea ice has melted back to a location where it's not being influenced by those sea surface temperatures any longer. So you've lost predictability in the summer sea ice, but those ocean temperature anomalies are still out equatorward of the ice edge and still remain predictable. If you march 6 months further into the future, so now this would be a year from our initial state, sea surface temperature anomalies are still highly correlated, still predictable. You can see that they have shifted from their original location. The sea ice edge has advanced equatorward, re-encountered those sea surface temperature anomalies, providing predictability. But you can see that where it's re-encountered sea surface temperature anomalies differs. So in the case of those anomalies that originated in the Ross Sea, those have remained close to the sea ice edge, and they provide predictability downstream in the Bellingshausen-Amundsen Sea. But the anomalies that originated in the Weddell Sea region have advected out of the sea ice zone. So those anomalies in sea surface temperature are still there, but the sea ice doesn't encounter them because it doesn't advance far enough north. So you've lost predictability in sea ice in that region. Okay, so that's the mechanism that gives this predictability and the regionality of it. So what are the implications for biology? I'm probably running out of time, so I'll go through this quickly. This is, again, this plot of ACC now of the net primary productivity as a function of longitude and lag. And so we do have predictability in NPP in this Bellingshausen Edmondson Sea region. You can see a lot of that is actually in winter when there's really very little NPP, so we don't really care about it. But we do have predictable conditions in December. So that is a region, that is a time of high NPP. And so basically we can look at the mechanisms that give rise to that predictability, and we see that it is associated with sea ice predictability, providing predictability to the light availability for that NPP, and then giving us a predictable signal in the net primary productivity. The iron limitation, nutrient limitation, actually responds to and doesn't drive the NPP predictability. So if you have higher NPP, you actually get more limiting nutrients, but it's a response, not a driver. So it's really driven by light availability. Okay, so to summarize, winter Antarctic sea ice is predictable on multi-year timescales, but this varies regionally. And the predictability arises from these long-lived ocean temperature anomalies that are advected with the mean ocean circulation and impart predictability downstream. So the location of where predictability is present in the sea ice is related to where those sea surface temperatures are relative to the sea ice edge. And this can impart predictability to the marine ecosystem. So thank you, and I'm not sure if we have time for questions, but thanks.
Rika, how about one question?
Thanks, Marika. Really fun to think about predicting it. I'm just wondering, with the recent really low Antarctic sea ice, if you rerun your predictions, are you thinking of doing that? Because there's this suggestion the winter, it's not coming back like it used to, and so you don't get that skill anymore.
Yeah, I mean, these are all perfect model experiments, and so, but I think there is this, you know, the ocean heat content does give us a predictable factor. So, and Ed Blanchard Wigglesworth, who spoke earlier, he's done some nice work actually predicting what happened last winter, and he actually gets some good predictions that are associated with ocean heat content about 9 months prior. So, yes, so you should also talk to Ed.
Thank you, Marika. So our last speaker is Laura Landrum and Rachel McCrary. Is Rachel going to be also? Oh, okay, just Laura.
She just helped a lot with this. And then how do I advance the slide when I need to? This guy, right? Okay. Okay. So thanks for coming today. This talk is going to be a little bit different. It's not a lot of science results per se. It's meant to stimulate.
Please speak into the podium microphone.
There we go. It's meant to, so this is going to be a little bit different. It's meant to stimulate conversations about what can we do as climate scientists to facilitate using our climate models to help communities who are navigating times of extreme climate change. A lot of this came out from talks with Rachel McCrary. I carpool with her from Fort Collins. And Rachel is an atmospheric scientist that does a lot of work with communities related to drought. And drought is rather subjective in how you define it. And anyways, so first off, this also came about thinking about extremes. And we talk often in the climate community, when we talk about extremes, we're referring to statistical or geophysical extremes, such as hurricanes, weather-related events. Sometimes we get into droughts. But human beings can experience climate not only from experiencing extremes, but also from chronic exposure to changing conditions or to extremes that are superimposed or compounded by changing conditions. They can also experience it, such as like studies have shown that people that experience several hurricanes are much more likely to move in their lifetime. And likewise, people can also experience climate change, and their extreme conditions might not be as easily defined by geophysical statistics, but they're still extreme. For example, sea levels rising compounds coastal erosion in the event, and storm surges and things like that. So basically all of this is around how can we maybe reframe or think about what we do as climate modeling scientists to help better serve communities. Really briefly, my background in this, this is work focusing on the Arctic, and this has come from a couple different projects that I've been involved with, both from the National Science Foundation. One is SEARCH, the study of environmental Arctic change, and the other was our Navigating the New Arctic program. And in both of those, we were looking to co-produce knowledge about how communities are navigating times of extreme change with Indigenous knowledge holders, Western scientists, and policymakers. So I'm going to go through 4 things briefly because I don't have a whole lot of time. But first, I'm going to set the stage in Beringia, the ecology and history of the Beringia area. Then I'm going to give some examples in 3 different areas. 1, extreme changes and subsistence harvest. 2, extreme and even non-extreme events that are compounded by extreme changes, namely coastal erosions and typhoons. 3rd, the possibility of cascades and tipping points, in particular with hazardous algal blooms. And then I'm going to talk a little bit about some other disciplines that are looking at climate risk and some definitions looking at climate indices and metrics from outside my discipline. So first of all, Beringia is a land right where Russia and the United States come quite close together. That area in the land that is closest is the Bering Strait. People have lived there for thousands of years. We think the first migration of humans to this area came about 16 to 20,000 years ago. They've been living there continuously for 14 to 16,000 years. There are many cultural and linguistic similarities between the indigenous communities in Russia as well as Alaska. This area is very shallow. So most of it's continental shelf, and the red area contours in here show areas of 100 meters or less in depth. The blue areas are deeper. There's a net inflow of water currently, water from the North Pacific into the Arctic. It tends to be relatively warm and nutrient rich. This region is an area of massive migrations, both on land and in the sea. And essentially, I think of the Arctic as the changes in the Arctic are primarily winter to summer. In the tropics, that's diurnal changes, day to night. Mid-latitude, it's seasonal. But in the Arctic, you have 24 hours a day of sunlight in the summer and 24 hours a day of dark in the winter. Massive migrations of animals and chasing energy, chasing sun, chasing the sea ice. So you have migration of marine animals, whales, seals, walruses, fish, and on land, caribou, birds. The region for these Alaskan communities, it's very isolated and rural. If you have any goods or services, they're available only by plane or boat. You can't drive to Ukhiavik, you can't drive to Nome, and you can't get a boat there in the winter. Most of the food is traditional, and I don't remember the exact percentages, but most of the indigenous communities are eating traditional foods, harvesting foods for their livelihood. It's also a very important part of their culture and their history. They do supplement food with grocery stores, but it's extremely expensive. As an example, a couple months ago, I was in Kotzebue, which is a relatively large community of 3,000 people. They get 2 planes a day, and I bought some instant oatmeal to have in my hotel room for breakfast, and the regular box, I think it's 6 packages, was $11. The fruit, if you get fruit and vegetables, it tends to be that transports really easily, apples, oranges, citrus. Most harvesting occurs using modern technology such as boats, snow machines, ATVs. Those require fuel. Fuel is extremely expensive. And so the communities there are bridging this economic difference, if you will, between a subsistence style living based on gathering of food and resources, sharing it, cultural traditions that have been around for thousands of years, with some participation in the wage economy, which they need in order to buy fuel for their boats or to buy some of their supplies, as well as to heat their homes. Larger communities that are wealthy have running water, but many communities do not. Ukhiavik, for example, is a community of about 5,000 people. In the 1980s, they got an underground sewer and water system. It's 3.2 miles, I believe, of underground pipes in the permafrost. It cost $800 million. That community had that money because of North Slope oil. It's the wealthiest borough in Alaska. Alaska has 229 federally recognized tribes. It's very complicated as far as governance goes. Food preservation and storage is also critical for survival. Many of these communities, Ukqiavik and St. Lawrence Island, they often rely on getting a whale. You can't put a whale in your refrigerator. You can't put it in your freezer. You can't even put it in everybody's refrigerator, provided everybody has a refrigerator and power to power the refrigerator. So food preservation systems often consist of underground ice cellars. Those ice cellars are in permafrost in many places. Some places are kept cold just by the permafrost. Other places they add snow in the winter to help keep the temperatures down. And in other places like St. Lawrence Island, they often harvest sea ice to put in the cellars to keep them cold. Traditionally, many communities have thought that you need a year's supply of food in order to make it through a hard time. They are now beginning to think you need 2 years' supply. Many of these cellars are failing right now because they might have a rain on snow event in the middle of the winter and the cellar freezes, or the running water gets full of running water and it freezes and the food spoils, or the permafrost is not staying cold enough, or the ice is not close enough to harvest ice, or they don't get enough snow. So they're facing a lot of compounded challenges due to climate change. So the examples I'm going to give are, the first one is going to be of extreme changes. And that we see these happening in subsistence harvest. I'm going to use walrus for St. Lawrence Island, bearded seals from Kotzebue. Second one will be extreme changes that are happening and being extreme events that are being compounded by extreme changes, namely coastal erosion in this case. And third, I'm going to talk about possible tipping points and cascades. Walrus in the Bering Strait area is it's a primary source of culture, history, food, living for about 19 communities in Alaska and 18 in the Russian Far East. They've harvested walrus for going on about 1,000 years. The accessibility to walrus is changing. Walrus migrate from the south to the north, chasing that sea ice edge. And the changing sea ice conditions are changing the ecology of the walrus as well as accessibility to it for hunters. These examples are coming from St. Lawrence Island, the villages of Gamble and Savunga, which are highlighted by that square on that. St. Lawrence Island is actually a little bit closer to Russia than the United States, still part of the United States. I don't see the thing. This was supposed to be a nice video showing the sea ice conditions in February from the Sea Ice Atlas for walrus, or from Walsh. And on the right-hand side is a plot showing sea ice concentration near St. Lawrence Island. And the first 1850 to 2015, where that black line across is taken from the Walsh extended data set. So it's from observations on ships and then sea ice concentrations from satellites starting in 1979. Essentially, the lighter the color, the more sea ice. The darker the color, the less sea ice. The months of the year are shown across the bottom. In the 1850s, the area around St. Lawrence Island had typically 8 or 9 months a year of sea ice, concentrations above 20 to 30%. In 2020, typically they are seeing closer to 4 to 5 months. It's a dramatic change in a relatively short amount of time. Now, Pacific walrus, they can't swim indefinitely. They have to come up. They have to haul out on ice or land to take a break. They also birth their pups and nurse them, and sea ice serves essentially as daycare for pups, for the moms. Walrus are benthic feeders. They feed off the bottom. They can go up to about 80 meters in depth. They really like to go about 10 to 50 meters in depth. They use their tusks to churn up the sediment and get primarily clams, but other invertebrates. So if you can imagine if that sea ice edge retreats so far that it's no longer near the continental shelf, the walrus cannot eat, and they can't follow the sea ice. They can haul out on land. Hauling out on land is not as, it's risky for a walrus because they can panic, and if you've ever seen movies of walrus, they can't run very fast. I mean, they probably could compared to me, but they panic, and they often trample each other, and they can kill each other on the land, whereas the sea ice, and it's spread out, they prefer sea ice. Harvesting walrus at St. Lawrence Island depends on sea ice conditions, where the walrus are, and weather conditions. Most of the walrus hunt from Gamble Island occurs when sea ice is between 0 and 30% right next to the island, but they have to be able to not only get their boats in the water, they have to have clear water near the land, but they have to have walrus close enough that they don't risk not coming back. And the ice there has to be a high enough concentration for the walrus to haul out. Likewise, if it's too cold, usually if it gets really cold and a really calm day, no winds, that surface water is so cold and the air above it is also cold that it refreezes pretty quickly and their boats get stuck. So they like a little bit of wind, but not too much. Over about 9 or 10 meters per second, it's too windy even for the walrus to want to get on the ice. They just stay in the water. So those days have been decreasing for them. The other example I have is from bearded seals in the Kotzebue area. Bearded seals also rest on ice. There are 4 events in Kotzebue. That map shows Kotzebue. That Kotzebue Sound area is about the size of the state of Iowa. And Kotzebue, and there's a hunter on the below, there are 4 ice events that signal the start and end of the bearded seal hunting season. The first is when kilometer-size leads open up in Kotzebue Sound and seals can access it. It's a resting and feeding point on their migration north. The second big event is when ice opens up and clears water about 600 meters in front of the town, and then people can get their boats in the water. I only have 2 minutes? You've got to be kidding me. Okay, we're going to go through this really fast. Yeah, really quickly. This is showing sea ice conditions in May, June, and July. Basically, the Ugruk hunting season has decreased by 1 month in the last 20 years. It's a little bit over a day a year that the season with which they can hunt Ugruk is happening over the past 20 years. Coastal erosion. Coastal erosion rates in northern Alaska are some of the highest in the world. Those red areas on the North Slope are where the shoreline is decreasing at about 5 to 20 meters per year. They're huge. Part of this is because sea ice is retreating, and sea ice serves as a mangrove swamp. It serves as a seawall. It serves as road. It serves as refrigerator. And in coastal areas, it helps diminish the energy that the waves carry to the shore. And as you reduce the sea ice cover, you have a longer fetch, and a storm can get more energy in the waves and destroy more coast. This is a picture of Shishmarif that was right after Typhoon Merbak, which was in 2017 or 22, excuse me. It was the strongest Bering Sea storm in September in 17 years. 90-mile-an-hour winds, 50-foot seas, 1,300 miles of coastline was damaged by that. That's 1,300 miles of Alaska that only has 4 water height stations that operate year-round. So you can imagine some of the challenges with being able to predict sea level, storm surge, tidal surge in a region like this. Okay, I'm going to go quickly. That Bering Sea, Chukchi Sea area is also what we consider kind of a climate hotspot. We anticipate in the next 10 to 80 years, we're going to see an increase in the number of storms reaching up there, a decrease in sea ice, number of ice-free days. It's going to be a lot of changes. Harmful algal blooms. Sorry, I did not. I just want to say that the Chukchi Sea is, recently they've discovered a cyst, Alexandrium cyst. Alexandrium is an algae that causes, that does have massive toxic algal blooms, and it's toxic. It accumulates in shellfish and on up for shellfish eaters. There's a massive cyst bed. It's the highest in area as well as density in the Chukchi, I believe, of anywhere in the world. Those cysts can survive up to 100 years. There's this question of when the temperatures get warm enough, are we going to see extreme blooms there? And communities that depend on benthic feeders such as walrus and seals in order to survive, and they don't have facilities to measure algal blooms within the tissues. Anyways, I think I'm at an end, so I'm going to put all these up here. There we go. There are ideas from insurance companies as well as people who work with drought to look at climate in terms of climate risk and to measure a risk as a probability of a hazard happening in an environment times the magnitude of the consequences. And I would like to suggest that the CESM and climate models have the potential to be really powerful tools to look at the hazard and the exposure. So hazards can be an extreme event like a hurricane, a shock, something you can recover for immediately. They can also be a stressor, a slower onset. And climate models do a good job of measuring the statistics of changes in some of these areas. And likewise, the exposure, the likelihood that some of these events and communities will be exposed to this. And I think I'm over. So sorry that took so long. But I just wanted to say thank you. Thanks for coming. And thanks, many of you have had lots of great discussions with me. And thank you. I look forward to more.
So I think we're at time for the big plenary discussion. Oh, well, I guess we could just keep this room. We could hold this room hostage, guys. Okay, I don't hear people like right at the door, so if there's questions for Laura, we can maybe take one or two.
Thank you, that was cool. I would be curious about how collaborative research and communication works in that area where basically Russia and the United States could or should for the best work together.
There's tremendous challenges like that. The Alexandrium cysts, we don't know how far that bed goes over because we can't measure it, can't report it, and don't know. And yes, that region, it's all continental shelf. Russia and the United States are quite close, and there's also great concerns given the political environment of the past couple of years. So for example, the port of Nome has recently been received a large chunk of money to make a bigger port so that they can house some bigger ships and a Coast Guard and have some response. That it does hinder communication. I would also say that communication is challenging between Western scientists, community members, and policymakers. We all speak somewhat different languages and somewhat different backgrounds, and like Maddie had a great slide up about sea ice, and sea ice processes that we think about from climate models, where we deconstruct sea ice into its different components, and melt ponds, basal melt, surface melt, precipitation, and then we attach mathematical equations to these, and that's how we think about sea ice. Community members don't think about sea ice that way. They think about it as a church, refrigeration system, access, food, and even just trying to find, I wouldn't say common ground, but a way of communicating and understanding one another is challenging in addition to the geopolitical challenges, which are significant.
Hi, Laura. Kind of an overwhelming topic, I would say. I'm a little depressed now, but happy to share that with you. Okay, so I have a question related to permafrost and this community, thinking about water resources in terms of thawing of permafrost and how the different materials in the soils could enter the water systems. Because I'm thinking about it from a point of view of aerosol, of course, where it can be a source of nutrients to the ocean, but also it could impact water quality. So I'm just curious if anybody's thinking about that in terms of the water streams and, the watershed part of it.
Okay, I'll just say that's not my background, so I don't know a lot about that, but there is tremendous concern. So the example I gave of Ukjavik that has an underground sewer and water system, that because the permafrost is thawing, they're having a lot of challenges with that. And just recently they approved a pilot study that they're going to do with 27 households for an above ground system. It's going to cost $5 million for 27 households as a pilot study. There's tremendous concerns about water quality, even in communities that do not, particularly in communities that do not have a system to process or clean the water that might be downstream from, say, the Red Dog mine, for example. They can't trust their water to drink, so they get it all imported in plastic water bottles. That was kind of a sidetrack to that, but that's, sorry.
Great, thank you, Laura. So just to wrap up the session, just like two teeny announcements. First of all, we have a Slack group. So if you're not a part of that Slack group yet, please join the Slack group because it's very exciting, let me tell you. I wish it was a little more loud. So if you're loud, especially, please join the Slack group and like make it exciting. The second thing I want to say is, we have a new computing proposal coming up very, very, very soon. And so we will make an announcement on the Slack group, and we will make an announcement on the email listserv. And if you have needs for computing time, please let us know, because we will literally just give you computing time for awesome science, because we love you all and we want to support you. Okay? Awesome. Thank you all so much. Bye.
Check, check.
Like this is when you need some good dad jokes, right? To it's not my strength. All right, let's get started with this wrap up. We all good? Okay, great. All right, so mainly this is going to be question and answer, but just want to do a few thanks before we get into that. So again, we did some thanking at the beginning, but after now having experienced the week and seeing how well it goes, I wanted to thank again the multimedia team. It is a challenging thing to manage the changing rooms and the technology and the technology that we've had to sort of adapt as we move into this hybrid world. So thanks to the multimedia team, Event Services for the food, and also especially to the CGD administrative team, Daniel, Elizabeth, Kayla, and Teresa. They've been around all week and helping everybody out and making everybody feel really welcome, I hope, to do that. So can we give a round of applause to And it's been really fun to have a good crowd back here for a CSM workshop. We had a pretty good crowd last year, and I think we were a bit bigger this year, coming back from post-COVID. And so here's our photo. I think it looks great. It's really excellent photo, and a few more just of people mingling. And this is, as I was really encouraged and heartened to see how much everyone was enjoying the discussions that are going on at the break. We had to push people back in after the break to get back into the sessions. And that's really a good sign, right? People are here to connect with each other and to see the science. It's a dual purpose meeting, and that was really rewarding to see. And I really appreciate seeing some of the senior scientists making the time to talk to all the early career scientists, because that is a really big part of this meeting as well, is to give these early career scientists the opportunity to start meeting people and learning where they can fit in the field in the long run. We had a lot of fun going to Sunita's Brewery. That was super fun, having beers and chatting with old friends and new friends. And just one stat here: 185 total oral presentations. That's pretty solid. This is almost like a conference level, and 49 posters. So that's good. So thanks everyone for doing that. Reminder, just please send your poster image with any details you would like for the online poster gallery and any presentations if you have not already submitted them to Elizabeth, so we can post them to the website. And there is the CG YouTube channel, which has all the recordings of all the sessions, and you can go back and listen to specific talks if you missed some. Take your posters home today, or they will be recycled if you want to keep them. And also, you should have received a survey. Is Elizabeth here? They have received it? Oh, at 5 o'clock. Okay, you're going to receive a survey very shortly, and please fill it out. It's we're asking basically about how the workshop went for you, asking some questions about all sorts of things, and including things like which working group sessions did you like, which cross-working group sessions especially, and which types of new cross-working group sessions you might like to hear about in the future, and basically any feedback you can provide to help us make this meeting better going forward, to benefit you the best. And then also, most likely everyone here is on the mailing list, but if you're not, please join the CSM mailing list if you want to stay involved. There's a bunch of different mailing lists for different purposes, and you're welcome to join any and all of them that are relevant to you. I think that's it on that. And so now it's really turning over to questions or comments, and we could, I guess, bring up the Slido. So as far as I know, when I checked earlier, there wasn't really a lot on the Slido, so that was an experiment that didn't work, or maybe we need to find a better way. Sometimes in the past it has worked, so I guess an experiment, I don't quite know why it didn't work this time, but we'll have to find it a different way. But so we can go through those, but really at this point, I want to just open it up for questions or comments from anybody. And I'd like to ask us to start, if there's an early career scientist who's brave and wants to get up and ask the first question. We haven't been doing that as much as we probably should have at this meeting, is encouraging early career scientists to get up and say something. That is something we try to do in other settings, and this is maybe slightly more intimidating, which is not a great reason not to do it, but so now I'm realizing that. So if there's an early career scientist who'd like to jump up and make a comment or a question, let's try to do that first. All right, we can do a little bit of an awkward pause and see how long we can last. Is there anybody who wants to get up and say, hey, I really enjoyed it? Hey, you guys don't know what the heck you're doing. Okay. Okay, nobody's going to do that, so another failed experiment. Okay, now let's open up the questions. Okay, we can go through and maybe we'll go through these questions. And I have not really reviewed these other than quickly scanning, and some of them may have come in. Oh, it looks like there's maybe more in them now than there were earlier. So I will just start with the first one. And I'm going to draw on help from the other co-chairs or other leadership of CSM, or really anybody who wants to help me answer these questions. Okay, nobody seems willing to talk about prioritization here. New MIPS are proposed and higher resolution and larger ensembles and higher tops, but very few discussions of what is more important. Is it informing the IPCC, doing new advanced science, improving the model, broadening the user base? I don't think CSM can do all of this at the same time and given current resources. After CSM 3, should we stop for a while and figure out the differences between CSM 1, 2, and 3 much better instead of going for shining new things? Yeah, it's a good question, and it's one that we wrestle with all the time. John in particular, since he's arrived here, has been really trying to force us to make, to have these conversation discussions. We did not discuss it here, and I think it's a little bit hard to do in the CSM workshop context. But we are going to have a meeting tomorrow with the CSM working group co-chairs, the CSM advisory board, and the SSC, and that is going to be one of the topics of discussion. So it's a little hard to do with a group of 200 people to talk about prioritization. It's hard enough to do even with a small group, and it's almost impossible with 200 people. But so we are thinking about it. There's a lot of good questions there about how we prioritize, and I don't really have great answers for you. I think we definitely prioritize participation in CMIP level activities. I think that's been a long-term priority, and we're going to continue to do that. But there's reasonable questions asked about whether or not we should be moving, how aggressively we should be moving towards high resolution or ultra high resolution. I think we've seen a lot of really strong evidence that going towards high resolution, quarter of the atmosphere, tenth of the ocean, is really clearly a useful model configuration for us. And that we'd like to pursue going forward. Going to kilometer scale is a little bit less clear to me, and I think to a lot of people, but I think you can make a lot of arguments for why you'd want to go to kilometer scale, and part of it is if we're just being honest, is future-proofing for CSM, that there is going to be some need in the long run for us to be able to do some high-resolution capabilities. There's lots of scientific arguments for why you would like to have a configuration that works at very high resolutions, even for short time periods, to understand scale interactions. There's being able to sort of keep up with new technologies that forces us to move into those new technologies faster than a lower resolution version would do. And there's several other reasons. And so, again, we are, John and I are actually starting to work on a document that will get a lot of feedback from many people here in the room that helps us rationalize this so that we can make sure we have a strong understanding of that, and that after reviewing that document as it gets built, that we really still believe that that's the way to go. So I will stop there and let anybody else want to chime in on this. I feel like this is probably our biggest challenge, right? It's the biggest challenge for CSM, and we have kind of prided ourselves over the years on being a model that can do a lot of things. We have a very flexible system, and a lot of you are here because we have that flexible system, right? That they have the ability to study a lot of different things. So it definitely is something we have to play off each other. Also, the other thing that I think we're definitely going to prioritize is ensembles. I think we've seen throughout this meeting, and every time I go to any meeting that shows CSM results at this point, it's all, so many of them are showing the ensemble simulations and our ensemble prediction simulations. So I think that is really, really clear that we need to do another large ensemble, and I do think we should be thinking about creatively thinking about how to build an ensemble that's even more useful than that last one. And I'm particularly interested in parametric uncertainty, but there may be other things we want to do there. But that is going to be a discussion we're going to have over probably the next year or so. You know, right in the last 6 to 9 months since I've started, we've really been trying to say, can we get a configuration together? And then once we're kind of feeling close, like we're going to get there, we'll have more energy to think about exactly how we're going to use it. John. There's a mic there. Mic's there, yeah.
I don't have much to add on what you said, but to give you a bit of a break from
Yes,
feeling
thank
you
you.
have to respond to all of this. I think the thing we need to think about is how we prioritize before we think about what we prioritize. And that's a much more impartial conversation and something to think about. So it's easy to wade in and go, should we do high resolution or not high resolution? But the question to start with is, well, how do we make the decision? We've got a finite resource. NCAR invests a certain amount into this activity. There are partners that are involved in investing in certain areas that we develop. And all of those have got a stakeholder, a stakeholder say, a say in what we should do. But the role of CSM and the activity is to allow the best science to get done in the US and potentially internationally. And so how do you if you think about customers, think about the community as customers, and think about the resources serving that and working out, and think about Apple, and sometimes the phone does what Apple think. You have to make some decisions on what you give people, but you've got to listen to what the customer wants, essentially. And it's that process that we've got to refine. We don't want to listen to the loudest voice. It might not even be that we want to listen to the biggest group, or maybe it is. I don't even know the answer to that. But these are the kind of things we want to pin down. What are the drivers? What are the things that we need to change? Where are they coming in? And so to build up a bit of a framework that allows us to prioritize, we're more likely to be able to prioritize then than we are by just sitting with a blank sheet of paper and going, oh, well, should we do high resolution? Should we have more complexity and these kind of things? So hopefully that's a bit of a break for Dave on that question, but I think that's what the document is that we're trying to put together. And then, how do you do the engagement to then build up that priority?
Okay, let's take this question on urban and high resolution. I'm not going to read through it. You can read through it, but essentially it's asking is if we move to high and ultra high resolution, will we have the ability to resolve urban scale processes? I think it's an interesting question, and in this I think it's sort of talking about sort of through the atmosphere. So, for those of you who don't know, CLM has a pretty sophisticated urban scheme, which gets more sophisticated all the time, and so it has been used historically to understand the impact of, say, climate change or atmospheric forcing on the urban climate, more so than actually the feedback to the atmosphere, because the scale hasn't been right. So we've been able to ask pretty interesting questions about what is the urban climate going to look like as you add air conditioning, as you change white roofs, or as you kind of implement white roofs. And it's been really a productive use of the model that maybe not everyone here is aware of. But as we go to ultra high resolution, I do think you can start asking the questions about, is your circulation or your atmospheric feedbacks going to change from large urban regions? And certainly I know regional models find that. So I do think we have the capability. I think one interesting feature we have in the urban model, which could be applicable here, is that we have the ability to evolve the urban characteristics through time or in time slice. So as building codes change, or we can go for more efficient, that actually changes the urban heat island effect as people, especially in the global south, move from more subsistence type living to more urbanization, more modern urban climates, urban regions. You might be able to see some interesting feedbacks there. So that'd be kind of a new space that we could kind of enter into in the urban world. I will say one limitation that I'm aware of that a real regional model would maybe focus on, like WRF, is actually capturing the fact that urban, especially high density urban, is actually getting 3D into the atmosphere, and ours is not. There's no concept of essentially the urban skyscrapers affecting the flow or anything like that. They're just there's roughness term, but that's it. So we would be limited on that capability. Anybody else want to add anything there? But I do feel like it's an interesting area that we could move forward on. Okay, from Meg, I've seen a lot of discussion around CSM1 remaining an incredibly useful tool due to the comparatively low model cost. How do we strike a balance between developing a cutting-edge global model and ensuring that it's usable by the broader community? Yeah, that's an excellent question. I've gotten that question more than once in this workshop. A lot of people like CSM1 because of its speed, and it was a decent model. For definitely lots of the model was good. I think a really good atmosphere model. The land model was carbon cycle model was very deficient. So we would not promote doing any carbon cycle research with the CSM1 land model. So it's the eye of the beholder. We have not had a ton of conversations, honestly, about supporting CSM1 going forward. If you asked me today without any conversations, I would say we're probably not going to do that. That would be the kind of thing we have to drop off to be able to maintain our sanity and ability to keep up. But that would be the kind of thing we would need to decide in this prioritization type of exercise to see if there was enough support for that to consider it. But if I'm being honest right now, I would say that odds are we would not be able to support CSM1 for too much longer. It looks like Ali wants to maybe add to this, and then John.
Yeah, I just wanted to say that on the atmosphere side, we have an NSF-funded project to try and keep CAM4 and CAM5 physics alive within subsequent generations, so we could at least maybe have cheaper options that people can mix and match on the atmosphere side with better carbon cycle and things like that.
Yeah, that's a really good point, and that's something that we are sort of planning to maintain is the ability to run CAM4, CAM5, CAM6 physics.
As you've already said, it's a prioritization issue. I might phrase this in a different way. The amount of demand for a fast model, which isn't necessarily a legacy model, is something we perhaps want to consider. So to what extent can we have traceable differences between our current model and a fast version of it, because there's much more benefit to come from that. So there's more work involved in that than probably looking after a legacy model, and therefore we might not be able to do it, but that would be optimal, because then all the work links together and we're not dealing in that space.
Yeah, absolutely. And we were talking with one of the breaks with Jane, okay, and that's the strategy the UK team has done, is they've built their so-called fast model, although she said it's not that fast, but that's fine. The faster model, again, that's the thing. It'll be the same. It wouldn't be that fast for us either. So we could build a faster model, and that is definitely something we consider. But that probably would actually be more work than supporting CSM1. Unfortunately, I'm not sure about that. We'd have to talk to our SE team. Betty.
So you probably know what I'm going to say. CSM1 is the only model that has isotopes, water isotopes, coupled right now. So if you went to the Paleoclimate Working Group session, I'd say at least a third, maybe a half of the presentations were using that version of the model. So we'll have to get isotopes into CSM3 is what it comes down to.
Yeah, as you know, I'm fully aware of this, and it is a problem. It's a significant problem that we don't have a near-term solution for.
And then CSM 1.3 is the only model that we have for high-res.
Yeah, exactly. So, yeah. So let me just say, we will be having conversations about this, and we will try to engage with the community about making a decision about how to go forward on this, following the sort of rules we're going to try to lay out about how to have these conversations productively. And as John pointed out, we don't want it to just be the loudest voice. We really want to come up with equitable decisions that are to the benefit of either the science or the size of the community. We have to come up with rationale. Yeah, Dylan.
I just want to echo a comment that was up there that is no longer up there, and it's on CSM1. Just porting it to derecho would also be nice. Even if you don't maintain it or service it going forward, having it on derecho for people to use if they want to would be nice, if it's not already there.
Yeah, Eric's probably going to comment on that, and
okay,
he's going to tell us. It's going to be like an hour of work. Right?
No. Well, I just want to point out that our support policy is that it's already not supported. So other than for paleo. So.
Support policies can be changed. That's
okay.
To be
fair
fair
enough.
Yeah.
Okay. Okay. But also it would there would be a lot of work to do that.
Yeah.
Is it worth it?
Okay, there's a question from Eric about our support for Cupid. This is the unified post-processing and diagnostics package that we're building from the ground up now as we kind of moved away from the NCL world and our diagnostics capability. So we don't have much support for that, and John is fully aware of this. I'm fully aware of this. There's a few things in this space where I think, we're really hurting. Yeah, we can look at these things and say what is slowing us down the most, right? Among the things we don't do, and I would say that this particular lack of a robust and easy to use post-processing diagnostic system is one of these things which is deterring progress. I think that's my opinion. Now again, we should ask other people. So I do think it should be a priority, and I think John kind of agrees with that. But you know, we don't have an immediate source of additional funding. I will say I've been pretty encouraged by the grassroots effort, and it's not the best way, and John's probably going to hate me for saying this, but you know, a lot of things in CSM come through grassroots activities, and if we can distribute the load across this large group of people here, I think we can make a lot of progress with a lot of people putting in not that much work. And so we are trying to build the structure of it to make it possible for the community to contribute. We had, like I mentioned in my first talk, have some evidence that might work, you know, but we really have to build the core scaffolding for people to be able to do that. Okay, question I guess is Jim Everidge, but really coming from Alan Robach. Does CSM provide a low resolution version that grad students can use for homework assignments? This would be for a general course in climate modeling. Is there a way to run experiments and use your tools to visualize and analyze the output? For CSM2, right, we had the 2-degree version of the model, so I guess it would be nice to have Alan here to know if that was a fast enough version of the model, which was, I guess, was that functionally supported, not scientifically supported? We actually call it scientifically supported. Anyone here know? Scientifically supported? Yeah, so right now, CSM2 2-degree version would be probably what we would recommend for this kind of application. And we do have some visualization tools through a lot of our tutorial stuff now. Everything, all of our tutorials are being built in Jupyter Lab, and so that a lot of those tutorials include visualization that could be extended. So I do think we have some of the infrastructure there. I did, you know, after my talk, I got a few emails from people saying that they had actually developed some materials. Specifically, it was Jen K. Said she had developed a course on using CSM for a climate course, and I'm guessing there's quite a few other faculty around the country who are doing this, and it might be a thing we could do. Maybe looking at Elizabeth, maybe, but you know, you're really interested in the education thing. Maybe we could try to get a survey and a sort of a understanding of what you know, faculty around the U.S. and maybe around the world are doing, and hopefully they could do some cross-fertilization of some of those activities and not all be reinventing the wheel and producing new courses. That's something we might be able to try to do. Will?
I'll just add that Donica Lamberdazzi is leading up on the land side, a land model kind of curriculum development platform that's using the Neon tools, so single point simulations that people are starting to use in classes. So if you're interested, I'd reach out to Donica about that.
Yeah, so I'll see if I can spearhead an activity there to try to get some sort of understanding of what, you know, how CSM is being used in the classroom. I don't think it's going to be like at the top of our priority list, but I do think it'll be useful. So I'll try to I'll put that onto my to-do list. Okay, there's, let's see, I saw, I think from Brian, which disappeared about the second one. Oh yeah, okay, yeah, oh yeah, okay. Yeah, the cost for newer capabilities. What are the community's ideas about how we can better coordinate ultra high resolution science, given that the cost of the model is going to be out of reach for the vast majority of science teams? Yeah, so Brian knows my answer to this, so he's seeding this question to see how I answer. I don't see if it, what's that? Okay, yeah, let's get somebody else to see it, how they would want to answer it, or you know, like Gokon or somebody other than me who's going to give that answer. Yeah, Eric.
Thanks. Yeah, I don't know. I guess maybe the first thing to do is admit that, first of all, there's no such thing as a 3-kilometer climate model, right? I mean, DOE may have ambitions to do 1,000-year control runs and, you know, bounce top of atmospheric energy balance and so on. And maybe the other thing to admit is that maybe there's no such thing as a 3-kilometer community model. You know, the notion that people would download this or get an account on Derecho and run their own experiment is a bit sort of futureful, at least for now. And, you know, in the alternative space to that, you know, maybe something that could be feasible is a small number of, you know, integrations that, you know, the community could somehow agree on, and then be curated and hosted and served to people who wanted to look at particular things. You know, if you're going to do that, then, you know, I guess I have at various times encouraged various people to coordinate, to organize a kind of community workshop on, you know, what would be the reasonable science drivers that could be used to develop protocols for 3-kilometer MIPS. You know, so I know, for instance, that Allison Wing is interested in convective organization, and Diamond has done that too. That may be something that's already been done. I've seen people do interesting things with cloud microphysics, with 3 kilometers sort of global models, and that's something that can be done with relatively short integration, so maybe that's something that's approachable. There's a community of people who are interested in gravity waves. You could do relatively short simulations, and I think you could learn a lot about, is it really true that the way our gravity wave drag parameterizations work represents how the atmosphere actually works? I could easily imagine things like, you know, climate process team, you know, groups organizing around these things. For example, the way that people use LES models as if they were the truth to develop parameterization schemes, I think has actually kind of worked, you know, and it's possible that gravity waves have a similar sort of tractability in 3 kilometer sort of simulations. And so, you know, I think there's a lot of people who just, you know, when I see presentations on 3 kilometer, a lot of it just sort of ends up being a discussion of software and hardware. You know, how do we get these things to run in our model? Our Brian Dobbins is very eloquent at describing just how small your computer is compared to the thing you would actually need to run this beast. And so that's so all-consuming that I don't know that people have had the bandwidth to really think about, okay, what would be the things to do? People will tell you that, oh, I want a global model that gets the eyewall replacement cycle of a tropical cyclone. Well, I'm not sure why you exactly need that. We want a model that's global but also does mesoscale convective systems, but how exactly are you, what's the science question that you're really going to address, and how can you be specific enough about that science question that you can use it to devise an actual protocol that, say, a number of modeling centers could agree on? Because certainly you have a good, you're going to develop 2 dicores, I guess, here. GFDL has one. In the DOE world, there's one. ICON has one. Certainly, you know, there's scope for coordinated modeling experiments if you can decide on, if you can be specific enough about what the things are that you're really looking for, and find configurations that are tractable. You know, and I know, for instance, at GFDL that Nadir Javanji and Tim Merlis have a lot of good ideas about these things. You know, it might be good to talk to them about, you know, what you might like to do. The other conversation that I had last evening with Christian is, hey, you know, make the world smaller, right? I mean, there's a word for this, right? I forget, it's called the deep atmosphere approximation or something. So I think in her telling, it's just, well, you know, you just set the radius of the Earth to be 1/10 of what it actually is. But oh, and by the way, if you want to get the Rossby deformation radius to match, then you have to spin the world 10 times faster. Okay, well, we can do that. That's not a problem. You know, and so you could start to invent these kinds of configurations that would cost a lot less to run just because you're reducing the domain size. You know, and I've heard of this hypohydrostatic approximation, you know, where you just weight the vertical acceleration term and it slows everything down, and then the CFL condition doesn't kill you, you know, and so then again you get some savings because you don't need these tiny time steps, you know, and so those kinds of configurations I think would save you a lot of compute cycles, but they're going to be sort of bespoke to certain kinds of problems. They're not going to work for every single problem that you might want to do. I don't know if you can look at the interaction of gravity waves in the QBO on a planet that's 1/10 the size of the Earth and still get the right answer. You know, I don't know what happens to the phase speed of the QBO when you cut the size of the planet by 10. But those kinds of things, I think, that might actually be a community model, you know, because people could actually run those kinds of configurations. You just, I don't know whether there are good enough science drivers to make it worth your while to do those things. So, I mean, those seems to me to be the conversations that ought to be going on, and they're not going to go on perhaps right away just because people are still kind of consumed with the question of how do we get this thing to run on our computer. But I think that's how you get around the fact that there's no such thing as a 3-kilometer climate model, and there's really no such thing as a 3-kilometer community model either.
Yeah. Sarah.
So I just wanted to add a bit about if something is computationally very expensive, can it be done at a university? I just want to give an example. So some of the most computationally intensive integrations with CESM are actually done in collaboration with Texas A&M that Dave Lawrence showed. And having a community facility will certainly allow a few universities to interact with NCAR in a much better way. It may not be for all, but a particular university which had a particular expertise in some aspect of that could work with NCAR in this setup. But I mean, this the IS runs, which now are funded by, the continuation is funded by NSF. The Mesa Clip runs are a really good example of that.
Yeah, I'll just add on one more thing on top of that is, I guess I look at inspiration from all the people here. And so you just go to the sessions we saw at this workshop, or you go to AGU and you see how people are creatively using the large ensemble for stuff that we never even imagined, and how they're creatively using our prediction experiments in ways we didn't even imagine. So I think we have to keep that in mind, that there's going to be, even if we only produce a few short integrations, people are going to find some really creative ways to use that in ways that I can't even anticipate right now. And so I think we just have to sort of, and it's a little bit unsatisfying me, but I think we have to plan for that innovation that's going to come from this, from the power of our community. And I think that's another place where we have a little bit of a benefit from some of these other modeling centers, which are doing a little bit more prescribed stuff, is that we might have this, this community which might take it in a direction that we can't anticipate. So that's what I'm sort of hoping for as well. Okay, do we think, I'll go to the next question. Do we think a priority for CSM is to increase the usefulness and usability of the model for applied purposes, I guess as actionable science? And if not, how can we be more responsible in communicating the limitations of our model for use outside research context? Does the community think we need better to manage misuse? I guess that's a question for the community, kind of. Does anybody want to make any comments on that? I have thoughts, but does anybody want to respond to that at all? I think I think certainly it's a priority for CSM to make it an easily usable model by the research community. That's clearly a priority, and we're doing that as much as we can. And most likely then it will get used for applied purposes. I think there's no question that's going to happen, and we'll probably be participating in that. At NCAR and with our collaborators across the country and the world. Personally, I think the more accurate a model we can get, the better it's going to be. So that's why I'm really excited about the parameter calibration work that's coming through LEAP and other activities to kind of bring us towards a model that's a little bit closer to the real world. I don't know if that's actually going to give us better information, but to me, at least intuitively, feels like we're probably better. In terms of the question of in terms of communicating the usefulness of the model, yeah, it's an open question, right, about how to really establish that. Certainly, I'm sure all of us have seen in the literature use of the model in ways that are incorrect, and I don't know how we really stop that. I don't think there's going to be an easy way to do that. And historically, our kind of idea with how to use the model in general, like we have this discussion in our development team meetings, it says, should we just stop people from being able to do this thing? And our general thing we say is no. We're not going to stop people from actually turning on this configuration and setting up a model in a way that we haven't done before, because we want people to have the creative ability to do that. And just knowing that they may run into having a sort of nonsensical, that's their responsibility. So it's a difficult space. I don't have a super great answer for it, but John, if you want to add. What?
I didn't stand up to give a super great answer, no. But an answer, I think if we're trying to get to, if we're trying to make the model better, which is what we are, and trying to reduce biases and have the best possible representation of the Earth system, then it will become more applicable to applied purposes. So the answer to the first question is, yes, it's a priority to increase usefulness and usability, because getting it better should do that, and that's what we're trying to do. So I don't think it's not. That doesn't mean that we shouldn't explore ways in which we try to communicate what we think are the strengths and weaknesses of our capabilities more openly than perhaps happens already. And follow the likes of and there's been discussions along the lines of how to best use observations. We can begin to describe how you might use and not use our models more. Again, it's one more thing to do, of course, but it's and it's quite a big question, that one, and it's being discussed, and we know it's hard, but it's important too. So I think they're the answers.
Yeah, I totally agree. It's a big task. I think the openness of the CSM community we need to continue to lean in on that. We do things like publish a paper that shows we had the wrong, an ECS that didn't support the last cluster maximum, and that's the way we should do it. We didn't hide. We could have chosen to say we don't want anybody to know about this. That once we found out that result, but we published it. So. We're always going to push for that openness, I think, and that hopefully will help with this. Okay, in 10 years, what will be the role of machine learning in CSM? What role will CSM have? Yeah, it's a pretty big question. Boy, in like 2 months, right? Machine learning is changing so fast, right? It's so dynamic right now. It feels like predicting 10 years is probably futile. But I'll just repeat. I do think we have the opportunity, right, to build a hybrid model. Right now, we have that potential to build a hybrid machine learning physics model, replacing some parameterizations with machine learning based parameterizations, targeted ones where we're doing that our current parameterizations are not doing well, or trying to resolve processes that we really don't have we really just can't capture with our current parameterizations, and in sort of a practical sense, we have 2 big projects with significant funding behind it, and so I think we should take advantage of that opportunity, which, we don't know if that would come along again. So that's the M-squared lines and LEAP, which are really behind this right now. So that's definitely a priority of mine. We'll be discussing this throughout the next couple of years, probably with the SSC and others who are involved in making decisions about the direction of CSM, but I do feel like it's an opportunity. Beyond that, it's a little bit more murky. I think there's a good chance that we've already seen quite a bit of evidence that there's ways to use machine learning to improve the output of the model, or to improve the utility of the model in terms of understanding predictions. I've seen a bunch of good work on that, so I think that's definitely going to expand, and maybe we can build some more standardized kind of processes with that. And then I think there's a decent chance, I don't know if it's our responsibility or not, but I think there's a decent chance that machine learning is going to help with downscaling quite a bit if we're trying to get actionable information, and that may be a pretty good path towards getting more actionable information out of large ensembles as to using machine learning-based downscaling. Whether that's our responsibility or whether we just kind of support that, the community that wants to do that isn't as clear to me. It feels a little bit like outside of our core domain right now. Anybody else have any other thoughts about? I mean, the other big one would say we're going to build a fully machine learning based model all on AI, that like Klima's doing, I guess. And for my sort of obvious, I think you're going to guess my reaction is that that's what Klima's doing. So they're taking on that kind of challenge of trying to see if they can do that. And our strength is in building parameterizations and building a fully coupled model, and we should lean into our strength. But does anyone have any other ideas? I know that there's other ideas. Dan has some good ideas.
I think one point that maybe didn't come up as much as it could have in the machine learning session is the extent to which some of these techniques could revolutionize the model development process, and that we're in an era of rapidly increasing numbers of observations. How do we bring these objective constraints to bear on the model, and hold ourselves to that standard? So one thing that we're talking about is if we can, is our role to construct emulators for our models of the Earth system, and if so, then data assimilation becomes extremely cheap, and maybe the way that we iterate on the model, if we want to check something, we don't have to integrate it for 1,000 years, right? It's much quicker. Or alternatively, is our role to keep focusing on the process and kind of think that we're going to outsource some of that emulation to others. So I feel like it's good if we can make these decisions deliberately.
Yeah, that's a good point. Yeah, there are groups trying to do that, right? Some of the emulation for filling in the space. Yeah. So again, should we be doing that, or should we be leaning on others?
Yeah, I was just going to add that in terms of the technology for the parameterizations that Dave is talking about, our goal is to try to have a simple framework where you can take like a PyTorch network and plug it in. So people who don't want to do model development and want to change a parameterization that is machine learning based, can train a new set of data and just replace it with a nameless option. So we're trying to think about making it as maximally usable for the end users as possible. If you have ideas, if you know, PyTorch or TensorFlow are both compatible with each other, so we've been looking at some PyTorch bindings, but I'm definitely happy to hear from anybody. We want to make sure that that aspect of it is as usable as possible for people without digging into the code.
Okay, so we're coming up just a few minutes left, and so Jim has a question here that I think is really outside of our ability to answer it. It's essentially a political question, but it's an interesting one. We can have it. That's over a beer kind of question. But I'll just say, if anyone here wants to ask one more question, we could try to address it. Otherwise, we can close. I'm happy to go through and move it out, respectful of people's time as well. Well, Elizabeth is actually asking a question to all of you here, and I think it might be the answer. She wants to know, is there better ways for us to communicate with you? And I think maybe you can answer that in the survey. There's an open space in the survey if you would like to think about ways you would be better communicate on status updates with CSM. You know, do you feel like you're not tracking what's going on closely enough? Too much information? You know, too many meetings, not enough meetings? All those kind of things. We'd like to hear about it. Great. Is there no more questions? All right. So thanks very much, everyone. Really appreciate everyone's contribution and keeping us, holding our feet to the fire with these kind of hard questions, and for all your contributions to the project. So we'll see you next year, and hopefully before. Bye. Oh, yep.
I mean, one last time, we've got to thank Dave for organising, running the project, doing everything that you get. Standing up here and taking responsibility to answer all your questions as well. So, but also then one last thank to we thanked at the start, but let's thank again all the organisers, everyone that's made this work all week, events and services, Elizabeth, the whole team. Thank you very much. It's been brilliant.